You can check with your slides because that's so which one?
Zoom is Zoom PDF should be absolutely no problem. But let me try.
Because you use some different form.
No. That's when I have animations.
Okay, but here this one is fine. If it is just
you're able to see, right?
Yeah, I can able to see. Yeah, this is fine. Present as let's so yeah, this is fine. This is fine. Yeah, yeah.
Hi, Archon.
Yeah, hi Arul. Sorry, my microphone was muted. Yeah. How are you? Long time no see.
Yes. Well, we all survived as we can.
Yeah. Let's hope. Yeah. We're getting the final booster doses now, and from Omicron.
Okay.
So hopefully, hopefully things will be all right. We can have our, usual in-person discussions.
Right.
Anyway, great to see you. And you were also sharing the session, and now look forward to your talk today.
Thanks.
No, it becomes difficult in online, I mean, in office, suddenly somebody calls, and there is this meeting, that meeting.
Absolutely.
You cannot really get away. I mean, in a conference, when you're outside somewhere.
No, you can't concentrate, right? So
yeah, that's the biggest thing. You can't concentrate. You can't get away for the full day. Anyway, but due to the help of all of you, we have still managed to at least have some wonderful talks here. And,
No, it's very nice. Again, I couldn't attend a lot of them, but it's a really fantastic conference. You guys.
Yeah, some of them at least. Yeah. So all of them, nobody could attend, not even me. But at least some of them, if you have.
It's a very comprehensive set of talks. Yeah. But they're all there on YouTube, right? Recorded.
Yeah, they're all there on YouTube. So anyway, if anybody wants to hear them at any point, so.
Yeah, it's fantastic. Yeah.
Good then, good. Yeah. And some of our young kids, they are more this tech savvy. Say what do they do is they mostly sleep during the day, and then later on at night listen to the talks. So that's why I found from my.
You're actually describing my class. You're describing my,
I see. Yeah. You're of course absolutely right. Yeah.
So I was actually told that cheerfully that everybody knows students turn on the thing, go to sleep, and then they.
Exactly. That is what it happens usually, and but we have to take it now. What to do? We can't really. I mean.
Yeah. But I think hopefully you'll start soon. Yeah.
Certain things hopefully we have already started, and unless there is any other, there is no indication worldwide of any other kind of dangerous variant. So at least in that sense, we are.
Yeah, the world has started fighting, so I think humans have started killing each other. So I think
exactly.
It will become normal now.
So that's good indication.
Yes.
So that's a very good indication. Certainly it is. Yeah. So also, who else is around? Yeah, Aravinda also.
Hi, Archandra.
Yeah.
How are you?
And all of us. Yeah. Okay, going on. This is the best we could do. And towards the end of the pandemic, we thought we haven't met or seen anyone. Of course, we have had some kind of online interactions using our Quest and other things also. But then we thought, let us have a little bit of opportunity to warm us up, and then kind of let's hope very quickly we can resume our in-person meetings, etc.
Yeah, I miss this Kolkata. Really.
Yeah. As soon as things open up, you come down. So we are towards the institute. So you visit us and stay for a while, and then we can have some really business kind of dealing, because conference is fine, but if you have to get to the heart of things, I mean, really, you need some close-knit interactions. So welcome to visit anytime. And where is our session chair, Professor Alok?
I don't see him yet.
Yeah, Professor Alok is yet to. Of course, it's only 5 minutes, so These people are very kind of, what should I say, punctual, not like us old timers.
I actually thought that I was session only for one and I goofed up. My first session, I goofed up.
No, that is not an issue. I mean, of course.
Yeah.
No.
I was in the middle of something else. I saw only one session, and then I said, okay, so I marked that. So and then
yeah. So we have been quite liberal in actually imposing this on our friends.
It's perfectly fine. It's just that I didn't look at it properly.
Yeah. No. At least I mean somebody that's Mihal Horodeki. He actually even missed the date and schedule of his talk, so he had to be called by other people, and we had to start somebody else's talk, things like that. So these things happen actually.
Yeah.
But fortunately, at least apart from Chris Fuchs, we have had no cancellations, and Fuchs was indisposed, so we couldn't help it. But otherwise, we've had pretty nice, strike rate.
Oh, Guruda. Hi, Guruda.
So Professor Guru Prasad Sir is there, and so you can take over.
Yeah. Today also, Multipartite is speaking, but by mistake, we have kept him in contributory talks, but he's actually professor at his institute.
Yeah, he is in Chennai.
He's in Chennai Institute of Technology.
Yeah,
Chennai Institute of Technology.
No problem. He is our, he is one of us, so he will not mind, I hope.
Hi, Guruja. How are you?
Yeah. Arvind.
Yeah, nice to see you.
So how are things on your part?
Guruja, started slowly.
He is in a holy place, no? I mean, the holiest of holies in India.
Yeah.
Varanasi.
But Tirupati town is not on the hill, I think.
No.
So your institute is in the plain.
In the plain. Yes. Yes. So we are going to shift by May completely. Already few sections have shifted. As of now, we are in the temporary campus. So it is just within 2 months we will be complete. It's built. Building is almost done. We are just waiting for fines.
Hello, Devashish.
গুরুদা অলোক তো জয়েন করবে না, তুমি শুরু করে দাও তাহলে।
হ্যাঁ আমি শুরু করে দিচ্ছি।
অলোকের কি ছেলের কি একটা পড়ে গেছে নাকি, স্কুলে যেতে হবে ওকে?
আমাকে রাতে স্বপন ফোন করেছিল। So
hi Devashish.
Maybe.
Yes. Hi Arul.
Hi.
So how are you? Fine. Okay.
As you can see, alive and talking.
Yes. You are fine. Okay.
Yeah.
Okay.
So our first speaker will be Arul. Already he has shared, I think, through sessions, so he has been introduced, but there is some formal introduction which some students are sending us. So I just read it. He completed his PhD in theoretical physics at the State University of Newark at Stony Brook. He was postdoctoral fellow at the Physical Research Laboratory, Ahmedabad. Currently, he is professor at the Department of Physics, IIT Madras. His current research interest is to study quantum chaos, quantum information theory, chaos and transport, mathematical physics. But Arul is a very popular figure in this community that, and I know him since for last 20 years. And I saw him working in this field. So, okay, over to Arul.
Thank you very much, Guruda, for a warm introduction and welcome. And it's a pleasure being here and at this very nice, fantastic meeting, actually, with such a collection of talks. It's an honor to present. I think you can see my screen. Yeah. So.
Yes.
Okay. So. Yeah. Thanks. So. The work which I'm going to talk about in the next 40 minutes is done with Suhail Ahmad Radha, who is a PhD student here at IIT Madras and also with Aravinda, who was a postdoc here and is now at IIT Tirupati. It's partially based on these papers, but there is some things which I'll talk about, which is also recent in these papers, and not talk about many things which are there in this paper. So I'm going to talk about construction of dual unitary operators and maybe why they are interesting to study. In fact, two of my collaborators have given very nice talks. One of them, Aravinda, who talked about dual unitary circuits, and Karol Szyszkowski, who talked about the AME 4.6 problem of 36 entangled officers of Euler. So they're all in one interconnected set of things. So I'm going to talk about around these things, but both of these talks have laid the foundation. So in case anyone is interested, these are all related talks. Okay, so the outline of my talk is kind of here. You can see. So first, I will motivate why we may be studying these kind of objects, and then talk about some definitions and measures that are useful. And then talk about channels which are constructed from these dual unitary operators. I think they are interesting also from a perspective of open quantum systems. And then talk about how to construct these dual unitary operators, which was the title of my talk, namely concrete constructions of dual unitary operators. I'll talk about some numerical constructions based on nonlinear maps, dynamical maps, as well as some analytical constructions, and then I'll summarize. So as it is well known and appreciated, quantum many-body systems are, interacting quantum many-body systems are difficult in general due to various reasons. Strong interactions, the dimensionality of the space is exponentially growing with the number of particles, and so on. And obviously, it is also a central problem in physics. But for us who are doing quantum information theory and quantum computing, these also appear as quantum circuits because we are putting together many gates to perform some algorithm. And then we are performing the algorithm, which is a time evolution. So here, so essentially every quantum circuit is a many-body system, and in fact, all examples of a quantum computer are interacting many-body quantum systems. So we wish to look at minimal models of many-body systems in the sense that minimal meaning minimal complexity in construction of the model itself, but to keep the essential aspects of these systems intact. So here is an example that made some news a few years ago with the so-called experiment where one is trying to establish quantum supremacy in this Google Sycamore processor. It basically consists of things that I'm kind of talking about. It consists of the single qubit gates, and these single qubit gates are interacting with two qubit operations. And this one, in this figure, the flow of time is in the horizontal axis. Okay, then you have these other qubits here. And you can see that the interaction is happening sort of randomly between qubits and not necessarily nearest neighbor. So as time progresses, an initial state, which is as simple as all products of zeros, starts developing a large amount of multipartite entanglement. And it's interesting to see what kind of state is at the end of it. And these are what one may characterize as complex states with a large multipartite entanglement content. And in fact, entanglement, as you know, is a driver towards thermalization in isolated quantum systems. So to find such a state here, it obviously depends crucially on the interaction which is happening between these qubits. So in fact, I'll be studying these kind of circuits and looking at these interactions more closely and what actually determines the complexity of the state at the end of the day. It has something to do with these interactions, but what is that something? And you see, these are all unitary operators and unitary gates. So the strength of interaction is a little bit dubious quantity at this point. And I will emphasize that what matters in these cases to a large extent, significantly, is the entangling power of these gates. And that seems like something reasonable to do. Okay, but even this circuit is kind of complex for me because it involves random interactions between pairs of qubits and so on. And also the interactions themselves can be different. There are a fixed number of them, but they can be applied differently. So it's an example of a random quantum circuit, and there has been quite a bit of analytical study because randomness also brings in some analytical possibilities of averaging and so on. So there has been a fair bit of work from condensed matter many-body system approaches to studying these random quantum circuits as models of Floquet many-body quantum systems. And there's been analytical derivation of quantities such as entanglement growth, information scrambling, and so on. And these, you can see some of these papers. Very interesting, but also many of these results depend on these averaging, as well as depend sometimes on taking local dimensions to being very large. So what we wish to do is simplify even further, and there are these classes of models. So this can't get simpler than this. So these are like brick wall models, where we have the same two-particle unitary. So these are all particles here. So you think of this as 10 particles. And there is a two-particle unitary which is acting on this. And they're all nearest neighbor. But as you can see, there is no interaction between these two pairs. But in the next time step, and this you can read as time now vertically, they interact. Okay, and you can also have in between local gates. That means one particle gates. So these are all circles of one particle gates. And so this is a picture of brick wall models that have been studied, in which case all of these unitaries are the same. So there's some translational symmetry invariance. You may take these locals also to be the same, so that there is the possibility of maintaining that translational symmetry. But even these kind of systems will depend heavily on the complexity of this two-particle interacting U here, which is there. In particular, there are certain kinds. So what are the kind of questions which one may ask? So if you were to start with some localized, say that you have some operator which is localized here, a single particle operator which is localized here, and you want to see its evolution in time, because it's the nearest neighbor interaction, there is a speed of in which the operator spreads. So in one step, it will involve these two operators, then two single particle operators, then four, and so on. So this kind of includes a light cone kind of effect here, which is coming because of the finite range of interactions. And all the correlations and so on can happen only within this light cone in this brick wall models. And if the dynamics is spreading very rapidly, we would expect that the light cone speed is achieved, and all these operators are, in some sense, getting scrambled. All these particles are getting scrambled and multipartite entangled with time. So, in fact, I'm going to study a particular kind of models in which there is only the light cone which survives, and everywhere else things get decorrelated, or there is no correlation between single particle dynamics in the interior of the light cone. So these are kind of extreme models of where the entanglement and complexity is developing very rapidly, and these are characterized by these dual unitary, these operators, these two particle operators U being special. And they are, these two particle unitaries are special in the sense that they have been called as dual unitary operators, I think around 2019, by a group of Bertini, Koch, and Prosen when they are studying these minimal models. But what are they? First of all, let me say that they call it dual unitary because there is some temporal and spatial connection, which I will come to in a minute. And of course, these models are also local. Okay. There's only local interactions which has happened. Okay. So in these models where you have this dual unitary U, one particle correlations of many body circuits are completely governed by a completely positive trace preserving map, which is specified by this unitary operator U. So this is quite remarkable. We are making some statement about quite a complex correlation function of the many body circuit, but based entirely on a property of this two particle interaction U. So in a sense, these models represent, they can be non-integrable models. They are in general non-integrable models, so you can't solve them in the sense of a spectral problem. However, they are solvable in some other ways, like trying to find these correlation functions. So there are exact results for these in finite local dimensions rather than in infinite or asymptotically large dimensions. Spectral form factors, entanglement growths have been studied. I'll come to correlation functions in more detail. And these out-of-time autocorrelators have been studied. In fact, in the talk of Aravinda, he talked in detail about these circuits. I'm not going to talk so much about the circuits themselves, and you can see these references. But I'm going to talk about these dual unitary U, which is constructing these circuits. So why are they called dual unitary? Is as I said, there's a space-time symmetry. So let's just look at a picture of a unitary. This was again there in Aravinda's talk, but just to recollect, this is now a bipartite unitary, two particles. Local dimension is Q. So unitary operator acting on that. So we have these two inputs, let's say here, there's I alpha state and output J beta, and that is the unitary operator. So it's a kind of tensor diagram representation of this unitary U. So we would think of this as the particles, and therefore these are locations. So I and alpha are locations. So the horizontal thing is space, whereas J and beta are outputs. So they are, it's now vertical is time. Okay. And in fact, you can build up circuits like this in space-time by putting them together. But what is interesting about, what is the dual? So dual is simply when you're looking at this operator as if the inputs were I and J, which is actually on the time axis. But now you think of them as inputs and the outputs as alpha and beta. Okay, so that just interchanges alpha and J in this picture here. So it's just a permutation of the original unitary operator and has been known as realignment for a long time in quantum information. Okay, but that is what is interchanging space and time. So realignment is essentially interchanging the role of space and time in this interpretation. Okay, and so in general, this realigned operator is not itself unitary. You have done some violation on the unitary matrix, you have rearranged elements, there's no need for it to be unitary in general. But a dual unitary is one special kind of unitaries for which the realignment is also unitary. So there are many examples of dual unitary operators. The simplest and most important one probably is the swap gate. It's very easy to see that the swap gate is dual unitary because it takes ij to ji. So when you interchange these two, nothing happens. In fact, the fact that nothing happens is indicated by the fact that the realignment is itself the swap. So this is even more special. Not only does it remain unitary, it remains invariant. It's exactly the same. So these are self-dual operators. Surprisingly, a Fourier transform, let's say on Q-squared symbols, discrete Fourier transform of Q-square sites, you can consider that as a bipartite operator of Q into Q. This is also a dual unitary operator, but it is not such that the realignment is itself. In fact, the realignment is quite a interesting spectral object. As we know, the spectrum of the Fourier transform is only plus minus 1 plus minus I. the spectrum of this is much more complicated and not really well said. Yeah. Is there some question? In the 2-qubit case, and I will come to that in more detail later, this is a parametrization of dual unitary operators, the one parameter family. You can see sigma x, sigma y, sigma. Sorry?
Carry on. Someone is, I unmuted him. Muzaffar Lone, possibly. Please mute yourself. Okay, carry on, Arun.
Yeah, okay. So there is this J here, which is a one parameter family of operators. In fact, for the case of J is pi by 4, for the case of qubits, this becomes a swap operator. Okay. So in this case, what is the realignment? Realignment is exactly U itself. Let's look at what happens to local unitary transforms. So if we take a unitary U and then do local unitary transforms, because now it's a bipartite system, we can do that, then it remains dual unitary. So a dual unitary is a remaining dual unitary under a local unitary transformation. That's rather easy to see because of the realignment property. In fact, so the realignment is a very special operation, but we know another operation which is like that, the famous partial transpose. So in fact, both of them play a role together. So just to remind you of the kind of matrix reshapings that are very useful in bipartite spaces Q into Q, I'm illustrating this for the case of qubits. So that's a 4x4 matrix, a unitary matrix. And the case of the realignment, which I was talking about, I have now indicated as R2 rather than just R, because you can block it into 4 2x2 matrices and just vectorize each of these blocks. So you take this 4x4 block, make it the first row, second block, make it the second row, and so on. That is precisely this realignment operation, R2. The other one, R1, is just making it into columns. The partial transpose, on the other hand, is something where there are again two types of partial transposes, which we may call either T1 and T2 or gamma 1 and gamma 2. So one in which we are blocking these into 2x2 blocks and then doing a partial transpose in each of these blocks. That is gamma 2, or just transposing the blocks themselves. So this is gamma 1. And gamma 1 and gamma 2 composed is the usual full transpose of a matrix. And it's quite interesting that these operations have, of course, been used in entanglement detection, separability detection for a long time. But their effects on unitary operators are also very interesting, and that's essentially what we are studying. Okay. So let me make use of these things. How do they input into the many-body circuit? So the connection between this block U, which is making up the circuit, and the brick wall circuit appears in certain ways. I'm going to talk about one particular way. If we look at autocorrelations of operators, so these are single particle operators, let's say at x equal to 0, at the origin. Okay? At some particular site you call origin. And then you evolve the single particle operator according to the many-body circuit in time. So this is actually quite a complex object here. And this is another operator at x equal to 0, at time equal to 0. Then you can find, well, autocorrelation really means the same operator. So I guess you can think about this as sigma itself at time 0. Then we are interested in such correlations. And it can be seen that this is equal to such a trace where this is a map, a CPTP map, acting on this operator at time at x equal to 0, or the origin. And these autocorrelations then in general decay according to with these rates alpha j. And what are these alpha j's? Alpha j's are eigenvalues of the CPTP map, which is determined completely by this unitary operator U, and is defined so. So we take this single particle operator sigma, and we can take the other particle to be in a mixed state, most mixed state. So that's that. And that is the interaction U between them. And then you trace out the most mixed state. So in fact, you can see that this is typical open system thing where you're looking at system environment and you're tracing out the environment. And this map can be written, it's dynamical matrix, or it's Liouvillean, or whatever it is that you want to call. You can vectorize this, and this matrix form of this map is given, in fact, by these realignment operations. Okay, so here is a realignment of 2 in the row-wise realignment of this unitary multiplied by that. So in general, this realignment is not unitary. Therefore, this is not in general identity. And this one ensures that it's a CPTP map. It's a positive one, and then this. So in the language of Sudarshan, this is a dynamical matrix, the one which is there inside. So you can see that there is a particular CPTP map which we may derive based on this unitary operator U, which determines sort of global properties in the circuit. Another interesting correlation is that along the light cone. So you have an operator at 0 origin, and the other operator is at time t. Okay, so that is along this line that I was talking about, the light cone. So that's the extreme. These are the extremes, autocorrelation and light cone. So here, this correlation is determined by a CPTP map, which is very similar, but you see now we are doing a curious thing of tracing out the system rather than the environment. Okay, and that leads to a partial transpose in this unitary operator, and the map is given by this. Okay, so the point is that there are, based on these unitary operators which are making these brick walls, and based on their transpose, partial transpose, and realignment, there are 2 important CPTP maps whose properties are determine these many-body system properties, especially some of them like autocorrelation. And these are related. The partial transpose and realignment are related by the swap S, and that's why actually you can see this easily, the connection between these 2, autocorrelation and light cone things. Okay. Now, I will come to what happens in a dual unitary circuit in a minute, but before that, let me talk about what happens in a dual unitary operator where U is unitary and U R, the realignment, I'm not now specifying 1 or 2, it's irrelevant, but you may think about R2 to be specific, is also unitary. What is the problem? The problem is the following. If we can take a unitary operator and do a Schmidt decomposition of it. These M's are local unitary operator bases, orthonormal bases. Lambdas are positive numbers such that this is equal to Q square, ensures the unitarity of U. And UR, the realignment, is simply given by this. It's not difficult to see that the realignment of this product is just this rank 1 matrix, which is given by vectorization of these operators. Okay, and therefore UR adjoint is spectral decomposition is given simply by this, where these are spectral decompositions of this MIA. I mean, vectorization of these operators MIA. And therefore, for this to be unitary, all you need is that these lambda i's be equal to 1. So it seems rather simple to construct dual unitary operators. However, if we simply take these mi to be lambda I to be 1, we don't know what to do with these MIA. What are these MIA such that U itself is unitary? So it's very easy to construct a UR which is unitary, but then U should be unitary. So the constraint is what makes it difficult for us to construct dual unitary operators. But the story is that these lambda i's are nothing but the singular values of these realignment, and they are themselves local unitary invariants. Okay, so now this is then an observation which wasn't obvious to those who were first using it in many body systems, that dual unitary operators maximize operator entanglement. Okay, so in that way they are very special. The swap, for example, something that's a completely non-local operation, although it doesn't create any entanglement. So dual unitary operators maximize this operator entanglement because all the lambda i's are equal to 1, because UR itself is unitary. There are many measures of this operator entanglement. A very useful one is just the linear entropy, so which is defined based on these eigenvalues or the Schmidt values of the operator Schmidt decomposition, or it can be written in terms of this realignment in this manner. And it vanishes for all product operators, and it is maximum for all dual unitary operators, including swap, and is equal to 1 minus 1 by q square, where q is the local dimension. Now, therefore, all dual unitary operators maximize operator entanglement. What then differentiates one from the other? That is differentiated by entangling power, which is the average amount of entanglement which is produced when an operator, in this case unitary operator, acts on product states. So this has been known since the work of Zanardi 20 years ago, that this average, if you take this linear entropy to be the measure of entanglement, then it's related to operator entanglements in this very nice way. And it's related by this EU, which is actually maximum for the case of duals, plus the operator entanglement is U times swap, okay, minus this constants, which are the operator entanglements of swap. So this is the entangling power of U. Now, in the case of dual unitaries, E of U is equal to E of S, and therefore, this entangling power for dual unitaries is simply given by this EUS divided by ES. And what is this EUS? This operator entanglement of U times swap is actually related to these partial transpose. You see, so we're not going very far. It is precisely coming from the singular values of the partial transpose. So we can define further T-dual operators to be unitaries for which the partial transpose is also unitary. And then we can define a two-unitary or a perfect tensor to be an operator such that it's unitary, its realignment is unitary, and its partial transpose is unitary. In that case, all of these things are equal to E of S. E of US is E of S, and you see that this entangling power is 1. So in fact, it's equal to 1 if and only if this unitary U is 2 unitary. So in fact, these are related. You can construct absolutely maximally entangled states based on this construction. In fact, that's how this absolutely maximally entangled states of 6 parties was recently done, by finding an unitary operator U in 36 dimensions such that this condition is valid. And that's easy to see because we have this mapping between states and operators. So we can take AB, and this is an operator acting on this, unitary operator acting on this. Can have ancillas A prime, B prime that are maximally entangled. Then the quantities that I've been talking about are the entanglement between A prime and BB prime that will be maximized if this operator U is dual unitary. If this U is unitary, it maximizes the entanglement between AB and A prime, B prime. If it is dual unitary, it maximizes also the entanglement between A prime and BB prime. If it is T-dual, it maximizes the entanglement between A prime, B, and AB. And if it is two unitary, it maximizes all 3 partitions, and therefore it is an absolutely maximally entangled state of 4 parties. Now, what are the implications for the dual unitary many-body circuits? So we'll go back to many-body circuits and ask what are the implications there. The autocorrelation functions, autocorrelations, remember, are given by this channel where the realignment appears here. Now, if the operator U is dual unitary, then the realignment is identity, and therefore this becomes a completely depolarizing channel. And the autocorrelations immediately vanish for t greater than 0 in dual unitary circuits. So I'm now going to be interested only in circuits made of these dual unitary or operator entanglement maximizing operators. So in that case, there is no autocorrelation, it vanishes. In fact, it was shown by Bertini, Koch, and Prosen in 2019 that the only surviving correlation is on the light cone. The interior of the light cone also this correlation vanishes, and it is governed by the singular values of the partial transpose. Well, they framed it differently, but that's what it's equivalent to. And therefore, the mixing properties of the circuit may be connected to this operator entanglement or the entangling power of this. So, I mean, there's a question mark. Can this be true? There is a caution that this channel M plus U is not a local unitary invariant. Okay, in fact, you can see that this is the connection between the channel of an operator U, which is locally connected. So this is not a unitary transformation, and therefore the spectrum of this M plus is different from the spectrum of this M plus. Nevertheless, actually, there are some connections indeed. And so one of the first things is the norm. The norm of these channels is a local unitary invariant that can be seen. And that is related, in fact, very interestingly, to the entangling power. So you see, there is some connection of these autocorrelation functions to these channels and the connection of these channels properties to the entangling power of these things. So this is what I was showing at the Google Sycamore thing, whether the operator entangling power plays a role in determining the complexity that can be generated from these circuits. But the powers of this channel are very important, and the norms of the powers are not local unitary invariant. But you can do some local unitary averaging now. Now it's not. Now we are envisioning the single particle operators to be random, but they are same everywhere. But you're doing an average over a random ensemble of them. And if you do a Haar average of that, you can relate that to the entangling power. Exactly for this power of 2. For an arbitrary power, we showed that this is an approximation. But it's still interesting that this needs more work, but we have found this to be true. We have given some analytical and numerical arguments. And therefore, the punchline is that the average largest non-trivial eigenvalue of the channel, which determines the mixing rate of the circuits, is in fact a simple function of the entangling power of this building block of this U. So you see, what played an important role in this is the fact that these are dual unitary operators, which are building up the circuit. So this was crucial, and the simplicity of this result is flowing from that, and this lambda 1 is the largest eigenvalue, which is determining then how fast the correlations will decay. Because this is the largest, it will be the slowest decay rate. So if it is much less than 1, it is going to be decaying very fast. So if this operator entanglement is exactly equal to 1, then this is equal to 0, and that is a case of what we call Bernoulli circuit, in which case the operators are not only maximally entangled, but they are also maximally entangling, and therefore they are perfect tensors, and they result in much more interesting circuits, which are, I think, being studied in more detail. Okay, so maybe I will, how much time do I have? Maybe 10?
It is actually 40 minutes talk, so
5 only,
yeah.
I guess.
You can take more 3-4 minutes. Yeah.
3-4 minutes, yeah. So I think I'll skip this part here, where where I'm actually looking at all unitary operators and looking at their entangling power versus what is called gate typicality bias, which is essentially like an EUS picture. So in this, if you see, these are dual unitary operators come in this line here. The T dual, which I talked about, where the partial transpose is unitary, come here. The locals are connected here. This is for qubits. And C0 gates are here. And you don't see anything where EP is 1. And this indicates that there are no 2 unitaries for qubits. And powers of swap, partial powers, that is fractional powers of swap, connect the local and the swap. Okay, so these are borders. And this is for qubits and above. you see that there is a 2 unitary point there where the entangling power is maximum. Okay, so we can look at several many-body problems which have been studied in the literature and understand them from this perspective of what is the fundamental building block and what is the kind of unitary operators which are building it. From localized models to highly mixing models, which Arvinda talked about as Bernoulli circuits. Okay, so just in the last few minutes, then I come to the main topic of constructing these dual unitary operators. Sorry about that. So they are based on block diagonal and swap combinations. Okay, then the permutation. This was talked about by Karol Szyszkowski when he was talking about AME 4.6, how to use orthogonal Latin squares to construct maximally entangled states, which are then equivalent to 2 unitary operators. Then I talked about the Fourier transform as a dual unitary operator. There are generalizations of this, and they are related, interestingly, to things called cat maps, which are studied in dynamical systems. And then there are complex Hadamard matrices based constructions, and then nonlinear maps based on things which we did. Yeah, just to give you an idea of the nonlinear map itself, what we do is the following algorithm. We take a unitary operator U, arbitrary unitary operator U, and we want to make a dual unitary out of it. So what we do is we realign it. It will not be unitary anymore, but we find the nearest unitary via polar decomposition. And then we iterate this map. Let's call this MR. We iterate this many times, and then we ask whether the resulting thing is a unitary operator. So is it close to an unitary operator? In fact, it turns out that that is the case, and that these dual unitary operators are period 2 fixed points of this map. And here is the entangling. This is operator entanglement for random operators of qubits. Okay, so the average is 8 by 9. And you can see that it's spread all over the place. If you apply the algorithm, you will see that its operator entanglement is tending towards maximum. And this is after 100 applications of this, almost all of them maximize this. Okay, so we are able to produce numerically very close ensembles, not just 1 or 2, but ensembles of dual unitary operators using this method. We can also tweak it to produce 2 unitaries, okay, which can produce these things. This is for qubits, for example, before the map, and this is the spread of operator entangling power, and after the map, the spread of entangling power. Entangling power is not equal to 1 for qubits, therefore it's not going there. But for qtrits, you see, there's a fantastic thing happens where this generic operator in entangling power just goes into maximum. So it's very easy to create these kind of 2 unitaries for qtrits. There are some which are sticking out. It's very interesting. We don't know why that is the case, but almost all operators become 2 unitary under this map. And for q quads, q equals 4, you can still produce 2 unitaries. There's some very interesting fractal structure which we don't understand. But for q is 5 and 6, it is gets more difficult. Okay, so there are many questions, but for lack of time, I'm not going to discuss that. How fast is the convergence and so on. In the case of qubits, we can do analytics on our map and show that the convergence to these dual unitaries which are there here is in fact assured. And this convergence can be at an instant rate, or it can be polynomially slow, so algebraic approach to the swap gate, or it can be exponential. So all of these things are possible, and it's generically exponential. So that's a good news for the algorithm as to that. So there are other ways of constructing it. Dual unitary operators. It's actually easier to construct T-duals where the partial transpose is unitary, multiplied by swap. So this is a trick which we use. So here is, for example, the simplest diagonal T-unitary or dual unitary, T-dual unitary. It's simply a diagonal. So multiply that by swap, it in fact is a self-dual unitary. So, but all of these are restricted in the sense that the entangling power is not very large in these. But we can have block diagonal constructions, and that also has these things. But these kind of block diagonal constructions are limited in the sense of their entangling power is never going to be 1. In fact, we can prove analytically that there can never be 2 unitaries. So for 2 unitaries, we have some cat-map constructions, which are also Hadamard matrices, especially in odd dimensions. Okay, so I will summarize here. Dual unitary operators have maximum operator entanglement, and they're useful as building blocks of many-body circuits. Dual and 2 unitary, or in general multi-unitary matrices, are not fully parametrized for local dimension greater than 2. We pointed out some approaches to finding and characterizing dual unitary operators. And these channel and mixing rates based on this shows the role of entangling power of interactions in many-body systems. So I thank you for your attention.
Thank Arul for his beautiful talk. Now it's open for a few questions and comment.
Thank you.
There are some questions in the chat box.
Oh, can you? Can you read them, or?
Yeah.
I'm not able to see.
Okay. Nearest, this is a question by Ajit Iqbal Singh. Nearest in which norm?
Any unitary invariant norm.
So, madam, if you can unmute and you can ask directly there also.
Any unitary invariant, such as the H's norm, or you know.
And there is one more
thing. Professor Singh, you can speak also.
Yes.
Yes, you know, I already pointed out relation with Musto and Vicari and Reuter's work at Arvinda's talk. That is one point. But
right.
What I wanted to ask here was, you know, they are commuting subsystems, maximal commuting subsystems. That was one question that I'm going backwards. Okay. Another thing that I wanted to ask was, you know, if you take Kaifan norms, because you said nearest point in any norm. Now, nearest point may not exist. There may be many points with the same distance. So, which one will you consider? And do you consider different Kaifan norms also?
Yeah. So, thank you for the questions. There. Yeah. Now I can see the chat box. As far as the remark about the mathematical work of Vicari and Musto and others are concerned, I think there are no concrete. It's not very clear what are the concrete examples of dual unitary. For example, the swap itself, which is quite easy to see that that's a dual unitary operator, is one of them. But I think that it would be nice to have general parameterizations and also to study it from the point of view of entangling power. This is something which I want to say that the mathematicians have not classified these dual unitaries, differentiated them as far as I can see. Okay, not a mathematician myself, from one to the other. So,
Shruti Murli.
Sorry?
Shruti Murli's PhD thesis under Sundar and Kodyalam.
Yeah, I'm aware of that. So one of the things, for example, I think a very nice result which they showed for Q-trits is that in terms of permutations, if you restrict yourself to permutations, there are 18 different classes. Okay, and local unitary invariant classes, I think, if I'm not mistaken. There's something like that. But you see, the interesting thing is that these 18 different classes are actually differentiated by entangling power. So this is what is, I think, something which is something to be said there. As to your question about there may be more than one which is equidistant, absolutely. So this depends upon the map, the polar decomposition being unique or not. So in the case where the polar decomposition is not unique, you will have multiple choices to go to. In our case, we found that it doesn't matter what you choose. You can choose any of them, and then you can, if you want to go to a dual unitary, you can do that, or even a two unitary. But this is a point which I think has to be looked at carefully in looking at these maps analytically, that sometimes they may not be maps at all. You will be having a thing from 1 to infinity because of this polar decomposition is not unique. But wherever the polar decomposition is unique, then this is a one-to-one map. As to,
Thank you. A very concrete. Thank you.
Sorry?
We cannot take further question because we are running little late. So let us thank the speaker once again, and we move to our next speaker. Our next speaker is Nirman Ganguly. Nirman Ganguly from BITS Pilani, Hyderabad. His PhD was from SN Bose National Center for Basic Sciences, Kolkata. His research interests includes in quantum information theory, especially the domain areas being deletion of quantum entanglement, entanglement witness, positive maps, and quantum entropy. Currently, he is working as an assistant professor in Birla Institute of Technology and Science, Telangana. His title of the talk, A Unital Operation and Their Relation to Quantum Conditional Entropy. So over to Nirman. Hello, Nirman, you start. Hello, Nirman, do you hear me?
Hello, can you hear me, sir?
Yeah, we can. Yeah, we can also see your slide.
Just a minute. Okay, thank you, Professor Guru Prasad Kaur, for this introduction. And also I am thankful to the organizers for calling me over here for this particular talk. So I'll be talking on a recent work of ours, and that is about A-unital operations and their relation to quantum conditional entropy. So this has been a work which we have done with the collaboration of Ms. Mahati Vempati from IIIT Hyderabad, Soumya Shah from IIT Guwahati, and Indranil Chakraborty from IIIT Hyderabad. So this has been published in the journal Quantum, and also in the archive reference also is given. So to talk about this particular thing, what we have seen is, like in a previous talk, my collaborator, Professor Indranil Chakraborty, has already told about that why it is important to detect states which has a negative conditional entropy. And he talked about how to find out witness operators which can detect quantum entanglement, and not just only quantum entanglement, but entangled states with negative conditional entropy. And he also talked about the states which preserve their conditional von Neumann entropy being non-negative even under global unitary operations, which we call as Icqif class. That is, states which are preserving their non-negativity of conditional entropy even under global unitary operations. So to carry on this forward, what we are trying to see right now is that is, if we consider the states which has a non-negative conditional entropy as the states which are free in the resource theory that we are trying to propose, that is the resource theory of states having negative conditional entropy. So those states which are having a non-negative conditional entropy can be considered to be free states. And then the next question is, what comes is, like, what are the free operations that one can do? So our work is actually a path in that particular direction. And to start with, I'll give you some general outline as to what I'll be talking about. And then I will go to that, what are the free operators or the free channels that we are defining over here. And we will show that those are indeed completely free for the states that we are talking about. So as we all know that negative conditional entropy states are key ingredients for information theoretic tasks such as superdense coding and state merging. So now, how does one detect if a channel is useful in preparing negative conditional entropy states? A-unital channels, which we will be introducing, and in fact introduced in our particular paper, are the largest class of conditional entropy non-decreasing channels. A-unital channels, as we will show, that these are precisely the completely free operations for the class of states with non-negative conditional entropy. We will also see some relation with the other established channels like the separable channels and the entanglement breaking channels. And we will see that it is not about strict inclusion. Rather, we can have a-unital channels which are not separable, and again, separable channels which are not a-unital. So we have a very varied kind of a relationship with other channels that we'll be talking about. And we'll also talk about the last one, that is the class that I was talking about, states preserving non-negativity of conditional von Neumann entropy even under global unitary operations, which we denote by ACVNN. So we will see that what are the completely free operations for such class of states. So just to figure out some of the notations that I'll be using in my work. So the set of bounded linear operators over Hilbert space is denoted by this BAB. The set of bounded linear operators that are Hermitian, positive, semi-definite, and have unit trace, that is the set of density matrices over HA, is denoted by DA. And a channel is a linear map from DA to DB that is completely positive and trace preserving. So this is kind of a an axiomatization of channel, a mathematical axiomatization of channel when we talk about the quantum evolution. That is the most general way to see it as it is a completely positive and trace preserving map. So now talking about entanglement. Entanglement is something is just for a pedagogical reason I'm talking about this one right now. So we all know that entangled state rho AB is called separable if it can be written as a convex combination of pure product states. That is the thing over here. And separable states are the free states in the resource theory of entanglement, which we denote by Fs A by B. So coming down to our topic and the main motivation of our particular work, that is, we know that conditional entropy is defined in this particular way, where S rho is the von Neumann entropy, and the set of states rho AB, which belongs to the density operators on AB, for which S of A by B is greater than or equal to 0, that is the set of states position non-negative conditional entropy is denoted by FC A by B. So these are some of the main notation that I'll be using in my work. Now, coming to some definitions which will be helpful in understanding what we are trying to do. It is that if we go through this remarkable review by Professor Eric Chitambar and Gilad Gaur, where they have defined this, given a very good framework for quantum resource theories in the reviews of modern physics. So what we have is, like, if we have a channel from DAB to DCD is free for FC A by B, please keep in mind that this FC A by B is those states whose conditional von Neumann entropy is non-negative. So if for all rho belonging to this, on this particular set, after application of the channel, it still belongs to that the set FC C by D. So this class of channels will be known as the free channels, and we denote it by this. And if the input and the output spaces are same, then the class is denoted by this one. So this is when the input and the output space is same. So now talking about that, okay, we have understood that what are free operations, then what about completely free operations? So this completely free operations that will be defined, that actually has been defined in this quantum resource theories review, is some kind, it has an analogy with this completely positivity. So what happens over here is that we are enlarging this Hilbert space and the operation remains free over there also. So precisely, mathematically speaking, what we are having over here is that this particular channel is completely free for FCA by B if for all finite dimensional Hilbert spaces HA dashed and HB dashed and rho belonging to this, we have, when we are extending this with this identity map, it still belongs to, after application of the channel, it still belongs to FC A dash C B dash D. And this class of all such channels, we are calling it to be completely free, and we are denoting it this by OC max C. And again, when the input and output spaces are the same, we denote it by this OC max C A by B. So now coming to a very, very interesting thing, and it is like, when are we saying that a particular channel is conditional von Neumann entropy non-decreasing? So its definition is quite intuitive, and precisely mathematically speaking, it is that if for all rho belonging to DAB, we have that it is not decreasing the conditional von Neumann entropy, then we call such channels to be NCVE channels. And those NCVE channels, again, when the two spaces are same, we are denoting it by NCVE A by B. So what we are trying to do over here now, let us understand this, that NCVE are those which are actually conditional entropy non-decreasing. We have the completely free operations. And now what we do over here is we define this A unital operations. So this is how the A unital operations are defined. That is, it is a channel from AB to AB is called A unital if n satisfies this condition. So where for some rho B dash belonging to the density operators on B. And we denote this class of channels as uni A by B. And similarly, we can say that a channel is B unital if this happens on the subsystem B. So, and the set of all B unital channels on DAB is denoted by uni B by A. So this is the channel. So now, see, we have defined, we have shown that what is A unital channels. We have defined that A unital channels. And what is our next target? The next target is to show that this uni A by B, NCVE A by B, that is the channels which are non-decreasing conditional entropy, and the completely free channels OC max C are all equal to each other. And in fact, it is diagrammatically represented by this. So if a channel belongs to uni A by B, it will mean it belongs to OCC max A by B, and it will mean that it belongs to NCVE A by B, and it will mean that it belongs to uni A by B. So this diagram actually shows the equivalence of all these classes, and that is what we will try to prove. Now, I apologize for one thing, that since the proofs are very it's not very brief, they are very elongating proofs. So I'll just give a brief sketch of some of the lemmas that help us to prove this theorem. And taking all the lemmas together will show that these classes are indeed equivalent to each other. So the first lemma that we are saying is that if a channel belongs to uni A by B, it will also belong to NCVE A by B. So how does we show it? For that, we take this particular help of this relation of expressing the conditional entropy in terms of the relative entropy, and using the monotonicity of relative entropy, we can say that basically S of A by B n rho, which is this, will be greater than equal to log D minus this one, and which indeed is equal to S of A by B rho. So basically this expression that we have over here on the left hand side is S of the A by B n rho. So that means that the conditional von Neumann entropy is non-decreasing. So it will mean that n will belong to NCVE A by B. The next lemma is that if x belongs to NCVE A by B, it will also belong to uni A by B. So this is the brief sketch of the proof. So this particular proof tells us that we start with this n belonging to NCVE A by B and assume that n does not belong to uni A by B. So then there exists some state sigma b belonging to dB such that n of IA dA tensor sigma b is not equal to this. And this will imply that S of A by B is equal to log dA, because this is a very important relation for conditional entropy. This is the maximal value. But due to this, it will be less than log dA because it is not taking this particular form. And this will mean that this is a contradiction. Hence, n should belong to uni A by B. Now coming to this one. So if n belongs to uni A by B, and we are doing a tensor extension of this with this identity map, then it will belong to uni A dash A and B dash B. So this is given by this particular proof, and it relies on the fact, this proof actually relies on the fact that it is possible to write down the operators in terms of the density matrices. So this is what has been done over here, that it is application of this channel on this state is giving me this, which means that this particular map belongs to uni A dash A, B dash B. So if you now look at this, that means we have seen that if n belongs to uni A by B, and you are taking a tensor extension of this, then it belongs to the A dash A, B dash B. So if you now look at this particular fact, how does we prove that if n belongs to uni A by B, then n belongs to these completely free operations. And this is done by this thing. That is, NAB belongs to uni A by B. So from lemma 8 we have, so this is my lemma 8, this was lemma 8. So from this lemma, what we have is that this will belong to uni A dash A and B dash B. Now in lemma 6, we had proved that if something belongs to uni A dash A, B dash B, it will be there over here. So on NCVE class. So for all row belonging to FC A dash A, B dash B, we have this thing because it belongs to NCVE A dash A, B dash B. So what does this imply? This implies, according to the definition of completely free channels, that NAB will belong to OC max A by B. And coming to the last lemma, which actually will close this theorem, and it is that this is done by proving the contrapositive statement. And in this contrapositive statement, we have proved, and for the details, you may kindly refer to our particular paper in quantum, that what we have done is that in order to show that if n belongs to OC C max A by B, then n will belong to NCVE A by B. And what we have done is that we have proved this using the contrapositive statement, which is that if NAB does not belong to NCVE A by B, then NAB will not also belong to this one. So if you now take all these lemmas together, we are having this particular equivalence that we were talking about, that these all classes are equal. So now going along. So what we see over here is that we would like to see some of the properties of this A-unital channel. So what are the properties of this A-unital channels? So the properties of this is that the serial and the parallel concatenation of this A-unital operations or A-unital channels are A-unital channel, and this is what is readily seen by this thing. So this is the serial concatenation and this is the parallel concatenation. So serial concatenations and parallel concatenations, if with respect to these two kind of operations, A-unital operations are closed. And it's very easy to see that a convex combination of A-unital channels is an A-unital channel. So now, as I talked about in my outline, I showed you that it is also very it is intriguing to see that on the basis of the established channels that we already have, like for example, the separable channels and the entanglement breaking channels, then what are the relation between them? And in fact, as I told you, that there will be some channels which are A-unital but not separable, and vice versa also. So this is what is doing that is these channels which we have defined, which is this is the preparation channel, this is the partial trace channel, and this is the swap channel. So if you take this particular channel, which is we are calling a swap and the prepare channel, so it will be a unital channel, but it will be non-separable, and it is pictorially represented by this particular diagram. So this is an example of a channel which is A-unital, but it is not separable. Then what are examples of channels that are non-A-unital but separable? And that are replacement channels which trace out a given state and prepare a product state. A very trivial example of a channel that is both A-unital and separable is the identity channel. And of course, if you want to look for a more non-trivial example of a channel, then it is this one. So this channel, which is given by equation 10, where each KIA, that is the cross operators on the A subsystem, are unitary channels. So CAB is separable by definition. However, it can be shown that it is A-unital. So this particular channel will lie at the intersection. Now coming down to this one, an example of an entanglement breaking and this relation between entanglement breaking and A-unital channels. So this is the classical quantum channel from DA to DA. So all classical quantum channels are entanglement breaking according to Professor Wilde in his notes on quantum information theory. But this is not an A-unital channel because of this particular relation. One can easily see with this particular application of the channel. So this actually shows that this A-unital channels that we have defined over here, although there may be some common intersection between the channels, but there are also some channels which are A-unital but not separable, or separable but not A-unital. So it's not like thing that they are strictly included in each other. So that actually shows that it is indeed interesting to look forward and see that what happens when an entangled channel, or rather an entangled state, has a negative conditional entropy, because that is a very unique feature in quantum theory. And this is the relation between a-unital, b-unital, and unital channels. So unital channels, as we know, that these are very important. And why they are important? Because these unital channels that we have are the von Neumann entropy non-decreasing channels. And this unital A by B are the conditional entropy non-decreasing channels. So this is the relationship between a-unital, b-unital, and the unital channels. So see, unital channels, you can see that if you like want to see that this unital channels, what we are doing right now over here is that, you know, that unital channels are mapping identity to identity. But what is happening over here is that if you just look at the subsystem for our a-unital channels, it is mapping that to the identity, the subsystem to the identity. So there might be some relations between this unital and a-unital channels that we are talking about. So coming to this one, so as I told that we'll be also talking about some states which are agven. Agven means, again, I repeat, that it are those channels which are preserving the non-negativity of their conditional entropy even under global unitary operations, and which Indranil has already talked about in his talk on 2-qubit systems. So basically this can be easily extended to 2-qubit systems, and this is how they are defined. That is, even under global unitary operations, their conditional von Neumann entropy remains non-negative. Okay, so this is again a difference between what has happened in entanglement, now what is happening in the states having non-negative conditional entropy. So the important thing over here is that, like over here also, if you define the completely free operations, that is a channel NAB, DAB to DAB is completely free for f a c a by phi if for all finite dimensional Hilbert spaces HA dashed and HAB dashed, where DA dashed is equal to D dashed, this will belong to FAC. That means these channels will be called as the completely free operations for agven. So the class of all such completely free operations mapping DAB to itself is denoted by OAC Cmax A by B. And what is the most important thing right now? As I told about that, unital channels, we know they are very, very important in the study of quantum channels. In fact, this is the thing that we have found out, that a channel N belonging to this OAC Cmax A by B will belong to this if and only if it is unital. That means unital channels are completely free operations for these states which preserve their conditional von Neumann entropy non-negative even under global unitary operations. So that is indeed another interesting characterization of unital mapping, unital channels. So to finish my talk, I would like to just like ponder about some of the open questions that our work actually throws open. And it is intriguing to see that a necessary and sufficient condition for the unitality of a channel is for it to be expressed as an affine combination of unitary quantum channels. This in fact was shown by Mendel and Wolf in this paper in Communications in Mathematical Physics. And why this is important is because if you look at, and if you go back and go to the Birkhoff's theorem, then a doubly stochastic matrix. So doubly stochastic matrix actually represents a classical channel. So a doubly stochastic matrix can be expressed as a mixture of permutations. But when you come to this unitary channels over here, the unital channels over here, this is not happening. It is not a mixture of unitaries, but it happens in the asymptotic limit. So they have showed it that it is an affine combination of unitary quantum channels. So then the question is, what will happen in our case? That is, can we provide a similar decomposition for a-unital channels will be an intriguing problem to look after. It is not only mathematically interesting, but also physically motivating. And this is another thing that we can look about, that state conversion under a-unital channels, because according to the Ullmann's theorem, a state rho can be converted to state sigma under unital channels, if and only if sigma is majorized by rho. And that came in this particular Nielsen's work, and also by Professor Paul Bush, who showed this with the relation with von Neumann entropy. So we would like to also see that how can one define state conversion, or what is the necessary and sufficient condition to see state conversion under a-unital channels. So these are some of the work that you can always think about. So thank you very much for this patient hearing. So we would like to see, and thank you for giving this a patient hearing to this. Thank you very much.
Thank Nirvan for your beautiful talk. And now it's open for a few questions or remarks. Bialan, yes.
Hello. Thank you, Nirmanda, for this nice talk. I would like to ask that in resource theory of purity, the unital operation is also a free operation. And in this case also, unital operations is also free. So is there any connection between these two resource theories? Can we think of like that?
Thank you, Bialan, for this question. But first of all, we need to clarify one thing. Like when we talk about purity, then it is free. But I don't know whether it is completely free or not. So when we talk about unital channels, so unital channels, we have shown that if we take those states which preserves their conditional von Neumann entropy, and preserving means preserving the non-negativity of that. So if you take those states as in the thing, so what happens is that unital channels are completely free operations for them.
Okay.
So it will be indeed interesting to see that how does it carry over to purity.
Okay. Thank you, Nirmanda. Thank you.
So if there is no further question, let us thank the speaker once again for his beautiful talk. And we now it is the turn of Daniel Bargott from Macquarie University, Australia. He will be talking on one bound to rule them all from adiabatic to Zeno. Yes, Daniel.
Thank you so much. Can you hear me okay?
Yeah, we don't see your slide yet.
Yes, I have to share my screen, but you can hear me.
Yeah, we can hear you.
Just 1 second. Let me set this up.
Yeah, we see.
Wonderful. Okay, so thank you very much for accepting my contribution to this conference. It's a pleasure to virtually be here. And as you can see, I've actually changed the title of my talk to A Bound for the Rotating Wave Approximation. So it's a new title. And the reason is that I simply do not have time to give you the broader picture in this, in which this work is framed. So I can only talk about the details in this presentation, but I hope that the presentation will be interesting nonetheless, and maybe raise some appetite to look at the actual paper, which is on the archive here. And so this is some collaborative work with Paolo Facchi in Bari, with Giovanni Gramegna in Trieste, and with Kazuya Yuasa at Waseda. So let's just jump right into it. I think the rotating wave approximation we've all come across. And in fact, I'm only going to talk about the simplest undergraduate version of the rotating wave approximation, as you might have encountered it yourself in your own undergraduates. So the setup is that you have a time-dependent Hamiltonian in terms of Z and X. So Z and X here are just the Pauli spin matrices. And it's time-dependent through some cosine-style driving. And so this is one of the simplest time-dependent Schrödinger equations one can write down, but it is actually surprisingly difficult to solve it exactly. In fact, there was an analytical solution in 2010 only. Until then, people didn't really have a good handle on how to solve this. Anyway, I will not talk about analytical solutions, but I will talk about the approximate solutions that people talk about, which is effectively the rotating wave approximation. So then we have to solve the Schrödinger equation. So this is the time-dependent Schrödinger equation with the appropriate initial condition. Everything here is finite dimensional, two-dimensional, in fact, so we are not going to have any problems with this. And of course, I set h bar equal to 1. And then the typical thing people do in this teaching this is to go into a different frame. So let's do this as well. So we define another unitary, which is just the exponential of z with omega. Notice that I have an omega 0 here, so these might be in general difference. This omega is the omega from the driving frequency. And then we just define another unitary. This is what people sometimes call the rotating frame, which is defined like this. So what I'm going to do now is very, very elementary, very, very basic, but just to remind you of your good old undergraduate time, so to say. So the idea is to find an effective Schrödinger equation for this picture. Of course, we know at time 0, this is the identity. But if we want to take the derivative, then all we need to do is use the product rule. And in fact, everything I'm going to say today is really on the level of the product rule in terms of technicalities. So it's really a very simple result that I want to present. So when you do the product rule, of course, you get 2 terms here. One comes from V and one comes from U. And it's pretty obvious what they have to be. You can simplify this a little bit. You know, there's 2 terms with Z, then people call this usually the detuning, which might be 0 or might be non-zero. At the moment, I leave this completely open. Okay, so this is the simplified version. But then if we want to have a Schrödinger equation in terms of R, then we really need to bring this V dagger to the right side. And of course, we can do that with Z, because Z and Z commute, but we can't do it with X. So we just do it like this, right? We bring it up to here and we introduce a new identity here. V dagger is just equal to the identity. So then things are fine. We just have our R on the right side and we actually have a Schrödinger equation. Now, in the next step here from this line to this line, what did I do? First of all, I have to compute this. This is easy. This is just Pauli X rotating under Pauli Z. So you get some kind of oscillation between X and Y in the X and Y plane. And then you still multiply with the cosine here. So you have to do the double Icqif formula for this expression. And you can immediately see that it's this. Okay, so this is probably something that the teacher at university might have left as a simple exercise. You can express the Schrödinger equation effectively in this rotating frame like this. Now, at this point, there is really no approximation. This is just going into a rotating frame. So everything is equally hard to solving the original Schrödinger equation. And you might have wondered at the time, what's the point anyway? And then probably what your teacher would have told you at the time is that in this rotating frame picture, there are some terms here that oscillate at a frequency 2 times omega. And so they are fastly rotating when omega is large. And therefore, your teacher would have told you that you can ignore them. That's the usual story that people tell when they talk about the rotating wave approximation. Now, if you were an alert student, maybe you would then go back to the teacher and you say, well, actually, I mean, I have a differential equation. What allows me to just neglect these 2 terms here? They're not small, are they? I mean, the norm of them is not small, and not even on average it is small. So how can I just remove them, right? And in particular, you might ask, well, what was the point of going into the rotating frame in the first place? You know, you could argue that this term here, which oscillates at frequency omega, when omega becomes large, is also fastly rotating, right? So why can't I just go in this original picture and then cross out this term? This gives a completely different solution. So this is the question that I also had at the time when I was a student, and I never really got a good answer at the time. Of course, the teacher might say something like, this is not the correct frame, right? So you have to go into the correct rotating frame, but then maybe the next question is, how do you define the correct rotating frame? What is there such a thing? And there are infinitely many different rotating frames in which you could go. So in fact, what I want to convince you of in this talk is that the rotating wave approximation has really nothing to do with the rotating frame at all. You can make the rotating wave approximation in any frame you like. And I also want to convince you that highly oscillatory terms cannot in general be removed. In fact, in general, this will be wrong. Nonetheless, I want to argue that in some sense, this rotating wave approximation is correct. I want to justify it, but in a slightly more quantitative way. So why is it correct? And before I tell you the result, I just want to give a little quote here from a book on averaging theory, which is the mathematical version of doing this. And there's a nice quote here which says that the fact that averaging seems so natural obscures the pitfalls. And this is exactly what I meant earlier, that why can I average this term away to 0, but I cannot average this term to 0? Both look equally naturally, perhaps. So in order to really understand this, you need to have a quantitative result. Okay, so So this is our bound, and it's again a very elementary calculation which I want to guide you through because I think it's a kind of cute calculation, and the bound also has applications in many other areas of quantum mechanics. So everything that I'm going to talk about now is about finite dimensional systems, but I'm not necessarily focusing on the rotating wave approximation in the sense that I just want to look at two Schrödinger equations. So of course, I have to assume that H is well behaved in the sense that the solution exists. For example, you might say it's continuous or something like that. But I have two different Schrödinger equations, and I want to compare the two solutions. How far are they from each other? And if I can then show that for the rotating wave approximation, those solutions are close to each other in the limit of large omega, then I'll be done. And this is essentially what I'm going to do. But before I apply it to the rotating wave approximation, let me derive the general bound. It's very simple. It's again just the product rule. Everything I do is product rule. So this is generic Hamiltonians and finite dimensions. And what we do is we just write down the difference between these two, and we put an I in front. And you see then that in the notation that you usually use for Riemann integrals, you can rewrite it like this. So this is like a boundary term from a Riemann integration. When I put in t here, then the u1 will cancel against the u1, and I get u2. So this is the first term. And when I put in 0 here, then these will both be identity, and I'm left with u1s, and this will be subtracted. So this is u1. This is just a standard trick, of course, to write some difference between terms as an integral, because with integrals we can do estimates. So then by Riemann, this is just the integral over the derivative of these two terms. And this is where the product rule come in. So I need to apply the product rule. I'll get two terms. First, I have to take the derivative of u dagger. Of course, you can get that by taking the Hermitian conjugate of the Schrödinger equation. So you get a minus hj, so in this case, h1. And my u2 gives me another term, so I get a h2 from this part. And that's it, really, right? Now, the quantity that is important for this talk is what you might call an action, because it's an integral over a Hamiltonian. So this action is the integrated differences between the two Hamiltonians. So let's just define this S of t. And then if we define it like this, and we want to recognize it somewhere in here, well, then you see that this middle part here is just the derivative of the action, right? So now we've got an integral over some term, a derivative, and some other term. And so then you do partial integration, which is nothing but a product rule backwards. So I get a boundary term. In fact, one of the boundary terms is 0, because at t equal to 0, this integral is of course 0. I'm only left with a boundary term at time t. This is this. And then I have to shuffle the derivative on the other two terms. Okay, so I have to take the derivative of this and the derivative of this. So the first guy here is u1 derivative, and the second guy is u2 derivative. And then I just play the same thing from above. So I just apply the Schrödinger equation to write this out a little bit more explicitly. You see here in green, I've introduced an I so that it's clear where the factors come from. This cancels, so this is just this term. And then here, well, I've got a u1 dagger and a u2 at the end, and in the middle I just get these two derivatives, right? So one is I get a h1 from here, of course there's an s already, and the other one is I get a h2 from there, and there's an s already. So this is the form that we get. All right, so this is the key equation for this talk. And in fact, now I'm going to take norms on both sides, and I'm going to take the spectral norm. So in this case, of course, the I doesn't really matter. And if I take the spectral norm of such an expression, I can use the fact that the spectral norm of anything times a unitary, and a unitary times anything is equal to the spectral norm of anything. So I can just remove all the unitaries here. This one goes away and this one goes away. So I get an overall factor of s from the first term. And I have an s here as well, which I want to take out of the integral. So I'm going to take the supremum over the whole range between 0 and t. I can certainly do that. And so then I just have a 1 from the first term. And then here I have the norm of the modulus of the Hamiltonian. So I've taken the norm inside the integral and the norm of the second Hamiltonian. And so this is the key equation. This is what in the original title we call the one bound to rule them all. And now we want to apply this to the rotating wave approximation to understand why this bound is useful. But before I do that, I want to point out a little bit of what is the point of this. I mean, so there are many simple bounds that you can get in terms of comparing two unitaries. And the simplest one is just that the difference between the unitaries is equal to the integral over the norm of the difference of the Hamiltonians. But the norm of the difference of the Hamiltonians might be big, even though the norm of the integrated Hamiltonian, so if you integrate first and then take the norm, might be small. And this is because if you have oscillatory terms, then there might be cancellations. But if you take the norm too early, then you can't see this. And this is the reason why we had to do this little partial integration trick here to get something where you might have a chance that this S of t here actually gets small. And in this case, the U1 and U2 are close to each other. That's the idea of this bound. Okay, so you get an average, in other words. So a much more sophisticated and theory of this, by the way, for even nonlinear differential equations is the, what is it called, Krylov-Boguliov-Mitropolsky theory from the 1950s. But that's really a canon to shoot this really simple problem. This is much easier here and much more explicit. So let's apply this finally to the rotating wave approximation. So I just wrote down the bound for your convenience once more because it's a bit lengthy. And now we want to apply this for the rotating wave approximation, where we learned that in the rotating frame, the Hamiltonian is like this. And then what your teacher did is they just crossed out these oscillatory terms here, right? So what I'm doing here is I'm doing it in the rotating frame. I could equally do it in any other frame, but I'll do it here. So now the action is the difference between the two. So there's a lot of cancellation here. And then, of course, there's just a very simple integral here over those cosine terms. And you see that from the integral over the cosine, I get a 1 over omega. So when omega becomes large, this integral goes to 0. So this is this action. And we can actually bound the norm of the action in a really simple way, because these are just Pauli matrices, so you know what their norms are. By the modulus of G. G is the coupling between the coupling that the spin fields in the X field or in the original frame, divided by 2 omega. So this is just this guy, and this goes to 0. And then I have to estimate also the norm of H1 and of H2. These are just, again, following from simple properties of the Pauli matrices. And I can take a bigger bound and make this term here a little bit bigger to get one uniform bound that is simple to understand. So we just have that the difference between the two unitaries is in spectral norm is smaller or equal to the coupling divided by the frequency times the term here that depends on the detuning. That's important. It depends also on the coupling. That's less important. The coupling is already here. And it depends also on time. So as time gets bigger, actually the approximation, at least the bound for the approximation, gets worse. And I want to argue that this is really the way the rotating wave approximation should be presented, because once you have a bound, there's no need to go into rotating frames or to give any sort of hand-wavy or perturbative arguments as it's usually done. And in particular, you see that if we take omega going to infinity, well, we have to be a bit careful. We have to keep G and, of course, delta, the detuning, constant. Then if we do this, then the error goes to 0. And so you can actually see, and you can see quantitatively how good the rotating wave approximation is. Okay, so finally, I just want to make some remarks on this. So the first remark I already gave, but I just want to emphasize and clarify a little bit more. So the bound that we have grows linearly in time. This is pretty bad. Actually, the actual error, if you compare the dynamics of the rotating wave approximation and the non-rotating wave approximation, also grows in time. These times are usually much longer than linearly, but they are there. So in the sense, if you take the maximum distance that is achieved over arbitrary times for some finite value of omega, no matter how large, you will actually find that it's always maximal. So the rotating wave approximation is only really valid in a certain time frame. And because I just essentially use partial integration, I think this is a simple enough derivation to actually include in undergraduate lectures. And I wish I would have been taught this way. And then what I mentioned in the beginning is that this really could have been applied in any other frame. So there's really no reason I did it in this frame. For example, if you do it in the original frame, you will see that instead of crossing out the cosine term, which would have been really wrong, you actually add a sine term, right? So okay, you divide also by 2. This comes from the averaging, but this is even less counterintuitive if you follow this idea that you can cross out highly oscillatory terms. Here we actually add a highly oscillatory term, which seems completely counterintuitive according to the story that people usually tell. And so then finally, the key bound that I introduced is this one here. And this is valid for any finite dimensional system. And as such has many other applications. And so that I don't have time to talk about those applications, but I just want to mention them in name. So you can actually use this to get bounds on Trotter theorems. You can rederive the standard adiabatic theorem in quantum mechanics. You can apply it to dynamical decoupling and prove bounds for dynamical decoupling. And you can use it for proving the quantum Zeno limit. So it's really a quite useful little tool. And with that, I'd like to thank you for your attention and refer you to the paper for more details. Thanks.
Thank Daniel for your beautiful presentation. And now we can take a few questions if there is any remark. Any question?
Can I ask a question?
Sure. Question?
Am I audible?
Yes.
Shivashish,
I can.
Yeah, you speak. Yeah.
So it's a really nice talk. You know, in this this Markovian open system dynamics, like this Lindblad formulation. So
yes.
we, in the microscopic derivation, we take the rotating wave approximation, right?
Yes.
Now there, generally, when we take a model Hamiltonian for interaction, so these people call as minimal interaction, like where you have these, dipole type interaction. So like, if you have a system operator, which is, let's say, S, so S plus, and then the field operator A minus plus S plus, S minus, and then A plus, something like that, right?
Yeah.
So, so my question is, in this formulation, so can one guarantee that in such a minimal approximation, minimal form of interaction Hamiltonian will be one of the solutions for rotating wave approximation?
Yeah, it's an excellent question. And in fact, there are 3 different rotating wave approximations in the literature. One is for the simple time-dependent qubit example and generalizations of that. Mm-hmm. Then one is for infinite dimensional Hamiltonians, such as the quantum Rabi problem, which is essentially a case of what you've explained. So where you go from quantum Rabi to Jaynes-Cummings.
Yeah.
And the third one is actually also what people sometimes call the post-trace rotating wave approximation, where you do the rotating wave approximation on the level of the Redfield equation after you've taken the trace to get the GKS equation. And so these are mathematically quite different from each other. The third one is relatively simple because in finite dimensions, almost everything is simple. The one for the Jaynes-Cummings model that you alert to with this minimal representation of the Hamiltonian, I would love to prove, and I'm actually working on that. But it turns out to be really hard to prove because it's an unbounded operator, and the equations that we have here, you can generalize for bounded infinite dimensional systems, but for unbounded operators, it's pretty hard. I have some ideas on how to do that, but it's really tough. I should also say that I've skimmed around 75 textbooks in quantum mechanics and quantum optics. This is just a curious point, and I only found 2 rigorous comments on the rotating wave approximation. And one is in the book by Domenico D'Alessandro on quantum control, and the other one is actually by the book on quantum optics by Argewal, who actually uses this Krylov-Bogoliubov-Mitovsky theory to justify the rotating wave approximation.
I see. Okay. Thanks.
Thank you.
Okay, if there is no further question, there is question?
Yeah.
Yeah.
Yeah, Guruda. Yeah.
Yeah.
So very,
Yeah.
very interesting talk. I want to know if there is, at a certain time your inequality becomes absurd. So is there some significance to that time, or rather it becomes trivial?
Yeah. So my inequality is very far from tight. In fact, when you plot the numerics, it's a good question. When you plot the numerics, you will see that there is some quasi-oscillatory dynamics going on, and the rotating wave approximation solution and the true solution will gradually get out of phase. In first order, this is usually called the Bloch-Siegert shift, and then my bound shoots off to sky already for relatively short terms. It's really hard to capture this. At which time really the evolution distinguishes itself from the true evolution? It's a great question.
Thanks.
Okay, we are not going to take any further questions because we are running a little late. So thanks, the speaker, once again.
Thank you.
And yeah, and we are moving to our next speaker, Professor Monirul Ali. He's well known to us because he did his PhD from S.N. Bose National Center for Basic Science under Archon Mojumdar. He has been abroad for a long time and recently joined to Chennai Institute of Technology. So he is going to talk on dynamical crossover from Markovian to non-Markovian dynamics in the strong coupling regime. So Monirul, over to Monirul. Yeah.
Okay. Thank you so much, Guruda. Yeah, for this nice introduction. And I should also thank the organizers, Devashis, Archunda, Somsubroda, Ramij, Indrani, and others for giving me this opportunity to present a talk here in this conference. Now, since the time is very short and we are 5 to 6 minutes late from the schedule, I request you to ask any question at the end of the talk. So I'm trying to share my screen. So is it visible?
Yes, it is. Yeah.
Okay.
Please
Okay.
start.
So I will mainly talk about the non-Markovian open quantum systems, system dynamics. Yes, for live good streaming. No, I will mainly talk about non-Markovian open quantum system dynamics and present some of our recent work in this area of research. Sorry. Yeah. So the page is not moving. So let me see. Okay.
Monirul, please scroll your mouse. It will move the screen.
Oh,
scroll
okay.
your mouse. Yes.
Oh, okay. Thanks very much. So here I give a small introduction. Open quantum system problems are basically quantum many-body problems where we have quantum systems that interact to their environment, and we know that realistic quantum devices usually interact to their surroundings, and we want to see how does this interaction influence the open quantum system, causing dissipation, decoherence, etc. And the theory of open quantum systems actually deal with various other areas of quantum science and technology. And quantum computation and quantum information processing, of course, provide a major boost to this field. Here, I show some examples of open quantum systems, say, for example, atomic or spin systems, trapped ions, cavity photons, cavity QED systems that interact to their surrounding environment, circuit QED systems where the atom-photon interactions are realized with superconducting electrical circuits and resonators consist of Josephson junction devices, solid-state qubits realized by quantum dots, and few more examples over here. There are hybrid quantum systems, for example, electro-optomechanical systems, through which one can transmit and process quantum information and transfer a quantum state from one type of physical system to a completely different type of physical system. There are different, these are actually different physical systems, but they can be coupled or engineered. I should also mention about nanoelectronic devices, where we study quantum transport of electrons and also investigate thermoelectricity through quantum dots or molecules interacting with electronic reservoirs or leads. For open quantum system, the total density matrix of the system plus environment evolves unitarily under the total Hamiltonian. Then we take partial trace over the environment to obtain the system dynamics. As a final outcome, we obtain a non-unitary time evolution for the system that can be expressed in terms of quantum master equation, or we can express it in terms of Krauss operator, the way written over here. But we should keep in mind that there is always some physical process undergoing behind each of these dynamical maps or quantum channels. To model the physical process, we need to have detailed knowledge about the system, environment, and their coupling. In most of the cases, it is very difficult to solve these problems exactly, and we use perturbative method, assuming that the system is weakly coupled to the environment. There is no memory. We also consider Markov approximation, where we assume that the environment or path correlation time is very short, resulting to a path correlation function that is delta correlated in time, the way I have written here, but I don't know why this is popping up here, this bottom part. Okay, so, and when we do a perturbative calculation, we should check at any given instant of time, the density matrix should satisfy the following properties. That is, trace rho should be 1, the density matrix should be Hermitian and non-negative. Now, having said that, there are experimental situations where the memoryless Markov approximations are not adequate or not valid, specifically for non-Markovian open quantum systems, where a wide range of problems are still open and unexplored. So the non-Markovian dynamics in open quantum systems are typically significant at low temperature. For example, finite size for finite size environment, also for strong system environment coupling, and for structured reservoir, where the spectral density of the environment can be tuned or engineered. Then the short time non-Markovian dynamics is very important for the ultra fast quantum devices, where we observe interesting revival dynamics of quantum properties in very short time regime. In this case, quantum resources decay, but decay and completely disappear due to these decay dynamics, and then it reappear again at a later time. That is, some quantum features can be revived. So this is why non-Markovianity is shown to be useful as a resource in the new quantum technology. And several measures have been proposed which try to define the border between Markovian and non-Markovian quantum evolution in open system dynamics. But there is no universally accepted measure of non-Markovianity. People have tried to quantify non-Markovianity using, for example, non-divisibility of dynamical map, backflow of information, non-monotonous decay of entanglement of the system with some ancilla, etc. And we have also proposed a measure of non-Markovianity using two-time correlation functions. The two-time correlation functions actually provide useful information about the system environment backaction processes, revealing non-Markovian memory effects because two-time correlation functions correlates a past event with its future. So here we plot our non-Markovianity measure for different spectral density with varying coupling strengths. In another work, we have shown significant results about decoherence-free subspace and disentanglement dynamics for 2-qubit systems interacting with a common non-Markovian squeezed reservoir. We found interesting differences between the non-Markovian entanglement dynamics and its Markovian counterpart. We also see here the Bath correlation functions playing important role in terms of the time-dependent coefficient, this time-dependent coefficient in the master equation. So actually, we found that the Bath correlation functions in general play a crucial role in the non-Markovian dynamics of open quantum system. And for the same system reservoir model, actually we have shown a revival dynamics of quantum non-locality for 2-qubit system induced by the memory of thermal squeezed environment. Along this line, we studied the exact decoherence dynamics of a superconducting resonator coupled to an electromagnetic reservoir characterized by 1/f noise at finite temperature. We showed a clear signal of non-Markovian dissipation and fluctuation dynamics induced purely by this 1/f noise. The exact decoherence dynamics was shown in terms of the Wigner distribution function. This is another work on non-Markovian open quantum system where we examined the time evolution of the distribution and shareability of quantum coherence of a tripartite system when the qubits interact to their local dissipative environments. For 3-qubit systems, total quantum coherence is usually distributed among various contributions. For example, local coherence, global coherence is again distributed in terms of bipartite global coherence and tripartite global coherence. And we identify transient revival dynamics of coherence in the non-Markovian regime for all these contributions of the coherence. Here also we see that the Bath correlation function is a crucial quantity which governs the dynamics. So this is another important work we have published recently in collaboration with an experimental group, Fragility of Quantum Correlations and Coherence in a Multipartite Photonic System. Earlier, we have investigated the non-classicality of a non-Markovian open quantum system using Leggett-Garg inequalities, which basically test the correlations of measurements on a single system measured at different times. We probe quantum signature of a two-level quantum system or qubit spontaneously decaying under a non-Markovian dissipative environments through the exact dynamics of two-time correlation functions. We have examined that for a wide range of system environment parameters beyond the Born-Markov regime. We have done similar investigation for a two-level system under decoherence in a non-Markovian dephasing environment also, where we discussed the non-Markovian dynamics of the LG violation at 0 temperature and at finite temperature for this model. Using the same formalism of open system dynamics, recently we have developed a non-equilibrium theory of quantum thermodynamics for single particle quantum systems in contact with a heat bath. We have discussed the real-time thermodynamics of open system in non-equilibrium. We have also discussed a dynamical phase transition in an interesting physical situation. And in this work, we have studied in detail the dynamics of coherence for single mode Gaussian states of a continuous variable quantum system. Continuous variable quantum systems provide an extremely powerful resource to quantum information processing. And a Gaussian state is completely characterized by these first and second moments of these quadrature field operators. The operator I have written here as xi1 and xi2. For multi-mode, there will be more of this kind. But first, we are considering here for single mode, and actually, two mode case we are considering now. Now, for our work, we are interested in the dynamics of coherence for this system. For our work, we use the relative entropy measure to estimate the coherence of a single mode Gaussian state. As we know that relative entropy of coherence is defined in this way, and usually we have to do this minimization, but here we have used one result from this PRA paper that says for Gaussian states, actually the closest incoherent state is a diagonal state of this form. So this measure can be used to compute the coherence of Gaussian states only. For non-Gaussian states, we don't know how to calculate. So this nu is the square root of determinant of this V. V is the covariance matrix, and this mu bar is the average particle number associated to that particular Gaussian state. So for that we first calculate this covariance matrix. So the system when the system is interacting with the environment, and because we need to calculate these average values of this operator, so we work in the operator time evolution, that is Heisenberg formulation. So we know how to do that, the time evolution of the operators for the system and the bath. From there, it is straightforward to obtain the quantum Langevin equation in terms of the system operator. And the solution can be expressed in this way in terms of some Green's function U. And when we calculate some other average values of these operators, we also have terms like f dagger f. So that is another Green's function, actually, this V. So these two Green's functions are very important in the dynamics of this open system. And they satisfy basically this integral differential equation, and these two Green's function are analogous or identified as the non-equilibrium Green's function of the many-body quantum theory. So once we have that, we can calculate all these average values of these time evolved operators to obtain the time evolution of the covariance matrix elements. And this is the result. They look they can be written in this nice form. And here again, I want to comment that these Bath correlation functions, that G and G tilde, actually play a very important role in the dynamics, because here also we can see that G and G tilde are there in the equation of the Green's function. So once we have that, we just put it in the formula. Here the nu is a square root of determinant of the covariance matrix, and from here we can have the time dependent coherence. We have analyzed this problem for a wide range of system environment parameters. I mean, we have considered several Gaussian states, like coherent states. For here, I have shown here for the time dynamics of the coherence for weak coupling and strong coupling. So in the weak coupling, as usual, we see these three curves are actually for different values of this alpha in the coherent state. So in the first column, this result is for weak coupling. The second column is for strong coupling. So in this strong coupling, we can see that that the coherence actually shows some oscillatory behavior here. And the right hand side, this one is for super ohmic spectrum. where in the weak coupling, we see a very slow decay, but in the strong coupling, the coherence actually after a very short time, it saturates to a value. It is like coherence is frozen there. So we have also considered another type of Gaussian state like squeezed vacuum state. And here also we see a quite similar behavior for weak coupling and strong coupling. And here also in the strong coupling case, in the superomic case, the coherence is frozen at some value in the long time in the strong coupling. Okay, so we have also considered another type of Gaussian state, that is displaced squeeze state. And we have here the plot is actually for the time. One x-axis is time, y-axis is actually the coupling strength, and the first row is for low temperature, and the second row is for high temperature. And in the first row, we have considered 4 different set of parameters for the initial state of the system, that is displaced squeeze state, that different values of alpha and r. So in some cases, we see that a large amount of revival of coherence occur when we go from weak coupling to strong coupling. And yeah, so yeah, for superomic case also, sometimes we see that the coherence actually is frozen there, it does not decay. And we also considered a more general Gaussian state, displaced squeezed thermal state. And we have analyzed it for weak coupling and strong coupling. We have considered actually a wide range of parameters for the environment as well as for the system state parameters. And we have also analyzed the steady state coherence for this. We can have some steady state coherence because in the strong coupling, of course, in the weak coupling, it will ultimately decay. But in strong coupling case, we have analyzed the steady state coherence. Here it is for ohmic spectrum. So we basically want to see which are the values of alpha and r for which actually we can get a large steady value for the coherence. And this is for super ohmic spectrum. And basically what happens is we plotted here this derivative of the coherence with respect to eta. Eta means that the coupling strength. So we see a crossover of, where the coherence derivative of the coherence goes from a negative value to a positive value. So that happens at a particular coupling strength. So this is a kind of a dynamical crossover, and this first column is for strong. This first, let me see. Now, first row is for low temperature. The second row is for high temperature. Okay, yeah. A similar dynamical crossover we observed earlier while investigating the non-equilibrium transient dynamics of photon statistics for an optical field coupled to a general non-Markovian environment. And we actually investigated the second order coherence function G2 correlation, where we saw that from weak coupling to strong coupling, when we go that G2 shows this oscillatory behavior, and it persists. It survives even in the steady state. Actually, the first column is for weak coupling, the second column is for the strong coupling regime.
Monirul, now you may conclude.
Okay, so thank you so much, Gurudev, and all of you.
Okay, thank you, Monirul, for your beautiful talk. And we are running late, so we can take at most one question. Yeah. Any question?
Can I ask a question?
Yeah, Shivashish.
Okay.
So, yes, Shivashish there.
So, when you consider these coherence of Gaussian states, for example.
Yes.
Right. So, now coherence, having non-zero coherence means some sort of non-classicality in the state, right?
Yes, yes.
Now, coherent states, particularly, which are also Gaussian states, in the quantum optical scenario, they, we know that their photon number statistics is classical, right? They have the Poissonian distribution for photon number statistics. So, when you get to see non-zero coherence in coherent states of quantum optical system, what does it mean physically?
In terms of, if we consider it in terms of Wigner distribution, yeah, you are right. I mean, it shows a Gaussian this thing, and the coherent for the coherent state now. But the coherent state is a superposition of, if you write it in terms of the Fock basis, for example. So it is a superposition state of all these Fock bases, right? So some coherence is there. It is not a mixture of all this.
Okay, this is a this is anyway. So this may lead to a long.
Okay, maybe I can.
I need to discuss. So I have a small another question. So what is your motivation behind studying this coherence in this in this paper that you are talking about?
Yes, purely from the resource theory point of view, that how much quantum quantum resource is there, even if the system is interacting with a finite temperature bath.
Okay.
Yeah, Shivashish,
okay.
we are running late, so if there is any discussion, you can do it in other way. So thanks, Monirul, for your beautiful talk, and we turn to our next speaker.
Okay. Thank you so much.
Alexander Hun, again from Macquarie University, Australia. He will be talking on unification of random dynamical coupling and the quantum Zeno effect. Okay. Alexander Han.
To stop share this. Okay.
Yes, thanks a lot for the introduction. So I share my screen. Can you see that?
Yeah, we see.
Perfect, amazing. So yeah, thanks a lot for giving me the opportunity to talk about this work. I'm Alexander Hahn. I'm in the group of Daniel Burgert, who was presenting earlier. And I want to present you some work that we did together with Kazuya Yuasa from Waseda University in Tokyo. And most of this work was conducted when I was staying at Leibniz University in Hanover. So that's why you see both of the logos here. And I want to talk about unification of random dynamical decoupling and the quantum Zeno effect, which are two concepts in the area of quantum control. And we, our goal in this paper was to unify these two concepts. And to give you some brief agenda, what I want to talk about today is, first, of course, I want to give you some motivation, and I want to introduce you the physical setting that we're operating in. Then I want to introduce you to dynamical decoupling in particular, and then shift to how is the relation to the quantum Zeno effect. And in the end, I'll give you some error bounds on how well dynamical decoupling performs, which purely depend on the convergence speed of the quantum Zeno limit. So that's kind of the unification that I was talking about earlier. All right, so let's get straight into it. So why is dynamical decoupling even an interesting topic? So usually you have a quantum system, and for instance, think about a qubit system where you want to store some data on, so some quantum memory system. But that's not the whole story, right? So the quantum system is also coupled to some bath or to some environment, which could be some surrounding spins, for instance. And this coupling will actually lead to some loss of information from the system to the environment. And this means that we will actually lose the data that we want to store. So that is not good, as you can imagine, right? So here dynamical decoupling comes in. And the goal of dynamical decoupling is to protect this open quantum system from the noise that is induced by the environment. And so how do we do this? So the setting that we are operating in is, we have the system Hilbert space and the bath Hilbert space. And I'm going to call the system Hilbert space H1 and the bath Hilbert space H2. And then I assume that both of them are finite dimensional. And of course, the total Hilbert space is then just described by the product space of these two. And I'll model a Hamiltonian on the composite system by this general form. I hope you can see my mouse. So the total Hamiltonian will have some system component, some Barth component, and some interaction component. And we can assume without loss of generality that all these Hamiltonians are traceless. And that's what we are going to do. So the usual premise that we are following in dynamical decoupling is that we can only address the system and we do not have access to the Barth. So that's also one premise that we will have in this talk. So then the idea of dynamical decoupling is that we average out all the components of the Hamiltonian on the system in such a fast and strong way that they will not build up again. And so this is implemented by acting with a finite unitary group that acts irreducibly. So we are going to just work with the adjoint representation, which is a fancy way of saying, okay, we are in the density operator picture, and when we want to act on a density matrix, we have to conjugate it from the left with our decoupling operation and from the right with the adjoint, right? And yeah, that's actually the setting that we're in. And so then dynamical decoupling is doing the following for you. So you have a time evolution under a Hamiltonian for some time t, and you split this time evolution into some smaller chunks. And at each time step of these smaller chunks, you'll apply some unitary from the group that you choose to take your decoupling operations from. Then what you will get is you get a time evolution, which is a product of small time evolutions, which are interspersed by these unitaries. And you can, of course, use the Trotter formula to bring them all up to the exponent and get just a sum. And if you do the math and go through this, you'll see that in the end, you get a time evolution that will only happen non-trivially on the Barth, and the system does not evolve anymore. So we'll actually achieve decoupling. The system and the environment evolve independent from each other. Of course, up to some Trotter error, right? Because we did some Trotterization. And the big question here is, if we want to quantify how good our decoupling performs, is how big is this Trotter error? And this is a question that I'm going to address in this talk. And in order to talk about error, we have to, of course, first introduce some error measure. So that's some intermediate goal that I'm going to do now, is I want to introduce you to some error measure that's a good way to measure this decoupling error. And in order to do so, we can use the Choi-Jamiukowski isomorphism to move from the area of quantum channels, which describe the evolution of our quantum state, to quantum states, right? And one thing that we can observe here is if we have a unitary quantum channel, we'll get a pure Choi-Jamiukowski state and vice versa. So this already gives us a hint that the purity of the system Choi state is a very good error measure for the decoupling efficiency. And I want to motivate this a bit more into detail and get quantitative about it. And in order to do so, I introduced two norms, which is first the Frobenius norm, which is just the norm induced by the Hilbert-Schmidt scalar product, and also the operator norm, which gives you the largest singular value of a matrix. So in our recent paper, we have a proposition that links nicely the distance to unitary of a quantum channel T to the purity P of its Choi state. And you can see that this inequality goes in both directions. So it tells you that if you have a quantum channel that is close to a unitary, then its Choi state will have a purity close to 1. And vice versa, if you have a Choi state with a purity close to 1, then the corresponding quantum channel will have a small distance to unitary. And this tells you that you can actually really use quantitatively the purity of the Choi state, or equivalently the operator norm of the Choi state, as a good measure for decoupling. But one thing I put under the carpet here is I used the Frobenius norm and I put quantum channels in there, right? But the Frobenius norm is actually a matrix norm, and quantum channels are not matrices. So I can't do that. But I mean, that's why I put these hats on there, so they'll actually save my life here. So I better tell you what they mean. And so if I think about a density matrix and I represent it in some basis EI, then a quantum channel will do nothing else than sending this density matrix to another density matrix, sigma here, for instance. And what I can do is I can just flip the bra, the EJ, to a cat, and then achieve some equivalent description of this density matrix in terms of a vector. And then the quantum channel as a linear map will just be a matrix that sends a vectorized density matrix to another vectorized density matrix. And by this, I achieve a vectorized a matrix representation of the channel. All right, so far so good. That's about dynamical decoupling and how we would measure error in dynamical decoupling. But I want to talk about random dynamical decoupling. And so random dynamical decoupling is particularly interesting because if you take large decoupling groups, long evolution times, or make the norm of your Hamiltonian big, then it has been shown by, in particular, Lorenza Viola and her collaborators, that you achieve better convergence or smaller decoupling errors. And what I mean with random dynamical decoupling is I will choose the elements, the group elements with which I intersperse the dynamics at random. In this case, I'll do that IID. So my probability distribution will just be flat. All right, so the question here then that arises is, okay, we achieve better decoupling errors in the random case, but how big is this error actually? And this is in general difficult to answer, because if I do it randomly, then if I do infinitely many decoupling steps, I also achieve infinitely many different random realizations of decoupling. So I have to find a way around that. And the way how we did it is with the framework that we call equitability of system and path. And that is, we do not consider the system evolution, which we are ultimately interested in, but we consider the path evolution instead. And then this gives us actually the exact same information, because ultimately what we want to do is we want to remove the interaction term of a Hamiltonian. And so if we remove this interaction term, then we just get a Hamiltonian that acts separate on the system and on the path. And both systems can actually be treated as closed systems. So if one subsystem evolves close to unitary, the other subsystem will also evolve close to unitary. So that's kind of the idea behind this equitability of system and path. All right, so I want to introduce some quick notation here in order to guide you through our results. So I already told you that we are working in the density operator picture. So I'll work with the Hamiltonian that acts by the commutator. And if I apply a group element, then as I told you earlier, I'll apply it from the left, and from the right, I apply the adjoint. And I also only allowed to address the system. So that's why it acts like VI on the system and identity on the path. And this whole action, I'll just denote capital V calligraphic, right? And then the evolution under a particular random realization of dynamical decoupling will look like this, where you just choose one decoupling operation at random VI, then you kick your system with this decoupling operation, then you let your system evolve under the Hamiltonian for some small time t over n. You choose another random decoupling pulse, let the system evolve for some small time, random pulse, evolution, and so on and so forth. And you repeat this whole procedure n+1 times. And then you get this En as your total CPTP map, which describes your evolution. All right, so let's assume we want to do this in the lab, and we have an experimentalist that does it, but he or she is really forgetful and just forgets which decoupling operation they applied, and we can't, like, they are at random, so we don't know which one they were, right? So we still want to describe this situation, and the way how we do it is we take the average over all these random realizations to get some average evolution. And this average evolution can actually be written in terms of this D, which is the projection onto the group average. And because the group acts irreducibly, the projection will always project onto the maximally mixed state, because in the end we get some evolution that is just that's just described by all the group elements, and then this will commute with the entire group. All right, so we will call the first one trajectory protocol, and the second one I'll call average protocol. Good. So now I introduced you dynamical decoupling, and I also want to introduce to you the quantum xenodynamics and make the connection to dynamical decoupling. So what's the quantum xenodynamics? Quantum xenodynamics is a pretty similar concept to dynamical decoupling. So we have a time evolution, and this time we don't intersperse it with unitaries from a group, but we will intersperse it with frequent projective measurements. And when we trotterize, we receive some effective evolution that is generated by an effective Hamiltonian, PHP, which we will call xeno-Hamiltonian. And this Hamiltonian just gives you an evolution that only happens in the subspace specified by the projection with which you will frequently project. And only in this subspace there will be some non-trivial evolution, and all the transitions between other subspaces are suppressed by the projection. And we have some very similar effect in the dynamical decoupling case, because the projection, the group average projection, is actually a Hermitian projection. So if we consider the average protocol, we get some xenodynamics. And so the xenodynamics that we receive here is a dynamics where we actually suppress all the transitions between the system subspace and the environmental subspace. So these are kind of the xeno subspaces that you should think of in the average dynamical decoupling case. All right. So the first thing that we did then is we computed the bound on the quantum xeno limit, and this takes this particularly simple form. So here you see the trotterized xeno evolution, and then here you see the target evolution, and the distance of these two evolutions just takes this particularly simple form and only depends on the evolution time, the number of projections that you apply, and the norm of the Hamiltonian. Now we can think of, we can use this immediately in order to bound the efficiency of dynamical decoupling. But the problem here is, since we are considering the average dynamical decoupling as a xeno effect, the average dynamical decoupling will project us to the maximally mixed state. So no matter which state I put in, I will always be projected to the maximally mixed state, and I'll actually destroy all the information. And dynamical decoupling, remember from the introduction, its target is to retain all the information. So basically, we can't just use this bound. But we can go a step further, and we can look at the evolution that is actually created by this xenodynamics from this group average projection. And as you can see here, the generator of this dynamics gives you an almost unitary evolution on the bath. So we can use this information and infer that back to the system. And so what we did here is we computed actually the purity of the choice state of this average dynamical decoupling protocol, and it's the purity of the choice state on the bath, for which we could just use this xeno limit theorem. And so now I just put this proposition here once more. We can use convexity, a concavity of the purity, or like Jensen's inequality, if you like, in order to infer this information down to the trajectory protocol, right? And so then we receive a decoupling error for the distance to unitary on the bath, right? Okay, but we are ultimately interested in how close is our evolution on the system to a unitary one. So we want to investigate this, but in order to do this, we are talking about these reduced choice states, and I want to go into a little bit more detail here because there are some subtleties. So consider a quantum channel T that acts on a bipartite Hilbert space and eats some row 1 tensor row 2. So how do I compute the choice state? I do it by first computing the reduced channels and by taking the partial trace. And then I can compute the reduced choice states from these reduced channels. But there's another way I could do it. And this other way would be, I first compute the choice state of my quantum channel, and then I partially trace out the respective system on the level of choice state to achieve some reduced choice state. And actually, these two are not the same. And we were like thinking about, okay, what's the relation between them? And what we found was they are actually the same if the input state over which we are trace is the maximally mixed state. And we were also able to bound the operator norm of the choice state for some arbitrary input state in terms of the operator norm of the choice state where I put the maximally mixed state as an input state. So we are going to use these two lemmas, of course, if we want to bound the convergence of the dynamical decoupling on the system. Right. So with this knowledge, we are actually now ready to introduce the main result. And the main result here is we computed the expectation value of the purity or the operator norm of the Choi-Minkowski state of the system for an arbitrary input state of the bath. And it characteristically only depends on the bound that we computed on the quantum Zeno limit before. And I want to give you some flavor how the proof would look like. So the first thing we would do is we would take this this expectation value of the purity, use Jensen's inequality again to get out the expectation value out of the square root. Then by definition, the purity is larger than the operator norm. And then by the lemma on the previous slide, we can draw a conclusion on the operator norm of the choice state where I have the maximally mixed state as an input state, because here I had an arbitrary input state. And now I just put the formula from the previous slide here once more. And now comes actually the equitability of system and bath into play. So what we are doing is the following. So we have the evolution under the trajectory protocol of the full system, and so system and bath. And the full evolution is, of course, a unitary. So because it's a unitary, it has a pure choice state, right? And because its choice state is pure, its reduced states share the same spectrum, and it's just given by the Schmidt coefficients of this big state. So actually, that tells you that the operator norm of the choice state on the system is the same as the operator norm of the choice state on the bath. And so using that, we can replace the operator norm of the system choice state here by the operator norm of the bath choice state here. But for the bath choice state, we already know how close it is to unitary, because we have this Zeno bound that we computed for the average protocol, and we can just insert it here in order to achieve a bound on the system choice state, right? So we also did some numerics, and so here you can see the expectation value of the purity, and this is the number of decoupling steps, and you actually see that we get the right scaling. So our bounds achieve the right scaling that we also get numerically, and the same for the operator norm. And similarly for the bound that we put on the xenodynamics, we also get the right scaling in n. Here we did the numerics for the group average projection as an example. Right. So with this, I would like to summarize in order to give some time for questions. So what we did was we computed a bound for the quantum xenodynamics, which takes this particularly nice and simple form. Then we were able to compute the efficiency of random dynamical decoupling. And you can see that this bound characteristically depends on the bound of the xenodynamics that we computed before. So we were actually able to relate these two concepts directly to each other and show that the efficiency or the convergence speed of the random dynamical decoupling just depends on the convergence speed of the quantum xenodynamics for these particular parameters. And this was all possible because of this equitability of system and bath framework, which physically we can interpret as, in the end, we only want to remove the interaction part of a Hamiltonian. And if we do that, both subsystems will evolve unitarily because we can treat them as closed. And mathematically, we can justify that by looking at the choice states. So because the total evolution has a pure choice state, its reduced choice states share the same spectrum and just given by the Schmidt coefficients. So with this, I would like to come to an end of my talk. Yeah, I think I'm a bit before time, but I think that's a great opportunity in order to ask questions, and I'm happy to take them. Thank you.
Thank Alexander for his beautiful talk, and now it's open for some questions.
Guruda, can I ask a question?
Yeah.
Hi, Alexander. So it was a nice talk. So I have actually a couple of questions. The first one is like you are defining the decoupling error in terms of the norms of different types of norms.
Right.
So the thing is that in finite dimensional Hilbert spaces, since the norms are equivalent up to a constant, so
Right.
how does it carry over to the error, measurement of error? How does this equivalence carry over to that?
Yes.
That is my,
That's a really great question, because we also talk about this in the paper, but I didn't want to talk about it in the talk too much because it would be quite technical. So we also can give bounds on the diamond norm error, for example, of the particular evolution. And what you will get is you'll just get some constants that depend on the dimension of the finite dimensional Hilbert space, of course. So yeah, you can use these bounds to and transfer them to other error measures, of course. We just found that this particular error measure is a pretty powerful one in this particular case, and also a more simple one to grasp, I think, because it's conceptually much simpler than the diamond norm.
Okay, thanks. And my second question is, like I was just wondering, I might be mistaken, does this work have any kind of relation, or can we like have an application in environment assisted error correction? Because there is one word like in environment assisted error correction, the quantum channels has to be represented in terms of mixture of unitary channels. So does it have something, any relation to that? I was just wondering about this. I might be ignorant about the whole affair, but I was just wondering about this.
So I think I can't answer this question because I don't know anything about environment assisted error correction. So I'm sorry, but yeah, I don't know. It might be, it might not be. I can't answer this question. Sorry.
Okay. Thank you, Alexander. Thank you very much.
Sure.
If there is no further question, then let us thank the. Yeah, there is question.
Sir, can I ask a question?
Yeah. Quickly.
Thank you, Alexander, for the nice talk. A quick question that I have is, you considered for the error correction, you considered the vectorization, you adopted the vectorization technique. So was it any problem if you could choose the difference between the two Choi operators instead of vectorization?
So you mean, yeah, of course. You could also take the difference between two Choi operators, but then you would need to specify the distance to which Choi operator, right? And you only know that you are close to a unitary evolution, but you don't know to which unitary evolution you are close to. So yeah.
Okay.
So
yeah. Okay. Thank you very much.
Sure.
Thank Alexander once again, and thanks all the speakers in this session. So our morning session is now closed. This is time for lunch break. So we'll meet again at 14:10. and did his PhD from most possibly this Shipur engineering, but now it has a different name, I think. What is the name?
IIEST, Indian Institute of Science and Technology.
Yeah. Okay, Sattyavrata Adhikari, you take over and start the session.
Thank you, Guruda. So, good afternoon, everyone. Welcome to the this second last session of this wonderful conference. So, in this session, we have 6 talks, and every talk has duration 20 minutes. So, I would like to request all the speakers to maintain the time limits. So first of all, I would like to call Tamal Guho to present his talk. And he's from University of Hong Kong. And the title of his talk is On Composition of Multipartite Quantum System, Perspective from Tamal, please share your screen.
Can you see my screen?
Not yet. Yes.
Yes. And
it again goes off.
Yes, I make it a presentation mode.
Now,
is it clear? Yeah. So can I start?
Yes, you will start. We can see that.
Yeah. Okay. Yeah. So thank you. I'm Tamal Guho from University of Hong Kong. I'm a postdoc here, and I just have joined here. And before that, I have just done my PhD from Indian Statistical Institute. So the title of my talk is basically, and I'll try to discuss on the composition of multipartite quantum systems, but from a time-like perspective. So it is here in archive. This is the archive ID, and this is a collaborative work by Shomda, Manikta, Mir, and there are 4 other guys from either TVM, Shahil, Edwin, Shomrat, and Ramkrishna. So you see, compositions are really interesting for our worldview, starting from that good old Gutenberg printing press to any daily life object. There are so many compositions. There are several parts, and we finally compose them and to get some new things there. But there are some weird compositions, like this picture. If you consider these individual rod, all of them are possible. But whenever you are trying to compose them in this particular way, they are actually impossible. Means our classical physics doesn't allow, or classical notion doesn't allow to compose these 3 rods in this way. So this is by famous Penrose triangle, and these are few many others examples. So okay, so these kind of peculiar compositions we know in the framework of classical theory, or classical notion. But what about the quantum compositions? What actually the most notion of my talk today? So if you just warm up, I know that every one of you are familiar with these things, but just for sake of a completeness, that any elementary quantum system, we denote it with a Hilbert space. And in the Hilbert space, over the Hilbert space, we will define the density matrices as states. But apart from the idea of state, we will move to some another thing that is called state cone. And this is actually the collection of all positive Hermitian operators, which is embedded in the collection of all Hermitian operators. These are basically my state cone. And what we define the measurement, these are the element of these positive Hermitian operators on this vector space and sum up to identity. So, okay, we know about our elementary quantum system, but the question is, what about our compositions?
So, as you remember, in the third day of this talk, of this conference, Miguel Navascas, he has correctly pointed out that, okay, for quantum composition, why we do need to assume the tensor product structure. But the tensor product structure is in the Hilbert space. What is the structure in the cone space? Means tensoring to Hilbert space, I can generate different state cone. What should be the state cone in the composite system? That is the main goal of our talk. So it may be like this, the left one called shape and the right one called shape bar, where this one is the state cone, the red one, and the blue one is the effect cone. That means that for the shape theory, I will only allow the product states as my state, and as a result, my effect will be larger. And in the shape bar theory, I will allow only the product effects as my measurement, and all the positive things will be taken to be my state. But interestingly, quantum theory is neither of these, but it is like this, where the state cone and the effect cone exactly merge. The question is why it is. It is sometimes called a self-duality, but not the self-duality in the sense of Hilbert space, but in the sense of state and effect cone. So our question is why it is so. So be used to with some terminology, what I will generally use for this talk. They are a shape which represents the minimal composition of state cone, and shape bar, which is the maximal composition of state cone. And there are the mathematical definitions of these compositions. Now, one more thing, what do you mean by distinguishability? You have some set of states, and what do you mean by the set of states are distinguishable? That by performing a measurement, for every outcome of this measurement, you can assign definitely a single state of a system. This is called the distinguishability. For quantum theory, this 0, 1 is distinguishable, but 0 plus is indistinguishable. And there is another thing, that what is operational dimension? In each single run, by performing a measurement, how many quantum state, or how many system state you can actually discriminate. This is said to be the operational dimension. For standard qubit theory, it is again 2. And what is the information dimension? You consider a pair, collection of set, so that any pair of the pair from the collection of this set can be distinguished in each run. This is said to be the information dimension. And again, you consider 3 states, suppose 0, 1, and psi. In each run, among these 3, you can choose 3 pairs, but only the pair 0, 1 is distinguishable here. 0 psi or 1 psi cannot be distinguished, at least for qubit case. So again, for qubit thing, the information dimension is 2. But is operational dimension and information dimension exactly same? No, it is not. You can consider some toy model like this square, 2 square inscribed in some rotated way. These omegas are the state and e's are the effect of this hypothetical model. And one can check that the operational dimension for this theory is 2, where the information dimension is 4. Means there are 4 pure states in this theory. If any 2 of the states are given to you, you can exactly discriminate between them. But in our standard quantum theory, this operational dimension and information dimension both are 2. So now the question comes that how do we generally exclude some correlation? Suppose this correlation. Is it allowed in our physical world? No, because you cannot communicate without communication. So this is the principle of no signaling. What about this correlation? Is it allowed? No, you cannot communicate too much with a little communication. This is the principle of information causality introduced by Marcin Pawlowski in 2009. So what about the correlations obtained from, say, bar theory, means the maximal tensor product? Okay, in bipartition, there is no difference with standard quantum by Barnum in 2010. However, with quantum input, there may be some difference, which recently been introduced by Edwin and other collaborators. And in multipartite case, they really differ, means there are different correlations, but at least from the no signaling perspective, they cannot be excluded. But whatever the exclusion principles they have considered, that is from the space-like scenario. What if we go to the time-like scenario? So what do you mean by the time-like scenario? So space-like scenario means there are 2 things, like A and B here, they are spatially separated. They will get some input, and depending upon that input, they will make some measurement on their shared correlation. and generate some output. But in the meantime, they cannot communicate to each other. That's why I have put them into different light cone. And here, this is a time-like scenario where this is the sender and this is the receiver. So the sender will send some system, physical system, to the receiver, and receiver perform a measurement on it and generate some outcome. So this is the probability generated here. And you see here, the total thing is put in a single light cone. So that means they are time-like separated. So these are the time-like correlations. So whatever I will try to talk about this part. So I introduce a particular game that is called the pairwise distinguishability game. Suppose there are some states, eta, and a particular state will be given to Alice, and some particular index, eta, will be given to Alice, and depending upon that index, Alice will encode that index in a system omega n and send it to Bob. Now Bob is asked by the referee that, okay, I will give you two index, eta and eta prime. What is Alice's message? Is it eta or it is eta prime? And Bob has to guess it perfectly. So we call this game like PND. D means distinguishability, and this eta, this N means what is the cardinality of the set eta. So it is obvious that if in some set theory we would like to win the game PND, then we will need n number of pairwise distinguishability game in that theory. Pairwise distinguishable state in that theory. But now we are allowing that, okay, so the game is so that Alice can send 2 qubit. What if she composed these 2 qubit in a separable way or in a set composition? So there is the main result. 4 qubit communication from Alice to Bob is required for winning the game P12T. Means if this En, number n, the cardinality of the indices eta, is equal to 2, then for the standard quantum theory, you will need 4 qubit communication, wherever when you compose them in a separable way, means if you consider the minimal tensor product, then only 2 separable bits are sufficient to win the game. And how does it happen? There are 2 different matrices. You can see E1 and E2. They are 2 entanglement witnesses, but E1 plus E2 is equal to identity, and they are positive on any separable state. Interestingly, if you consider 2 states, rho 1 and rho 2, then the effect of E1 on rho 1 tensor rho 2 is like this, and effect of E2 on rho 1 tensor rho 2 is like this. So you just remember this expression. Now you can see, consider this set of the states. There are 3 indices of k and there are 4. So 3 to the times 4, there are total 12 states. So if you take XX and ZZ, means 2 of the sigma x upstate or 2 of the sigma z upstate, then E1 clicks sharply on sigma x up, tensor sigma x up, and E2 clicks sharply on sigma z up, tensor sigma z up. So in this way, in the separable theory, you can discriminate between 2 sigma x upstate from 2 sigma z upstate. So this kind of notion was, I should acknowledge that this kind of notion has already been introduced by Arai and Professor Mahito Hayashi in 2019 in their famous paper in this Journal of Physics A. So you may ask that, okay, what is, so this is actually the set of the state n in our consideration. So what if the referee's option is xx and yy bar? You have said about xx and zz. What if it is xx and yy bar? Okay, then Bob will apply some unitary on the Alice's set bit, which is like U1 tensor U2, and this U1 tensor U2 is such that xx will be unchanged, but yy bar will be zz. Then again, you will perform the measurement E1, E2. So it is simple, and so on and so forth. You can check that for any pair from these 12 states can be perfectly distinguished by Bob, if we assume the separable composition. So this is the proposition that for n greater than 2k, the game P and D cannot be won with k qubits communication from Alice to Bob if the composition rule is standard quantum. But 2k number of safe bit communication is sufficient to win the game P12 to the power k perfectly if these are the separable composition, whereas it requires 2k plus some ceiling function of k log 3 number of qubit. So what we want to mean that with safe composition of qubit, you can make much more communication than the standard quantum communication. And this is a physical principle that you cannot communicate that much in a physical theory. So you see this Schrödinger in this 1935 paper, he has said that this entanglement is really discomforting. So this is the statement from his paper. It is rather discomforting that the theory should allow a system to be steered or piloted into one or the other type of state at the experimental's mercy, in spite of his having no access to it. You know, this somehow comes to the letter comes presented by Weismann as the quantum steering, but the Schrödinger has some problem with it. But entanglement do really exist. That is the experimental notion by Alan Aspect in 1981 and his group, and by Hensen on this paper by loophole free Bell inequality violation, which means that nature observes Bell inequality violation. So nature gives, means there are entangled states in nature. So what is our answer? Our answer that entanglement should exist. So these experiments say that entanglement really exists, but we argue that entanglement should exist because the strength of the physical communication should be limited in a physical theory. So if there is no entanglement, you have the separable states only the separable composition, you can communicate too much in a pairwise distinguishability game. So this is a physical principle. You cannot communicate that much. So safe composition of quantum theory cannot be excluded under time-like setting, but can be excluded under time-like setting, but not in the space-like domain. In this case, in this way, our work is really interesting. And this has no valid entropic description. So the information content principle introduced by this Horodecki group in 2007 cannot describe this safe composition. But there is another question that in our thing, referee has some input to the Bob's part. What if there is no input from the referee side to the Bob part? Then can we define some information theoretic principle which will set theory violate? It is not known. This kind of notion was introduced in 2007 by Delorno, Buscemi, Professor Vlatko Vedral in a famous paper of no hypersignaling. And moreover, any composition you consider from the separable composition to the standard quantum composition is actually excluded by the principle of pairwise distinguishability game or strong communication in the pairwise distinguishability game. So that's all. And at the end, I will want to remember one of the famous quotation by Sherlock Holmes: when you have eliminated the impossible, whatever remains, however improbable, must be the truth. Thank you.
Thank you, Tamal, for your interesting talk. And finish it in time. So we have few minutes for question answer. So is there anyone who want to ask anything to Tamal? Then they can ask. Okay, so if there is no questions or no comments, then
hi. Yes. So since I am a co-author of this, I would like to make a comment and also like a question to Tamal, that for these analysis we have taken this no restriction hypothesis, right? Right. Yes. Right. So if we don't assume such things, these implications don't directly follow, right? Sorry. If we don't assume that, then this SEP does not may not allow that much.
Yeah. You can put your restriction, avoiding this no restriction. You can put the restriction so that these kind of weaknesses will be just forbidden in your theory. Then it is also a very physical model, right? Yes.
Right. So could one think that how much restriction do you need to put just to recover this limited communication? Could one think like that?
Yeah, I think that if you use the separable composition of quantum systems, and if you limited your measurement up to the entangled measurement, which actually assured in the standard quantum theory, then it is exactly the same theory. means exactly a perfect physical theory, right?
Right. So even by introducing one more measurement, like which is not entangled, like some entanglement witnesses, could one preserve this? I mean, like
no, because the thing is that you cannot means you cannot add exactly one witness. You have to add two witnesses because you have to make it identical. And whenever you will add two witness, I think you can always give some examples.
At least more than two. Yeah.
You have some more than more communication power, right?
Yes. So this is also another corollary from this.
That's why I have mentioned that for any composition between the shape to quantum can be ruled out in our model.
Right. Okay. Thank you very much. Yeah.
Okay, so I just want to make some comment on Shomda's comment actually. See, this theory can be possible, but while taking this type of witness, we have to keep in mind that the reversible transformation should not be restricted.
Yeah. But if you choose only two, if you include only two witness, then your reversible transformation should be limited.
Yes.
At least if you think that just like quantum theory, there is an analogy between the state transformation and the measurement transformation, then your reversible dynamics should be limited. But we are talking about, okay, suppose there is a hypothetical model. Okay, I allow that my reversible transformations are limited. What about this? Obviously, I agree with you that the limitation on the reversible transformation actually leads to a peculiar model.
Yes, because whenever you choose all the reversible transformation, there is a possibility to transform those witness to the witness which is not allowed in this theory.
Yeah. Obviously. That's why you have to restrict your reversible transformations also.
Yes. That's right.
Okay. Yes. So thank you, Tamal, once again for your interesting talk. So now our next speaker is Sumit Nandi. Sumit, are you here? Yes. Sumit, please present your screen. So Sumit Nandi is from SNBO's National Center for Basic Sciences, and his topic of talk is genuine multipartite non-locality by generalizing Wigner's approach. Yes. Sumit, please.
Okay. Good afternoon, everyone. So is my screen is visible? Hello?
Yes, it is visible. Yes, it is visible.
So, do you hear me? Hello, am I audible?
Yes, you are audible also.
Okay. So good afternoon, everyone. So myself, Sumit Nandi, as introduced by Sottoda. So here goes the title of my talk: Wigner's approach enable detection of genuine multipartite non-locality and its final characterization using all possible bipartitions. So it has been done in collaboration with my dear colleagues, Dr. Devashish Shah, Professor Dipankar Home, and Professor Arjun Sen Mujumdar. Okay, so this is the content of my talk. After a brief motivation, I will speak about Wigner's treatment for detecting non-locality, which is quite a different approach from that of Bell-CHS inequality, and I will show how to construct genuine non-local inequality in tripartite and multipartite scenario using Wigner's prescription. Then I will discuss. Okay, so let us start with the typical Bell experiment in which two observers, namely Alice and Bob, share a subsystem which was originated from a common source, and each of them are provided with two dichotomic observables, which is labeled as X and Y, and which yield two possible outcomes. So these outcomes are A and B. So this kind of experiment is generally characterized by this kind of joint probability distribution, PABXY, which is the probability of obtaining the outcome A and B by measuring with the observables X and Y respectively. Now, in a more general scenario, when quantum mechanics governs the system, then this joint probability distribution cannot be rewritten as a product of the individual probability terms. So this is the essence of non-locality, and this non-locality is revealed by the violation of this inequality, which is commonly known as popularly known as Bell-CHSH inequality. Now, any state which satisfies this inequality the local states, otherwise it is non-local state. So the violation of this inequality implies non-locality as long we are restricted in a bipartite qubit scenario, and as well as it can be generalized in multipartite scenario also, and vice versa. So we will now show how to define this kind of non-locality in another way, which was given by Wigner. So in his derivation, so he assumed the existence of an overall joint probability distribution and a marginal distribution which is derived from this overall joint probability distribution. So let us take the example as before of Alice and Bob, who are playing a game with their subsystems and dichotomic observables X and Y. Now let us find the joint probability distribution corresponding to the outcomes as obtained from by measuring with X0 and Y0 with plus and plus. So this kind of marginals can be expanded in terms of this overall joint probability distribution given in the right hand side. So this summation will be summation is expanded over x1 and y1. So in this way, we can compute other joint probability distributions for different combinations of x and y, and rearranging for a bipartite qubit system, we will have 16 such joint probabilities, and rearranging those joint probabilities will straightforwardly can construct the inequality given in equation 3. So and this the violation of this inequality implies non-locality. And I would also like to mention that this inequality 3 is equivalent to Bell-CHSH inequality for bipartite pure state. Now, motivated by this prescription, in another work, this approach was generalized for detecting inequality in multipartite scenario. I have taken an example of a tripartite inequality, which is known as a generalized Wigner inequality. So in this inequality, as we mentioned previously, the procedure of deriving this inequality is same as before. Now, this all genuinely tripartite entangled state violates this inequality. However, violation of the above inequality does not necessarily imply genuine non-locality, as it can be seen by considering this example of this state. So this is a biseparable state shared between 3 observers, and here we can see that Alice's subsystem is correlated with that of the joint subsystem of Bob and Charlie. So this is naturally not a genuinely non-local state. But interestingly, this state can violate the locality condition imposed in equation 4. Hence, equation 4 does not necessarily imply the condition of genuine non-locality. So to overcome this limitation, we have used generalized. We have used Wigner's prescription, and we have constructed a genuine inequality for detecting non-locality in multipartite scenario. So this is the bottom line of this work. Now how to construct this kind of inequalities? So to construct this inequality, we have considered all 3 different bipartitions of a given multipartite state. So let us start with the tripartite state. So we know that for a tripartite case, there exist 3 different bipartitions, one across A and BC, another one is B across AC, and C across AB. Now we will consider that this BC as a single entity, and as if BC is being measured with 4 observables, which are the combinations of the observables given to Bob and Charlie. So these are the combination x0 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 x1 x1 x0 and x1 x1. So these observables also yield 4 possible outcomes: plus plus, plus minus, minus plus, and minus minus. Now we will find the joint probability distribution corresponding to the outcomes. So this is a typical example of a joint probability of obtaining the outcome plus plus and plus from each of the observable x0 x0 and x0. Now if we expand this inequality joint probability, so this sum is over x1 and x0 x1 x1 x0 and x1 x1, and this x0b and x0c is fixed with the outcome plus and plus to confront with the left hand side of this equation. So if we expand this sum, then we will have 128 such terms in the right hand side. Now rearranging all the joint probabilities for different combinations of x0 and x1, we will obtain a L inequality for this bipartition A across BC. Now let us read this following theorem. So we have provided this theorem to detect non-locality in tripartite scenario. Now after constructing all this inequality, one is across A and BC, which is denoted as IABC, and so on, IBAC and ICAB. Now if a given tripartite state violates all these 3 inequalities simultaneously, then we will call this state is genuinely non-local. So in this way we can eradicate the limitation previously shown in the example. All the biseparable states satisfy one of these inequalities. Now it may happen that some state violates the first inequality, but it satisfies or it fails to violate the other inequalities. So then it will be said not genuinely non-local state. So this is so in this way we have established a framework to derive genuine non-local inequalities in the tripartite scenario. But as we increase the number of subsystems, the complexity also increases, because we know with the increases of number of subsystems, and the number of bipartitions also goes on. For example, for a given n-partite state, we have 2 to the power n minus 1 different bipartitions. So we have to construct this much of LR inequality to certify genuine non-locality. So this is a non-trivial self. So to make our life simple, what we have done, we have constructed an inequality, LR inequality, for a arbitrary bipartition across, in which n number of particles are in one partition and another n minus 1 number of particles in another partition. Sorry. So we have denoted the observers R1, R2, and so on in the first bipartition, and S1, S2, and so on, and in the second bipartition. And as before, we have considered that they are using 2 observables x0 and x1, and these are dichotomic observables. Now in this way we are able to construct an inequality across the bipartition n versus capital N minus small n. So this is the form of this inequality. So it may look quite strange, but nice implications are there for this equation. So to see why this kind of inequality is important to certify genuine non-locality, let us take a few examples. So firstly, we will consider a tripartite case. So as I stated before, we need 3 LR inequalities to certify genuine non-locality of a tripartite state. So these 3 non-local inequality can be derived by putting small n equals to 1. So if we put small n equals to 1 in equation 10, then we will get this LR inequality across the bipartition A and BC. Now, similarly, we can construct other inequalities, but we will do it in a more easier way. We will just permute the observables and corresponding outcomes for deriving other inequalities. For example, if we want to construct inequality across BAC, then we will interchange the observables and outcomes between R1 and S1, and so on. So in this way, we will get 3 LR inequalities from equation 10. So this is the essence of equation 10. We can construct an LR inequality across any arbitrary bipartition by suitably choosing the value of small n. Okay, so now let us take the example of a quadripartite state. So for quadripartite state, there are 7 different bipartitions. The first type of bipartitions occurs between a subsystem and 3 other subsystems, and in this way we get 4 different bipartitions. And second type of bipartitions occur by pairing a group of by grouping a pair of subsystems in each partition. So in this way we have 3 different bipartitions. So altogether we have 7 different LR inequalities to be constructed. Now we will construct the LR inequalities across A and BCD by simply putting small n equals to 1 in the above equation, and we will get the other inequalities by putting small n equals to 2 in equation 10. In this way, we can construct 7 different LR inequalities to certify genuine non-locality of a quadripartite state. Now, in the next slide, we will compare the efficacy of our generalized inequalities with that of some existing LR inequalities to certify genuine non-locality. Particularly, we will talk about the inequality which was derived by famous George Vetrucci. So we know that he derived an LR inequality to certify genuine non-locality in tripartite case, and later it was used for any arbitrary and partite state. Now, if we take this particular example of few states like generalized W state and this maximally sliced state and quadripartite W state, then we will see that this doesn't violate Vetrucci's inequality. So for generalized W state, if we fix the parameter in this way, mu equals to pi by 4 and theta between 2.0 to 3.0, then we will see that we will see that Vetrucci's inequality is not violated for this particular parameter, but our derived sets of inequalities are violated for this particular parameter values. Now we will consider this maximally sliced state. This maximally sliced state doesn't violate Vetrucci's inequality, but it is a genuinely non-local state. But it does violate all the 3 inequalities simultaneously. So it is a genuinely non-local state. And more importantly, we know that W state is a famous genuinely non-local as well as genuinely entangled state. So if we go beyond 3 qubit state, then it can be seen that W state doesn't violate Vetrucci's inequality, but it does violate our derived set of inequalities. So this is the importance of our derived set of inequalities. We can set examples of few states which are genuinely non-local but cannot be detected using Vetrucci's prescription. Now we will consider another important significant feature of our inequalities. Suppose a given n-partite state is not genuinely non-local, but there may exist non-locality in some specific bipartition, say across small m versus n minus m cut. Now till date we have no such prescription to analyze this issue. There exists some literature where entanglement in subspaces has been discussed, but entanglement in non-locality in subspaces is quite a new concept, and it is till date we have no knowledge. Yes.
Sumit, you will have
Hello?
only 2 minutes. You have only 2 minutes.
Okay. So using our inequality, we can detect this kind of partial non-locality exists in some arbitrary and parted state. For example, we have given this example of a product state. So this is a product state, so it is not genuinely non-local. But if we construct inequalities across the bipartitions ABCD and ACBD and ADBC, then we'll see that these three inequalities are violated. So although this so this state is not genuinely non-local, but non-locality exists in the bipartitions, which are grouped, which are formed by grouping a pair of particles in each partition. So this is the essence of our inequality. Okay, so lastly, I will conclude by mentioning a future direction of our research. So we know that using multipartite non-local state, we can enhance the performance of quantum information processing protocols. So particularly, we want to talk here about conference key agreement protocol, which is a variant of QKD protocol in multipartite scenario. So it would be interesting to find the security analysis using our inequality for this protocol. And another important thing is that the study of comparative behavior between maximum violations of generalized WLR inequalities and the measures of multipartite entanglement, such as tangle. In this context, it would be interesting to find a comparative behavior between these two quantities in multipartite scenario.
Okay. Thanks, Sumit, for your nice talk. So we can take one quick question. Okay. Tapashwini Patro, and he's from BITS Pilani, Hyderabad. And the topic of our talk is absolute fully entangled fraction from spectrum. Tapaswini.
Yes, sir.
Please continue. Please.
So, does my screen visible?
Not yet. Yes, it is visible now. It is visible now. Yes. Please make it full screen. Okay, thanks.
Yes, sir. So, good afternoon all. I am Tapaswini Patro, a PhD scholar from the Department of Mathematics, BITS Pilani, Hyderabad campus. So, first of all, I would like to thank the organizer for giving me an opportunity to present our work in such a wonderful platform. The title of my presentation is Absolute Fully Entangled Fraction from Spectrum. And basically, this is a collaborator work. And they are my collaborator, Dr. Kaushiki Mukherjee from Government Girls General Degree College, Kolkata. Dr. Mohammad Asad Siddiqui, he is a research associate from the University of Electronic Science and Technology, China. Professor Indranath Chakravarti from IIIT Hyderabad, and Dr. Nirma Ganguly from BITS Pilani Hyderabad campus. And this talk is based on this archive paper, and this is the archive reference number. So over here, I would like to point out the outline of my talk. So as my title is Absolute Fully Entangled Fraction, so I will start my talk with a brief introduction of absolute fully entangled fraction and what is the relation of this fully entangled fraction in our work. Then what is the motivation behind of our work in this fully entangled fraction. Then here we will discuss that what are the work that have been done in this area. And in this section, we will discuss that are the result we have got in this particular paper. Then I will end my talk with the result which we have got and some future direction of work. So actually what happens in quantum information theory, detecting a quantum source quantum research which has some significant advantage over classical field is very much important, and entanglement is one of them. So actually, whenever a state is separable, but if you apply some non-local unitary operator or some global unitary operator, then it may convert it into an entangled state. So when you are applying a non-local unitary operator upon a separable state, there will be two cases. Either its separability criteria will be preserved, or it may convert it into an entangled state. So when the separability criteria preserved, then we are saying that this state is the absolutely separable state. And if the property doesn't preserve, then by applying some non-local unitary operator, we can convert the separable state into an entangled state. So when we are writing a particular state, we are choosing some basis. So when a state is separable in one basis, it may be entangled in another basis. So so if you apply some non-local unitary operator, the property of a given quantum state may be changed. So and non-local unitary operator have that ability which can change the basis. And in the area of absolute separability criteria, it was first proposed by Emil in the year of 2012, and various work have been done regarding the absolute separability criteria, which by fixing the eigenvalue. And our motivation of work comes from that paper. Like we are trying to do the same work in absolute fully entangled fraction, right? As we know that the state whose fully entangled fraction greater than 1 upon d that are useful for quantum teleportation and entangled distillation. So, and one more thing does, suppose if it is, so what we thought that suppose a state is there and its fully entangled fraction is less than 1 upon d. So we are thinking that can we apply some non-local unitary so that we can enhance its fully entangled fraction to greater than 1 upon d from less than 1 upon d. So in this particular work, what we have done, we have proved that this fully entangled fraction is convex and compact, and we have also got some example of state initially whose fully entangled fraction was less than 1 upon d, but after that we have applied some global unitary operator and its fully entangled fraction get increased. And we have also constructed a witness operator which detect those states whose fully entangled fraction can be enhanced by using some global unitary operator. And so our work is basically based upon the Han-Banach theorem of functional analysis. But it tells that suppose a set is there, if it is convex and compact, then one can always construct a hyperplane which will separate this state from its outside. So our motto is that suppose we will take a set of states which are absolutely separability, and if we are able to prove that this is convex and compact, then we can construct a witness operator so that it will detect those states which are not absolutely fully entangled fraction. So that by applying some global unitary operator, we can enhance its fully entangled fraction to greater than 1 upon d. Right? So this witness operator is basically a observable which has at least one negative eigenvalue, and it is satisfied this two property. That is, if you take any state from this set, then it should satisfy this condition, and there should exist at least one state from here, and it is satisfied this property. Particularly in this paper, they have constructed a witness operator and to detect those states which are useful for teleportation. Now, what is the absolute fully entangled fraction? For a given quantum state, the equation 1 is the expression for the fully entangled fraction, right? Suppose we are taking a set F, then F is the collection of those states whose fully entangled fraction is less than 1 upon d. Then what do you mean by absolute fully entangled fraction? Absolute fully entangled fraction means collection of those states whose initially fully entangled fraction was less than 1 upon d, but after that we have applied some global unitary operator, then also its fully entangled fraction remains preserved, and we termed as AF. Now, what is the motivation of our work, right? As we know that the state whose fully entangled fraction less than 1 upon d that are useful for teleportation. So suppose a state, the state which are whose fully entangled fraction greater than 1 upon d that are useful for teleportation. Suppose a state is there and its fully entangled fraction is less than 1 upon d. Then we may say that these states are useless for teleportation, right? So we are thinking that can you take some useless state its fully entangled fraction is less than 1 upon d, And can we apply some non-local unitary operator so that this fully entangled fraction can be greater than 1/d, and it will be useful for quantum teleportation. So this is the motto of our work. Now we will discuss that what are the work that have been done in this fully entangled fraction. There is to calculate the fully entangled fraction of a given quantum state, there is no direct method. But however, given certain condition, one can find the fully entangled fraction of a given quantum state. Even also there are some upper bound of fully entangled fraction. So particularly in this paper, by using the Lagrange's multiplier method, a formula have been found to calculate the fully entangled fraction of a 2-qubit state. And in particular in this paper and this in 3 papers, they are able to find out the upper bound of a fully entangled fraction, which depends upon the Frobenius norm, maximum eigenvalue, and correlation matrix. And particularly in this paper, this is the upper bound of a fully entangled fraction. But for 2-qubit system, they are able to prove that the upper bound is exactly the fully entangled fraction of a given quantum state. And in this paper, they have designed a necessary and sufficient condition for maximally entangled state, both for pure and mixed state, in the dimension of d dash tangent d, where this d dash is greater than or equal to d. Now, from a separable state to generate the entanglement, this work was done in this paper, and the characterization of a non-absolute, and the characterization is also done in this paper. And to detect the non-absolutely separable state was done in this paper. Right. Now, from here, we will discuss that what are the results we have got. So I will I will explain this by taking one schematic diagram. Suppose this white color circle is the collection of those states whose fully entangled fraction is less than 1/d, even under the application of global unitary operator. So we have termed them as AF, right? So as per the Hahn-Vanham theorem, if we are able to prove that this is convex and compact, then we can construct a hyperplane which will detect those states which are lying in blue color ring state. And before that, in one paper, this whole F set, it collection of separable state. And after that, in this paper, they have shown that it is both convex and compact. And they have constructed this teleportation operator which detect those state, this ring which lies in this green color ring state, right? But here our motto is we want to prove that this white color circle is convex and compact. So here we have proved that for convex part, we have taken 2 states, ρ1 and ρ2, which belongs to this A plus. And this is the proof for convex part. Now, to prove that compact, we have one result. It tells that the closed subset of a compact set is compact. And as I told that in particular in this paper, they have proved that this F is compact. So F is a subset of F. So if you are able to prove that this F is closed, then we can prove that this is compact. And now using the same state, they have shown in this particular paper, we are able to prove by taking some arbitrary limit point of F, we are able to prove that this F is closed. So if F is a subset of the compact set of F, so it is compact. Now convex is done and compact part is done. As we are able to prove that this white color circle is convex and compact, so now we can construct a witness operator. And in this particular work, we are able to construct a witness operator S, which is given by this expression S equal to U dag U, where this W is the teleportation witness operator, which was given by in this paper. And as it is a teleportation witness, this operator, it should satisfy this condition. Now we got another result. Sorry. Now we got another result. Like we are fixing the eigenvalue of a given quantum state, so that, and we are saying that if a quantum state satisfies this condition, then we will say that this particular state will belong to AF class, right? So we got that for D cross D dimension, if the maximum eigenvalue of a given quantum state satisfies this condition, then we will say that this state will belong to AF class. But however, this is a sufficient condition. But for 2-qubit state, we proved that this is both necessary and sufficient condition. where this lambda 1, lambda 2, and lambda 3, lambda 4 satisfy this condition. And we also got one result that the maximum fully entangled fraction is attained in the Bell diagonal state. So this is the proof. Now here we got some example whose initially fully entangled fraction was less than 1 upon d. Like for 2 qubit state, its fully entangled fraction was 1 upon 2. So after that, we have applied some global unitary operator U1. After applying the global unitary operator U1, the new modified state is this one. Again, we have calculated the fully entangled fraction, and now it is 2 upon 3, which is nothing but it's at 0.66. So initially, it was not useful for teleportation because its fully entangled fraction was half. But now we can use this state to quantum teleportation. Now we also got a state in 2q3 state. Sorry, and after that, actually we have constructed the witness operator, right? So as it is useful for teleportation, so we have calculated the trace of S1 and X1, right? And here we got the value is 1 upon 6, which is less than equal to 0. Hence, our teleportation witness operator, which are able to detect those states which lies in F minus F class, right? And here we have taken another 2q3 state. From this paper, we got this example, and here they have shown that for Q lies within this range, its fully entangled fraction is greater than 1 upon 3. So it is useful for teleportation. But however, for Q belongs to this range, its fully entangled fraction is less than 1 upon 3. So we have applied this global unitary operator upon this state. After applying this global unitary operator, the new modified state is this one. And as I told, there is no direct method to calculate the fully entangled fraction of a given quantum state. So here what we have done, by using the witness operator we have constructed, we are able to see that whether this state is useful for teleportation or not. Right? So the new teleportation witness is S2 equal to U2 dagger W2, where this W is the teleportation witness operator, which has taken from this paper. So here trace of SY2 equal to this thing and this one, and which is less than equal to 0. For Q belongs to 0 to 1 upon 3. But initially for 0 to 1 upon 3, its fully entangled fraction is less than 1 upon 3. So it was not useful for teleportation. But after applying this unitary operator, now it is less than 0. So it detects this teleportation witness operator detect those states which can be useful for teleportation, right? So these 2 examples we got, which fully entangled fraction was initially less than 1 upon 2 or 1 upon 3, but we have applied some global unitary operator. Now these are useful for teleportation. And the another thing is that in 2qubit state we have got one example, and here we have we got that this particular class of state will belong to A plus. Why? Here in this particular example we have taken the isotropic state, and the eigenvalues of this isotropic state are this one, right? And this state is separable for this range and entangled for this range. And here they have shown that all entangled isotropic states are useful for teleportation. Now the thing is separable. As we know that for separable state, its fully entangled fraction is less than 1 upon d. So it is not useful for teleportation. So yeah, we thought that can we, by applying some global unitary operator, can we enhance its fully entangled fraction from less than 1 upon d to greater than 1 upon d. But here what we got, the maximum eigenvalue of this isotropic state is 1 upon d. We got one result that if the maximum eigenvalue of a given quantum system will be less than or equal to 1 upon d, then we will say that this particular quantum state will belong to AF. And here we got that the maximum eigenvalue of this isotropic state is 1 upon d. Hence, this particular class of isotropic state belongs to AF class. Right? So we cannot increase its fully entangled fraction from less than 1 upon d to greater than 1 upon d. So this is the another result which we got. Now the next thing is that here we got that the relation between absolute separability and absolute fully entangled fraction. And we got that absolute separability is a proper subset of absolute fully entangled fraction. Actually, as we all know that a state which is separable, its fully entangled fraction is less than 1 upon d, right? So for absolute separability also, its fully entangled fraction will be less than 1 upon d. And same thing for AF. So if a state is AF, its fully entangled fraction will be less than 1 upon d, right? So here, but actually here what we have done, we have taken this example, and the maximum eigenvalue of this row is 1 upon 2. So as the maximum eigenvalue is half, so it will belong to F. But particularly in this paper, they have shown that this class of state is doesn't belong to S. So here we have got one state which belongs to A but doesn't belong to S. Hence, this absolute separability is a proper subset of A. And so these are the results that we have got. So we have we are able to prove that this class of F set is convex and compact, and we have got the relation between the AF and S, and we have also constructed a witness operator which are able to detect those states whose fully entangled fraction can be enhanced. And like we did the same work in symmetric dimension, but in future we can think about all the same work in asymmetric higher dimension like d dash tangent d, but d dash is not equal to d. And we can also one can also think about the external points of the given set. That's it. And these are the references that we have used in this particular paper. Thank you.
Thank you, Tapaswini, for your nice talk. So now, any question or comment? Okay, thank you once again, Tapaswini. So I would like to move on to the next speaker. So our next speaker is Moen Naseri. So I don't find him in the participant at this moment. So Moen, are you here?
Hello, good afternoon.
Okay, fine. Good afternoon. So our next speaker is Moen Naseri, and he is from Center of New Technologies, University of Warsaw, Poland, and he will talk about this coherence characterization of macroscopic quantumness. Okay, Moen, please.
Can I share my screen, or like should I send my PDF?
Yes, you share your screen.
Okay. Can you see it?
Yes, it is visible.
Okay. So good afternoon, everyone. The subject of this work is about macroscopic quantumness, and this work we did it with my master's supervisor, Professor Sadegh Raisi, in my master's thesis. And it's about coherence-based characterization of macroscopic quantumness. So first, I will go through some preliminaries, and we know that quantum mechanics has been a very successful theory, which has been explained many phenomena in physics, but we know that it's still unclear that why the macroscopic world around us behaves classically, and we exactly don't know what is the transition, the nature of the transition from like microscopic, quantum microscopic world to classical macroscopic world is. It is also Schrödinger's cited this problem in his thought experiment, and he also mentions that maybe like in microscopic realm, it would be like okay that we cannot characterize and specify some the objects with some properties like momentum and spin, but we know that because our basically our senses is unreachable to that realm, to the microscopic realm. But in microscopic world, having like quantum superposition is like kind of preposterous. So in this direction, there are some approaches to quantum to classical transition, some within the frame of quantum mechanics and some outside the frame of the quantum mechanics. So we know that like within the frame, we have the theories like decoherence theories and measurement precision theories, and also some other theories which are trying to modify the Schrödinger equation in order to guarantee that the wave function will collapse when like we are reaching the macroscopic scale. But before like presenting and introducing these models, first we have to take a step backward. And first of all, we have to exactly define what do we mean by the existence of quantum mechanics in macroscopic world. So this term should be exactly defined in order to be able to properly answer to these problems and questions. So now here there's a term is coined as macroscopic quantumness, which basically, like very generally, it means that collective or global quantum effects in macroscopic world. For example, maybe a Schrödinger cat state could be considered as some macroscopic quantum state, but exactly it should be defined, you know. So maybe at the first sight, it appears very simple that we said, okay, macroscopic quantumness is macroscopicity plus quantumness. Like, for example, consider superconductivity phenomenon. We can consider it a quantum behavior which exists in macroscopic system. But is it really a macroscopic quantum effect? We're actually referring to Leggett, Anton Leggett. We know that superconductivity phenomenon is actually the result of the collection of tiny quantum effects. So it could not be considered as a genuine collective quantum effect. So it's not a macroscopic quantum effect. So here's the question. So what is exactly the macroscopic quantum states, and how can we define it and measure macroscopic quantumness and compare this quality for different states and systems? In this direction, there have been introduced and presented some measures that these measures vary in approaches, formulation, and applicability. Like for some measures are only applicable for pure states, some only like consider the Schrödinger cat-like states, or also their applicability in different systems, like spin system, photonic, like massive systems, or some measures of a few measures also like applicable for general systems, any system. Let's like review some of these measures very briefly. Like, for example, Shimizu and Miyatara, they have introduced a measure based on the spread of entanglement, the genuine spread of entanglement in like multipartite system, and like they kind of quantify this intuition based on the maximum variance of a local observable, which is like maximized over all local observables. Or for example, Froese and Dor, they associate the property of macroscopic quantumness to the quantum Fisher information of the spin systems, which is maximized over, again here, which is maximized over all local observables. Or Yadin and Vedral, they quantify and also define the concept of macroscopic quantumness in a way that, given a density matrix, the maximum multipartite system of GHZ, which can be distilled with a optimum distillation protocol out of this density matrix could establish the definition of the macroscopic quantumness, and that maximum n, the number of particles in GSZ state, quantifies the macroscopic quantumness for that given density matrix. There are also other measures which trying to quantify and define this concept, like Li and Jiang, they like associated with the oscillations of the wave function in the Wigner space, in the phase space. So here, now I'm going to, we also in this direction present a new measure for this concept, the macroscopic quantumness. So first I go through the approach, which approach we had. We define, or generally our approach is that the state has the properties of macroscopic quantumness if it has large coherence between states that can be distinguished by a macroscopic measurement. So based on this approach, we see that the measure is actually basis dependent, because both the coherence and measurement are highly dependent on the basis. So based on this approach, we can say that the measure of macroscopic quantumness is actually a measure of coherence, which incentivizes the coherence between macroscopically distinguishable states. This could be another translation of our approach. Now we should try to kind of quantify this approach and intuition. So coherence is basically related to the off-diagonal elements of the density matrix, and maybe a simple monotone for the quantification of coherence is the CL1 norm of coherence, which L1 norm of coherence, which also could be expressed as the sum of the mod of all the off-diagonal elements of the density matrix. We expect a high coherence for macroscopic quantumness, because if we consider coherence as a genuine quantum effect, so a macroscopic quantum effect should also have like high quantumness. So if we consider it like equivalent to coherence, so it also, we expect high coherence for macroscopic quantumness, but it's not enough. Like genuine quantum or coherence is not enough for this quantification. And why is that? Because basically coherence, generally all the coherence measures treats all off-diagonal elements of the density matrix the same. Like for example, if I want to take an example, like consider these two states. So from the aspect of only coherence, they're both their coherence is the same. Like at least from the point of view of L1 norm of coherence. But we see that in the left side, it is like a superposition of two eigenstate of the magnetization, which they only differ in one spin. Maybe in real world, they only differ in the magnitude of H bar, but the other one, it is the superposition of two eigenstates which are different in their values in the order of n H bar, and n if n goes to a high value, so it's like the superposition of two completely different states. So we here define a concept of a measure of distinguishability, in the basis of the observable A, which we are investigating system from the point of view of the observable A. So a natural definition could be like the distance or distinguishability of two eigenstates of the observable A could be quantified by the discrepancy of the corresponding eigenvalues, like Dij is equal to the mod of AI minus Aj. Now, for a measure of macroscopic quantumness, we start from the measure of coherence, but we have to give weight because the approach was that we must incentivize the effect of coherence between macroscopically distinguishable states. So we can like multiply the each elements of the density matrix, which are kind of representation of the coherence by the distance dij, or the distinguishability of dij. But we should also be careful because this produces a weight to any dij. It should also be renormalized by the sum of all the elements of the density, the off-diagonal elements of the density matrix. So this could be a proposition of macroscopic quantumness, which simultaneously consider the coherence and the distinguishability in one formula. So this could be also, this is the final measure. And it could be also seen that if, as you see that this like rho ij over the sigma rho ij, basically it's a distribution function. So we can say that, or this final measure is the distance, the average of the distance over all based on the distribution function, which is consists of the off-diagonal elements of the density matrix. And this is some schematic like view of our measure, which like you give to any off-diagonal elements a distance, and the more the distance, so they participate more in the measure of macroscopic quantumness. But okay, what is this advantage of this measure? So the previous measures so far have been introduced. They are like, they consider some extremist states, like there are some extremist states which are established in the context that are like have genuine macroscopic quantum effects, like GHZ states or Nunes states. So the previous measures, they only consider some properties of these extremist states, and they would try to generalize it to the other. But we here, we didn't like consider these states. We just try to like build a first principle approach, like by some principles from some approach, and then we try to define it and then formulate it. So, and then we try to like apply it for these extreme states, and then we see a very good accordance with the previous measures, and also that it would maximize. Also, we proved by some method of Lagrange multipliers, we proved that this measure, that this one is basically is maximized for these extreme state, like for Nunes state or GHZ state. It is maximized for these, and also it has a good agreement with previous measures. And we see like some of the important measures which could also apply for different system and different states. Like here we have seen like these green boxes are they are kind of the same. Like we in some, like apart from some factors, our measure gives the same value for these states. And also it is this measure is also in accordance with the macroscopic quantumness framework of Yadin and Vedral, which has been produced in 2015 in their paper. And thank you very much for your attention.
Thanks, Moin. Thanks for your nice talk. So, any questions or comments? Okay, so Moin, I would like to ask one question that you have defined a measure for measure the macroscopic quantumness. So you already say you said that this measure you have not studied the properties that this measure should satisfy. But I would like to ask one thing, that what measure means if there is some measure, then what properties this measure should satisfy, means in earlier work. In earlier work, they may have some properties that this type of measure should satisfy.
Yeah, like in the framework of Yadin and Vedral, there are like 4 important basically properties that these measures should satisfy. As one, like the convexity, and also they should like it should be also monotone, you know, under some special operations. And these operations is not very well defined in this context of macroscopic quantum solutions, you know, because we actually don't know what is this macroscopic quantumness. So these operations is in any measure is defined is different, you know. Like for example here, if we define some operations which like destroy the off-diagonal elements of the density matrix, then it is like monotonic under these operations. And also there are two other properties, which is like it basically means that if you have two states like this, which the eigenvalue of the superposed states are bigger, like for example, the discrepancy of the eigenvalues of the 0n plus and the 1 tensor n is bigger than the discrepancy of the eigenvalues for the left state. So the right state should have a bigger value of macroscopic quantumness. This is also an important property which any measure should like satisfy based on the Yadin and Vedral framework of macroscopic quantumness.
Okay, thanks, man.
Thank you.
Okay, so if there is any if there is no question, then I would like to call next speaker, Bialan Bhattacharya. He is from SN Bose National Center for Basic Sciences. And he's talking about this generating and detecting bound entanglement in 2Q-treat using a family of indecomposable positive map.
Thank you, Shotobrada.
Yes,
am I audible?
Yes, you are audible.
Okay, so let me share my screen. Is my presentation visible?
Yes, it is visible.
Let me
make it full screen.
Okay.
Okay.
Is it fine? And the slides are moving? Okay.
Yes.
Okay. So, shall I start now?
Yes, please.
Okay. So, first of all, I'm Bihoran Bhattacharya from SN Bose National Center for Basic Sciences, Kolkata. First of all, I'd like to thank the organizers for giving me the opportunity to present our work here. And it's been a wonderful experience in this nice conference to be a part of this very nice conference. Thanks to the organizers. Today, I'm going to discuss one of our recent works that generating and detecting bound entanglement in 2Q-treats using a family of indecomposable positive maps. So it's a recent work. It's been published in Journal of Physics Communications. And it's a collaborative work with Dr. Suchetana Goswami, Ronak Mundra, Dr. Nirman Ganguly, Dr. Indradil Chakraborty, Dr. Shamyodev Bhattacharya, and Professor Archana S. Majumdar. So let me share the plan of the talk first. First of all, I'd like to give you a short introduction along with the motivation behind the problem. And from that, I'll come to the technical details. I'll require a few definitions. I'll discuss them because these definitions will be required for the rest of the presentation. And with that definition, that will include some part of the positive map as well as the entanglement theory. Indecomposable positive map that we have proposed will come after that. And along with that, I'll discuss about the entanglement witness that we have constructed and along with its properties. And finally, I'll discuss about the structural physical approximation of our proposed map. And with that, I'll discuss about the PPT entangled state that we have come up with. With this, I'll conclude. So, as we know that quantum entanglement is an amazing thing. It's an essential resource to perform several quantum mechanical or quantum information theoretic tasks like quantum teleportation, quantum lens coding, quantum key distribution. So these are the certain tasks without entanglement we cannot do. So we have a proper resource theoretic framework of entanglement. And whenever we have a resource in our hand, the first question that comes to our mind is how to detect that resource. So in this case, the question precisely is, given a quantum, here the entanglement is a resource, then how to detect entanglement? So theoretically speaking, one of the most effective way to detect entanglement is by using positive but not completely positive maps. For example, we can talk about transposition map. Transposition map is a positive but not completely positive map. Now, hello, is it okay? Am I audible?
Yeah, so, you are audible.
Okay, thank you. So, for example, we can talk about transposition map, which is positive but not completely positive. But at least we can say that for 2-qubit and qubit Q-tree scenario, all entangled states can be detected via transposition. But there is a big challenge. The challenge lies in the higher dimension. For example, explicitly speaking, that from 2Q-tree onwards, there are certain entangled states which cannot be detected by transposition map. We call it PPT entangled state. I'd like to mention here that this is a weak form of entanglement from which we cannot distill maximally entangled state under local operation and classical communication. So that is why these states are called bound entangled states as well. But detection of this bound entangled state is basically a challenging task. And for this, actually, we require indecomposable positive map, which is a very, I should say, it's a finer algebraic setting. We require indecomposable positive maps to detect such PPT entangled state. Now, in this work, we have actually devised a positive indecomposable map acting on Q-tree system, and we have also come up with a new PPT entangled state on 2Q-tree system. So with this motivation, I'll go to the technical things. I request some definitions for the rest of the talk that I mentioned. But before that, I would like to say a few words about the history of the positive map, because the idea of the theory of positive linear maps between sister algebras was originally, it was started by Cadison around 1950s actually. But after that, the theory got gradually developed, and later part, the positive linear maps between matrix algebra became popular because of it, the non-triviality of its structure. Basically, the positive maps, the structure of positive maps is highly non-trivial, even in low dimension. Now, throughout my talk, I'll restrict myself on the positive maps acting on finite dimensional operator algebra. So in this case, as you can see, my cursor, that CD denotes the d-dimensional complex Hilbert space, and BCD denotes the space of all operators acting on d-dimensional complex Hilbert space. It is necessary to say that on finite dimensional, every operators are bounded. So essentially, this is a class of all bounded operators acting on d-dimensional complex Hilbert space. So a linear map lambda from BCD to BCD is said to be positive if it takes the positive cone of operators to the positive cone operators. That is, if it takes a positive semi-definite matrix to some positive semi-definite matrix. Now, a linear map is said to be K positive if the amplification map that is acting on the system along with the ancilla, this is positive for some natural number K. Now, a linear map is said to be completely positive if it is K positive for all natural numbers. Now, similarly, we can define K co-positivity and complete co-positivity as the map along with the concatenation with the transposition map. Now, given a positive linear map, there exists an isomorphic image onto the operator space on tensor product Hilbert space. Given the isomorphism is given by the map acting on the one part of the maximally entangled state. So this isomorphism is famously known as Choi-Milankovsky isomorphism, and it plays a very crucial role in the theory of positive maps because it more or less translates everything from the language of positive linear map to the language of operators. For example, if whether a map is completely positive or not can be characterized in terms of its Choi operators. This isomorphic image of a positive map under Choi-Milankovsky isomorphism is known as its Choi operator. So a map is completely positive if and only if its corresponding Choi operator is positive semi-definite. Now I'd like to discuss about the decomposability. And on a historical note, when Caddison in around 1950 started the study of positive maps between sister algebras, a few years later, William Steinspring actually defined the complete positivity. Now, positive maps form a convex cone, and under this cone, complete positive cone and complete co-positive cone, they are the known famous subcones. So it was a kind of dream to the mathematicians whether a given positive map can be decomposed in terms of this CP cone and co-CP cone. But in fact, in 1963, Erling Stromer came up with the result that given a positive map on BC2, basically the two-dimensional operators acting on two-dimensional complex Hilbert space, all such positive maps can be written in terms of the CP map and co-CP map. And this is precisely the notion of decomposability. So decomposability, a map is said to be decomposable if we can express it as an algebraic sum of a CP map and co-CP map. But in 1975, Mandu and Choi came up with a twist that there are certain maps which we cannot write in terms of a CP map and co-CP map. Namely, these are called indecomposable maps. So these indecomposable maps will play a crucial role in this theory. Now, I'll say a few words about separability or entanglement. A bipartite quantum state rho AB on the tensor product operator space is said to be separable if there exists a density operator sigma I and delta I and the probability distribution pi such that rho AB can be expressed as a convex combination of sigma I and delta I. Now, given otherwise, it is said to be entangled. Now, given a state, whether it is separable or not, the first in 1986, Asher Perez first showed a necessary condition for separability. He showed that every separable state is positive under partial transposition. Obviously, with that we can say that every NPT state is entangled. But in the same year, Horodeczky et al. Came up with the necessary and sufficient condition for separability, which states that any bipartite state rho is separable if and only if all positive maps lambda, the operator identities a lambda on rho is positive semi-definite. And as you can see that how non-trivial it is, because to certify a state whether it is separable or not, you have to scan for all positive maps. And indeed it is true because computationally it has been shown to be an NP-hard problem. Now, a bipartite state is said to be positive under partial transposition if we act transposition on one party of the combined state, which is positive semi-definite. Now, this indecomposable positive map will see that this indecomposable positive map can detect only PPT entangled state. As you can see from this, if a map is decomposable, it cannot detect a PPT entangled. So with these technical things, we come with the first result that we define a one-parameter family of map acting on BC3. C3 is the three-dimensional complex Hilbert space, and BC3 is a space of all operators acting on three-dimensional complex Hilbert space. So this is a one-parameter family of map. The parameter ranges from 0 inclusive and 0 exclusive and 1 inclusive. So as a corollary, we show that this is a map which is it's not completely positive by its Choi-Milankovsky isomorphism, and it is an indecomposable positive map for each alpha because it can detect this particular PPT entangled state. Interestingly, in this 1982 paper, Erling Stromer derived a necessary and sufficient condition for indecomposability of a positive map. Now, in that paper, Erling Stromer actually used this particular operator to show the indecomposability of the famous Choi map. Now, in our work, we have also used the same particular operator, PPT entangled state, to detect the indecomposability of our proposed map. Now, this is the adjoint map that we have constructed. It is also positive and indecomposable. Now, every positive but not completely positive map gives rise to an entanglement witness. Entanglement witness is particularly a Hermitian operator which gives a non-negative expectation value to all separable states and a negative expectation value to some entangled state.
Now, given a positive but not completely positive map, its corresponding Choi operator gives rise to an entanglement weakness. So in our case, we have also constructed the corresponding entanglement weakness, but we can show that for a certain parameter value, namely for alpha equal to 1, there exists a pure product state, as you can see, delta and gamma, that this expectation value is 0, which shows the weak optimality of the corresponding operator. And obviously, one may ask the question about the local implementability of this weakness, and we can show that this can be implemented locally in terms of the standard Gell-Mann matrices. Now, one problem with the positive and not completely positive map is that it is unphysical. It cannot be realized in the laboratory. So one solution to get rid of this problem is the corresponding structural physical approximation of the positive map. Now, this SPA, or the structural physical approximation, has a nice geometric feature. If we consider a given map, positive but not completely positive, and if we consider a completely depolarizing map, and if we can imagine a line which connects these two maps, the line where it connects or cuts the CP cone is basically the SPA of the corresponding map. Now, the how to obtain the optimal structural physical approximation for a positive map was given by Pavel Horodotsky and Arthur Icqif in 2002. Finding the same prescription, we have found our the structural physical approximation corresponding to our map, and we have constructed the corresponding Choi matrix corresponding to this SPA map, and it is found to be a positive semi-definite operator because it is a CP, as I mentioned earlier. But interestingly, for alpha equal to 1, we can show that this is a PPT state. Now, once we have a PPT, we readily ask the question whether it is entangled or not. And at this point, we should keep in mind that your transposition map will not help us. So we have only two ways where we have to go either by detection of some indecomposable map. Otherwise, we have to apply some entanglement detection criteria for higher dimension. In this case, we have adopted covariance matrix criterion given by Ottfried Kuhne and his collaborator in 2007. This is a condition. This is a criterion which based on some inequality. Here it is a C matrix, is a corresponding covariance matrix whose trace norm has to be calculated, and these are the local marginal states. So in our case, we have computed the left-hand side and the right-hand side of the corresponding inequality, and this graph shows that at alpha equal to 1, the left expression is strictly greater than the right-hand side expression, which actually gives us the violation of covariance matrix criteria, which actually gives us the presence of entanglement for alpha equal to 1. So with this, we can certify that there is an entanglement for alpha equal to 1, which is certainly PPT that we found earlier. So we have got a presence of PPT entangled state on 2-qubit system. So with that, I come to the conclusion that we have devised an indecomposable positive map acting on qubit quantum system. So entanglement weakness comes out with the Choi operator corresponding to the map. It has been shown to be weakly optimal, as well as the local implementability of the weakness have been demonstrated with the Gell-Mann matrices. And we have constructed the structural physical approximation of the map corresponding to the map. And with that, we can come up with the 2Q3 PPT entangled state. And interestingly, this state cannot be detected by the famous Choi map and also another indecomposable map given by Robert Okiewicz and Marek Miller. So with that, I'd like to thank you. Thank you for your patience. I'll be happy to take questions.
Thanks, Bielan. So any question or comment? Okay. So if there is no question, then I would like to thank Bielan once again. And then I would like to move on to next speaker, Anindita Bera, who is from Nicholas Copernicus University, Poland. So Anindita, are you here?
Yes, yes. Hi.
Okay, fine. So she will be talking about this, a class of Bell diagonal entanglement witnesses in C4 tensor C4, optimization and this spanning property. Okay.
Can you see my screen?
Yes, it is visible.
Okay.
Yes.
Let me, is it full screen or let me make it a slideshow maybe?
I think it is full screen.
Now it is, I think that, yeah.
Yes.
Just a moment.
Okay. Start on it.
Okay. Thank you, Shuttada.
Thanks to all the organizers for giving me an opportunity to present my talk here. And from last 2 weeks, it's an wonderful seminar that we all are attending. And also, I mean, it's we all understand it's a very difficult task. And thanks a lot for organizing such a conference. So yes, let's start. Today, I'll talk about our recent work. The title is A Class of Bill-Diagonal Entanglement Witnesses in 4x4 tensor 4 systems. And I'll also talk about their optimizations and the spanning property. Actually, in the last talk, Biholan makes my job very easier. He talks about most of the stuff that, of course, I'll talk about, the initial stuff. Thanks, Biholan, for that. So, yes. This is the summary of my talk. First, I'll give some brief motivations, and then I'll talk about the entanglement witnesses. That also be some portions, I think this girl talked about. I forgot her name. And then I'll talk about this optimal entanglement witnesses. And then I'll talk about the entanglement witness that we considered in our work, which is covariant bill-diagonal entanglement witnesses. After then, I'll move to the known results of the optimal entanglement witnesses in 3x3 systems. And then, of course, I'll describe our results and some take-home messages. So here is the brief motivations. Of course, we all know that quantum entanglement is arguably the most peculiar feature of quantum theory that also demarcates it from the classical one. It is also a crucial ingredient in quantum information processing applications. For example, entanglement-based quantum cryptography, quantum dense coding, quantum teleportations, measurement-based computations, etc., etc. And though there are tremendous progress in understanding of entanglement, we still lack its full characterization, especially in terms of the entanglement detections. That is, the methods that can faithfully discriminate between the entangled and separable states. Indeed, we have a wealth of various operational entanglement criteria for bipartite quantum states, which already exist in the literature. For example, the partial transposition criteria, the majorization criteria, the cross norm or the realignment criteria, the covariance matrix criteria, etc., etc. However, due to a very rich structure of entanglement, most of currently available techniques are either only sufficient in characterization or restricted to a narrow class of states. Therefore, it is of paramount importance to have robust ways of entanglement detection. In particular, some operationals or, we can say the measurable tools that are of special interest here. And here comes the entanglement witness. That is, it is such a method which is based on the notions of entanglement witness and observable that is capable of detecting entangled states. So what is entanglement witness? The central concept is based on the Hahn-Banach theorem on nonlinear space. So this is the Hahn-Banach theorem. Let S be a convex compact set in a finite dimensional Banach space. Let rho be a point in the space with rho does not belong to S. Then there exists a hyperplane that separates rho from S. Based on this Hahn-Banach theorem, one can describe what is an entanglement witness. The entanglement witness is a Hermitian operator, and it satisfies these conditions. So it will be that there exists rho such that the trace is always less than 0, while for all sigma belongs to the separable states, this trace is always positive. Of course, then it comes to the decomposable point. When an entanglement witness can say decomposable or non-decomposable. Biholan talks about the decomposability in terms of the positive map, and there is this one-to-one correspondence between the entanglement witness and the positive map. And here I'm talking about the decomposability or non-decomposability in terms of the entanglement witness. So an entanglement witness is decomposable if and only if there exist operators P and Q with, if you can write it in this way, P plus Q of partial transposition of A. However, you can see clearly this decomposable entanglement witness cannot detect a PPT entangled state. The proof is very straightforward. So, and how one can describe the non-decomposable entanglement witness? An entanglement witness can said to be a non-decomposable if and only if there exists at least one PPT entangled state which is detected by the witness. And therefore, one can restate the consequence of the Hahn-Banach theorem in this way. That is, if rho is entangled, if and only if there exists a witness W such that the trace is less than 0. Rho is a PPT entangled state if and only if there exists a non-decomposable entanglement witness such that the trace is less than 0. Sigma is separable if and only if for all entanglement witness, the trace is always greater or equals to 0. So this is a schematic view of the Hilbert space with two states, ρ1 and ρ2, and two witnesses, EW1 and EW2. Clearly, here we are considering EW1 is a decomposable entangled witness, and it detects only NPT states like ρ1. And EW2 is a non-decomposable entanglement witness, and it detects also some PPT entangled states like ρ2. Note that neither of these witnesses, EW1 or EW2, detects all the entangled states. And here comes the notion of the optimal entangled witness. Given an entangled witness, let us define a set of entangled states DW, which are detected by the witness W. So the set of DW will be in this way, that is, you need to consider those rows such that the trace of W row is less than 0. If this DW is a superset of DW tilde, then of course W is more effective than W tilde because it detects more entangled states than W tilde does. Therefore, an entanglement witness W is said to be optimal if there is no other entanglement witness W prime such that DW is a subset of DW prime. Therefore, the knowledge of optimal entanglement witness is sufficient for the full characterizations of separable or entangled states. Now, I will talk about the sufficient conditions for optimality that we considered in our paper, which is the spanning property. What is that? That is, if a set of product vectors, if you consider in this way, Shike tensor phi case, such that it satisfies this averaging. That is, if you consider the averaging in this way, and also these product vectors, it span the whole space, then W is optimal. Note that it is a sufficient condition. And therefore, one can also say that this W has also a spanning property. Of course, I mean, these notions of the spanning property one can find in this PRE paper of this Maciek-Levenstein et al. And we considered in our paper the spanning property. Now I'll describe how we construct our entanglement witnesses here. Here we consider the covariant Bell diagonal entanglement witness, and the construction as follows. First, you need to fix a computational basis in this way. Suppose you are considering the computational basis 0, 1 until n-1. Then you need to introduce a family of well unitary operators, UMK, which of course can be defined by these equations. And of course, one may know that this well operators matrices, it need to satisfy these conditions. These are all the conditions that it need to satisfy. Now, by considering this well unitary operators, the generalized Bell states in tensor n systems can be written in this following way. And therefore, a bipartite operator X in tensor n system is Bell diagonal if one can write X in this way, summation over XKL PK. And of course, PKL is, this is the, we are considering the corresponding rank 1 projectors. Now we need to consider this when this X, so in our motivation is we need to consider this X should be the Bell diagonal as well it should be the covariant. For the covariant part, for that we first need to consider a maximal commutative subgroup of UN in this way. So this Tn is a maximal commutative subgroup of UN, and then a bipartite operator X is said to be a T-tensor T-star covariant whenever it satisfies this condition. And now this bipartite operator X also with this covariant structure, also with this covariant properties has this following structure. So this X we are considering in this way. It is Bell diagonal as well as it is the covariant operator. And note that we consider these Hermitian Bell diagonal operators, which are of course the tensor T-star covariant as well as the Bell diagonal. For such operators, there are some properties of this AKL and BKL. For such operators, the Hermitian matrices, this AKL is circulant, that is, this AKL is alpha k minus n for some real vectors alpha 0 until alpha n minus 1. And for BKL are constant, that is, we can consider all this BKL is equals to beta, which belongs to some real numbers. Now, of course, this is a Hermitian Bell diagonal operator, which is a tensor T-star invariant covariant. But also we need to show that this X is a legitimate entanglement witness. For that, of course, there should be some conditions between AKL and BKL. So what are those conditions? The sufficient conditions are here. So we give one proposition, that is, if the circulant matrix, this AKL satisfy these conditions, that summation over all these alpha i's are in -1 together with these conditions, and then this W will be an entanglement witness. Note that now this AKL are this alpha k minus n, because AKL is the circulant matrix, and here this BKL all are constant, and here it is -1. And if you consider in this way, then this W is an entanglement witness. Also, you can write it in a more compact form. So this is a more compact form where this Pn plus stands for the projector onto the maximal entangled states. So how it will look like? I mean, it may seem complicated, but there is a highly symmetric form. So the thing is, suppose consider n equals to 3. So for the C3 tensor C3 system, if we consider alpha 0 A equals to A, alpha 1 equals to B, alpha 2 equals to C, then our witness looks like this. So this is so look at in the diagonal we have ABC, CAB, BCA in this way, and all these II and JJ elements it is replaced by -1, and all the dot terms are 0 here. So this is for n equals to 3. You can increase the dimensions. For n equals to 4, it will be like this. Of course, then at the time you need to consider d equals to alpha 3. You can increase your dimensions and it will be in this way. So this is the covariant Bell diagonal entanglement witness that we consider. Now, one thing I need to mention is that, of course, there is a one-to-one correspondence between entanglement witness and the positive map because of the Choi-Jaminski isomorphism. So the witness that we have, of course, it will also correspond to a positive map in this way, where this for our witness, for corresponding to our witness, the map will have this form. That is, phi ii will be in this way, and phi ij one need to consider in this way. So this is a one-to-one correspondence between the entanglement witness and the positive map. Now let's come to the results. So this is the known results. This is not our result. This is already previously known results. But before going to our results, I need to tell about this. Otherwise, it will be systematic. So for the 3x3 systems, so what is this AKL? Is this circular matrix? So this is the structure for AKL, and then by considering these two conditions, it has. One can get all these conditions in a much more simpler form. So if one can calculate. So the conditions for the 3x3 systems is A plus B plus C equals to 2 and BC equals to A minus 1 whole square. This is the corresponding entanglement witness for the 3 tensor 3 systems. Of course, it looks like this. Now let's come to the questions of the optimality. Before going to the optimality questions, one can see this type of witness can be parameterized by a single parameter phi, which belongs to 0 to 4 to pi. And this is the parameterization, a single parameterization. Note that if our A is less equals to 1, then the authors, mainly the Ha and Kai, and later on the Professor Darek Kuczynski and Philip Udarsky and with Niefko, all of them showed that if A is less equals to 1, then this witness is an optimal entanglement witness. Moreover, if A is strictly less than 1, then this WABC enjoys a spanning property. When we say it is spanning property, what does it mean? So here, of course, it is an optimal, and spanning property means, so for the 3x3 systems, we should get 9 linearly independent 9 linearly independent vectors such that it can satisfy the average, the corresponding average should be 0, which means that here, this is the way if one can find these 9 linearly independent vectors which satisfy this averaging. And therefore, of course, for strictly a less than 1, this WABC, it enjoys the spanning property. Why at not a equals to 1? I'll come to later. Because at a equals to 1, this witness actually it becomes the Choi witness, and for Choi witness it is optimal, but it does not have the spanning property. Yes, for a equals to 1, this entangled witness corresponds to the Choi witness, which is W110 and W101. So this is the value of ABC. So we are writing WABC, for which there are only 7 vectors that satisfy this averaging. And note that at a equals to 0, it is a decomposable witness. So of course, it will not be an optimal here. So this is the results for the 3x3 system. Now let us move to our results. So what will happen if we increase our dimensions? So here we have ABCD is, we consider alpha 0, alpha 1, alpha 2, alpha 3. And of course, from here our AKL will have this circular matrix structures. And from these 2 conditions, one can get, these are the total conditions. And if one do some more algebra, then we get 2 class for the 4x4 systems. For the class 1, the condition is A plus C is equals to 2 and B plus D is equals to 1. And for class 2, A plus C is 1 and B plus D is 2. And then the corresponding entanglement witness has the following form. So, I mean, if you want to see a matrix structure, this is the corresponding entanglement witness. However, we have 2 classes. For the 3x3 dimensions, we have single classes where all the ABC, it can parameterize by a single parameter. For 4x4, we have 2 classes where A plus C, if the first class A plus C is 2, for the second class A plus C is 1. Of course, now we need to do the parameterization. Then we all have seen that for both the classes. So let us first consider the class 1. For class 1, also we can parameterize by a single parameter, theta, but this theta belongs to 0 to pi. And this is our parameterization. In this way, one can parameterize for the all the coefficients ABCD in class 1. And we denote the corresponding witnesses by in this way. We have shown that. So here you can see for theta equals to 0, it corresponds to the witness will be W1110. So this is the value of A, B, C, D. So A is 1, B is 1, C is 1, D is 0. And this corresponds to the kind of generalization of Choi entanglement witnesses. So also for theta equals to pi, we get another Choi-like witnesses where W is 101. So in principle, actually, when our A is 1, it corresponds to the, it corresponds, not always, but yes, for these 2 points, for theta equals to 0 and pi, our witness corresponds to the kind of generalizations of Choi entanglement witnesses. And this witness is decomposable when B equals to D, that is when theta equals to pi by 2. Now we need to check the optimality, whether this entanglement witness is optimal or not. To check that, of course, not at theta equals to pi by 2, because it is decomposable, it cannot optimal, it cannot be the optimal. So for that, what do we need to find? We need to find a family of this product vectors such that it satisfies these conditions, it satisfies this averaging, as well as it spans the whole space. If it can span the whole space, then we can say that it is the optimal entanglement witness. For that, we introduce a vector psi in this way. So psi can be written in this form. And this alpha k, it is a real phases. And we see that for arbitrary real phases alpha k, this averaging is 0. And then we give a nice propositions which says that the vectors, if you choose in this way, that if psi k can take in this form, then if you choose the product vector in this way, that psi k tensor psi k star, with this real phases nu k, it can span this n square minus n plus 1 dimensional space in tensor n system. Therefore, of course, if we have our n equals to 4, so following these propositions, how many vectors we have? We have 13 linearly independent vectors. So to check the optimality, how many vectors we need? We need 3 more vectors to have the spanning property. Also for the optimality here, clearly for theta equals to, previously I also mentioned that for theta equals to 0 pi, our witnesses is like Choi-like. However, we find that for the Choi-like witnesses, we only have 13 vectors, which is coming from this set. Also, for the 3x3 systems, when I said that for A equals to 1 for W110, there for the Choi witnesses, it is optimal, but it does not have the full spanning property, because for the Choi cases, there also all the linearly independent vectors are coming from this kind of vectors. You cannot get 2 other vectors for the Choi-like scenario. So therefore, for theta equals to 0 and pi, in 4x4, we have only 13 vectors which satisfy the spanning property. So now we need to see what will be happen in this region, between this 0 and pi. So for that, we considered the vectors in this way. So psi 14 will be taken in this, phi 14 will be taken in this, and we need to consider psi 14 tensor phi 14, and this kind of product vectors you need to consider. And you can see that it satisfies this averaging. However, so previously we have 13 vectors, now we have this 16 vectors. However, we see that these 16 vectors, it span only 15 dimensional space in 4 tensor 4. Therefore, and there exists no other linearly independent vectors in this subspace. Of course, how we can say that? We'll show it by subtracting an amount of the projector onto its orthogonal complement, and still we can get the entanglement witness. Therefore, summarizing from class 1, what we have 50 linearly independent vectors in this region 0 to pi, and 13 linearly independent vectors for theta equals to 0 and pi. Now, so for this first class also, at the point theta equals to pi by t, we say that it is decomposable. So it can be decomposable in this way. And here this p is
Anandita?
Yes?
Anandita, your time is up. Please finish it.
Yes, I'll take 2 or 3 minutes. Yes, I'll take 2 or 3 minutes. Yes, thank you. So here P is a rank 1 projector onto the maximally entangled state for tensor 4 with psi 1 can consider in this way. So this at the point pi by 2, this Wi is decomposable. And this A can take in this form. So one thing we need to mention that since Wi at the point pi by 2 is decomposable, then we can subtract this to P, and still we can get this A. This is also an entanglement witness, because and of course this is not an optimal witness, because you can subtract a positive operator to P here. However, we find that this is an orthogonal to 15-dimensional subspace that is spanned by all these vectors coming from the random phase and also the other 3 vectors that I mentioned. Hence, we can try to optimize Wi theta by subtracting a fraction of the projector P. And here comes our first theorem, which says that for the first class, if we can subtract amount of projector P, then this Wi prime theta, it will be an entanglement witness. And the value of lambda should be less equals to 2. Moreover, at lambda equals to 2, this witness is optimal. And also it has a full spanning property. The thing is, after subtracting the projector, you can get, all the 3 or 4 vectors that you can consider from the previous set, but after subtracting the projectors, you will get a set of vectors which satisfy these properties. That is, mod of psi0 is mod of psi2, and mod of psi1 is mod of psi3. And with these conditions, and also the vectors coming from the random phases, one can always span the 14-dimensional spaces. So we have 13 vectors from the random phases, and with these conditions, one can always get here the 14-dimensional spaces. And these additional solutions spans the whole 16-dimensional space, along with these vectors. So now let's come to the class 2. For the class 2, similarly, we can do the parameterization here in this way, and we can denote our entanglement weakness in this form, W2. And remember, of course, here also we have these 13 linearly independent vectors coming from the random phase. And at theta equals to pi, we can get this entanglement weakness, which corresponds to the reduction map. And for the reduction map, you always have the spanning property, as well as it is optimal for the reduction. Also, if you consider the higher dimension for the reduction, you will always get the optimality as well as the spanning property. However, at theta equals to 0, it is not, at theta equals to 0, it is decomposable. And it can be decomposable in this following way. So B can be taken in this form, and this P1 and P2 you can take in this form. And therefore, it is not optimal since it is decomposable. However, we find for the second class, this property, this mod of psi0 equals to psi-t, if one can consider the product vectors in this way, you will have always this form, mod of psi0 equals to psi2 and mod of psi1 equals to mod of psi3. This property actually we get for the first class after subtracting the projectors, but for the class 2 we already have this condition. Therefore, if one have these conditions, so therefore, how many vectors we have? We have 14 vectors which satisfying the spanning property. And after doing the decomposability at theta equals to 0, these projectors P1 and P2 we have also find it is also orthogonal to all the vectors if we can consider psi star tensor psi in this way, it's satisfying these propositions. But we have shown that the weakness for the second class is optimal with only 14 vectors, which satisfying the spanning property.
Anilita, please come to the conclusion.
Yes. I'm already at the end. That is, if you consider any vectors in this way, that is psi1 x psi1 plus y psi2, you cannot subtract any amount of this two of projectors, because it will not be an entanglement weakness for the class 2. So summarizing, for the class 2, we have the optimal entanglement weakness, but we don't have the spanning property. Of course, at theta equals to pi, it is optimal with the spanning property. So yes, this is our take-home messages that we consider here the two one-parameter classes of which are the diagonal in the Bell basis as well as which are the covariant. And of course, these investigated classes, it is the natural extension of a well-studied construction in tensor 3 systems, which can be described by a single parameters. And here are our results. For n equals to 4, we have two classes. For class 1, we have 15 linearly independent vectors, which satisfy the spanning property. We have Choi-like weaknesses, which has only 13 vectors. It is not optimal. Now you can optimize by subtracting a single projector. And this optimized entanglement weakness, it has spanning property, that is because it has 16 vectors. And again, of course, for the Choi-like weakness, we have only 14 vectors. It is optimal, but without spanning property. And for the second class, we have optimal entanglement weakness, and except at the theta equals to 0, which is decomposable. And of course, we don't have the spanning property here, except at the point theta equals to pi. For the reduction, where we have spanning property, as well as it is optimal. And also, because we all know that checking for optimality of a given entanglement weakness, it is a difficult task. And our analysis, it sheds a new light into the structure of optimal entanglement weakness. And it will be also interesting to find a general characterization for arbitrary n. And another interesting problem may be to deal with the issue of extremality, indeed optimality, etc. And this is our reference. This is our paper in Icqif, and it has been done with Philip and Professor Nievko and Professor Derek Kusens. Thank you.
Thanks, Anindita.
Sorry, I
so
took a little bit. Sorry.
We are running out of time, so we will take a quick question. So if there is any.
Hello.
Yes.
Yes, so the optimal witness operator that you have considered for C4 tensor C4.
Yes.
So is that witness is valid for all possible entangled state in C4 tensor C4?
Valid
means can it detect all entangled state in C4 tensor C4?
So, I mean, the way we construct our entanglement witness, it is optimal. And so if it is optimal, so you can say that, yeah, I mean, it can detect all the entanglement witness because optimality says you that.
Okay, the second question is, suppose Alice and Bob, they are sharing a bipartite C4 tensor C4 entangled state. And they are specially separated. So can they witness the entanglement by local measurement and classical by local operations and classical communications? Means Alice performs measurement in his lab and Bob performs measurement in his lab. So and they can do classical communication. So so can they detect entanglement, or they have to come together in a single lab to perform the joint measurement to detect entanglement?
Actually, Arun, we are running out of time, so I think
I'm not getting your point. Maybe we can discuss after this meeting. Yeah.
Okay, thank you.
Shotobrata, can I ask one very quick question to Anindita?
Yes, yes.
Okay.
Hi, Anindita, thank you very much for this nice talk. First of all, I would like to ask that you are considering the maximal commutator subgroup. So is this maximality comes under some partial order relation? Which kind of partial order relation in this case you are considering? Is it coming from some partial, because maximality of the subgroup you are considering?
Actually, I mean, this, just a moment, let me go to the corresponding slide. Yes, here you are talking about, right?
Yes,
yes.
The maximal commutative subgroup. So maximal under certain partial order relation or something that.
No. We are not considering maximal under some partial order relation. Because
in what sense it is maximal then? I may be something I'm understanding incorrectly. It may also happen.
So I mean, maximal subgroup, I mean, if suppose you can consider any group G. So I mean, when you can say it is a maximal subgroup, suppose if you denote your maximal subgroup at H, then a maximal subgroup H of a group G, it is a proper subgroup such that no proper subgroup K contains H that strictly. So in this way,
in that case, the partial order relation is basically the containment of one group to another.
Exactly.
Okay, and the existence is guaranteed by the Zorn's lemma again, the axiom of choice.
Yes, exactly.
Okay. Thank you very much.
Okay. Thanks, Anindita, for your nice talk. So now I would like to over to the organizer if they would like to announce anything before the tea break. So I think this is the time for tea break. Yes.
Yeah, thank you, Professor Shotobrata Adhikari, for chairing the session and all the speakers of this session. So we will take a small tea break and we'll meet again
1640. Okay, thank you all.
Okay. And it was just not in slideshow mode, means otherwise it was. Yeah. Okay, but it should be in proper slideshow mode. This is a bit odd. Let me try this. It would be nicer if it's so. Let's see. Let's try it this way around. Just do the same thing, the way you shared, and click on the slideshow. And that's now it's perfect. Yeah. Okay. Good. Yeah. So this was I did it the wrong way around. Okay. Good. Perfect.
So yeah. So can you hear me?
Yes, a little bit. Yes.
Yeah, very welcome, Martin.
Yeah.
It's a great pleasure. So we just wait for a couple of more minutes. It's about 5 minutes still left.
Sure. Yeah. I just wanted to be sure that I'm really on time. Yeah. Okay. So how many people are in the live audience? I mean, in the room.
In the room, maybe 15 to 20, maybe 30. But online, there are several people, and many more are on YouTube. So they.
Oh, I see.
See the experience. Yeah, they can actually
come
back and again see.
Right. Oh, I see. I see a familiar face actually. Okay. Right. Let me pin this one. I can see.
Yeah, we are just getting out of the pandemic lockdown mode. So hopefully.
Sorry?
We are just getting out of this lockdown mode, the pandemic-induced lockdown mode.
Yeah, I think. I'm well. Okay, let's say at least in the summer, I think we'll be fine. Let's see how it is in autumn.
You are not very confident that Omicron is the last of the.
You never know. I mean, it's anything can happen. So, how is it in your place at the moment?
Oh, well, the third wave of Omicron is nearly over, and variants anywhere in the globe. So we are a little bit on the optimistic side.
Right. Yeah, I mean, here also the Omicron wave is now just over the maximum now. It's starting to decrease, but we'll see how it goes.
Yeah, it's best to keep rather not make
Oh, I see Reinhard. Okay.
94 नहीं, उससे भी ज्यादा है. उसके 84 plus 22 है ना? उसके भी ब्रिज कोर्स है ना? बायोटेक के भी तो ब्रिज कोर्स है. तो फिजिक्स पर जैसे इसके
So right, so let us begin this concluding session of this conference. And over the last 10 days, we have had a number of very fascinating, very highly interesting talks, and in fact, wonderful presentations. So it is a fitting finale to have with us today Professor Martin Plinio, who is the Alexander von Humboldt Professor and Director, Institute of Theoretical Physics and Center for Quantum Biosciences at Ulm University, Germany. Well, Martin Plinio is extremely famous in this subject, and his research interests indeed cover a large span of fields, from quantum technologies using trap times, cavity QED, color centers in diamond, to many aspects of quantum information science and quantum biology. So Martin Plinio is indeed extremely well known for some very fundamental works on entanglement measures, coherence, and non-Markovianity. And indeed, it is no wonder that he has been receiving several highly cited researcher awards during the course of the last many years. And today he will be speaking on applications of resource theories to quantum computation and biomolecular switches. So Martin, you have 50 minutes in all, including questions. And so we welcome you. Over to you, Martin. Thank you.
Okay, well, thank you very much. And thank you for the very generous introduction. And of course, also for the invitation to speak at this meeting. And I do have to apologize to the organizers that I had been so late with providing my title and abstract, but in the end it all worked out. So, okay, so today I'm going to speak about resource theories, and in particular, I would like to, after introducing again some aspects that I will need for resource theory discussion, I would like to drive this a little bit towards applications, namely to provide efficiency bounds on quantum computation, and also with regards to biomolecular switches. And this is work that I've been doing over the years together with students and postdocs. So in particular, I'd like to highlight here Felix Arnefeld, who was a master student and now a PhD student who worked on this, Dario Egloff and Thomas Teurer, who have been working on this and now left the group already, and also Giovanni Spaventa, who does splendid work on the biomolecular switches, and a friend of the group, Maurizio Matera, who is in Argentina, but a visitor to the group on occasions, and Susanna Huelga, who have been collaborating on these topics. Okay, so let's get started, and I really start very simple. I just, resource theories. I mean, so, in physics, in an ideal world, all states and all operations are completely freely available and easy to implement. So, basically in paradise, and that is the basic foundation or the basic formulation of quantum mechanics also, where just all unitaries are basically allowed, all states are freely to prepare and so on. But of course, in the real world, the situation is a little bit different. So we have that some states and some operations are free, or at least very easy to do, while others are really not free at all and very expensive. So as indicated by, bread being a very simple, commonplace staple, while caviar is certainly something that is not every day and it's very difficult to come by. And so in the real world, we place costs on items in the free marketplace, basically. But in quantum mechanics, there's no such thing. So here we have to decide actually really how we determine the costs of objects, of states, of operations. How do we associate a cost to them? Yeah, and so that's really one of the goals, basic motivations for resource theory. There's someone. Okay, so this is the goal of resource theories, and that's definitely the basic motivation. But in the end,
when we have placed costs on objects and on operations and so on, we would like to take this to actually learn something about the efficiency of quantum mechanical processes and placing bounds on really practical schemes. And that will be the final goal of this talk. So, I mean, resource theories as a basic concept, therefore, always works by saying, okay, certain operations in quantum physics or in physics in general are costly and some are free. And this is determined by basically a constraint. So we place a constraint on the set of operations and call one set the free operations and the rest the costly operations or the resourceful operations. So in entanglement theory, this is pretty neat and clear. We talk about local operations and classical communications as being the free operations, the ones that we can easily implement, and the exchange of quantum information across a distance, so non-local operations, those are the costly operations that are resourceful and are not freely available. Okay, so here, we have the free operations and the resourceful operations, and from those flow then the concept of free states and resourceful states, because free operations can take a standard state, let's say the maximally mixed state, and turn it into other quantum states, which are easy to prepare. So in entanglement theory, again, this would be the separable states would be freely and easily prepared, while other states, like maximally entangled states, for example, are not easy to prepare. And so these states, then, the maximally entangled states or the non-separable states, are then the resourceful states, because their preparation requires us to use resourceful operations or costly operations, and therefore we need to put in some extra costly quantum operations. So that's every resource theory is basically formulated in this particular manner. So free operations, resourceful operations, free states, resourceful states. And so that's indicated here also in this as the dark spheres. The free states are usually a small subset, and the resourceful states are then the rest of the quantum world, actually. And of course, then we want to quantify the resourcefulness of states. And for that, we introduce resource measures. So again, in entanglement theory, this would be our typical entanglement measures, the entropy of entanglement, relative entropy of entanglement, logarithmic negativity, all these sort of things. And here we formulate this in a general manner, so that we say, okay, we have a mathematical function on states, so it maps states to a real number. And we would like this function to be such that if the state is free, so can be prepared by free operations, then this measure should be 0. And otherwise it might be non-zero. It should be positive, non-negative all the way around. And also we would like to require that if we are given a state and we apply to it a free operation, then the resulting state will be not more resourceful than the original state. And so therefore, the resource measure should be monotonic under the application of free operations. And that makes perfect sense, because free operations are freely available, so they should not increase the resource content of quantum states. And so then there's the great variety of measures that you can formulate in that, and I can certainly recommend the review by Eric Chitamba and Gilad Gur on this point. And one way of doing this in a fairly general way is to actually take a state, use a distance measure in this state space of states, and determine the distance of that state to the set of free states. And if we find the minimum distance, then we could try and call this the resourcefulness of the state, rho. And whether this really satisfies these conditions down here will very much depend on this distance measure here. And so one has to be, of course, very careful when one chooses this. Not every distance measure in such a construction will actually yield a valid resource measure that satisfies monotonicity. Okay, and so that's the basic setup. And so then once we have started to set this up, we want to, of course, find ways to decide which states are resourceful. We would like to learn how we can take resourceful states and how we can manipulate them. That means how we can transform one resourceful state into another. And then we also we want to see how we basically can implement quantum operations and maybe quantum algorithms and so on the basis of free operations and a supply of resourceful states. And we want to do this also with high efficiency. So we want to really find out how we can do this very effectively. And we also often, from an experimentalist point of view, we would like to actually find ways to efficiently test whether a quantum state or an apparatus produces a quantum state that is resourceful and how resourceful it is. So this may, in future, when we have really fully fledged quantum technologies, this might be of interest because you may want to go to a shop and buy sort of quantum resources, or a supplier provides you with quantum resources, and you would like to check very easily, effectively, how resourceful such a quantum state is. In some cases, this will be very easy, but in the case of entanglement, especially many-body entanglement, this may, for example, be a very complicated thing. So these are sort of the traditional viewpoints that one takes on what central goals of resource theory are. But and this is great. I mean, because it really gives us a conceptual idea of what resources are, how we can put them all into a general framework, so that we can find actual commonalities in the laws that govern them, so that we don't have to reprove everything for every new resource that we want to define. And that's great. And indeed, this approach works for a wide range of resources: entanglement, coherence, non-locality, Gaussianity, magic, all sorts of these quantities. And in each of these resource theories, people try and answer questions that I put here on this slide. But I think it's also important that on the one hand, we want to do this, fundamental considerations here and about how to manipulate resources and so on. But in the end, certainly when I present these sort of things to a more experimental physics-minded audience, I'm often asked, so what's the point? So is this only merely mathematics and quantum information that you do for your pleasure, or is this also useful for us experimentalists? And I think this is certainly a valid question. I mean, it's very valuable to do these things in theory to really understand deeply these concepts. But it is also equally valid to ask, okay, where can we make use of all these structures that we are developing here? Yeah. And one statement in this respect is certainly that if we have such a resource theory for a particular resource, then it gives us resource quantifiers. And because we know that these resource quantifiers cannot increase under free operations, this will allow us to place certain bounds on experimental processes. So what can we achieve and with what efficiency we can achieve it under the presence of free operations? And if we cannot do a process under free operations, how many resources we may need to do that? And that can be very relevant, for example, in linear optics, quantum operations, quantum computation, for example, where we can ask questions as to how many resources are needed to do, for example, quantum computation using linear optics and some nonlinear elements. And that in many ways is a very timely question. And it's very And I think it is indeed possible to do this with some of these resource theories here. And so it is in this spirit now that I would like to continue. And I would like to see, I want to go a little bit more real world here. And so on the one hand, I want to see now, I want to explore how I can use the resource theory of coherence to place bounds on the efficiency of quantum algorithms. And then I want to use the concepts of quantum thermodynamics, which is also one of these resource theories here, to place bounds on the efficiency of biomolecular switches that we switch by actually incident photons. And so really, I want to basically go to these more practical settings and place bounds on general bounds on those. So that's really now the goal that I have. So, and in the process, I will make use of a lot of the results that have been obtained in the study, in the fundamental study of resource theories. Okay, and so let's get started with the first part here, and that is the quantum coherence as a resource in quantum computation. And it's actually really still a kind of an unsolved question to really nail down what is the specific resource that drives quantum computational advantage. So it means advantage over classical computation. And so that's kind of the question that I would like to explore here a little bit. And there are, of course, many results already in this direction. A particularly nice one concerns entanglement, because it's often sort of stated that entanglement sort of drives quantum computational advantage. And indeed, there's a result by Richard Josa and Noah Linden from about 20 years ago now, that loosely summarized states that for pure state quantum computation, we need an unbounded amount of multipartite entanglement that is growing basically linearly with the size of the quantum processor. So if your quantum processor has L qubits, and if you want to basically have efficient quantum computation, what you really need is that the entanglement, that all parts of the quantum processor are somehow entangled with each other. So it's not enough that the number of components in the quantum processor that are entangled are fixed size when you grow the size of the quantum processor. Because if that was the case, then there are classical simulation algorithms. Okay, so that sort of suggests that entanglement seems to be an important resource in pure state quantum computation. But on the other hand, there are other results that show that even if you have this unbounded entanglement, it is not necessarily, it is not sufficient for superior performance of a quantum processor. So in fact, if you, for example, limit the action of the quantum operations that you can do to elements of the Clifford group, so like Hadamard transformations, for example, and controlled knots and controlled phase gates and a few more of those gates, then actually we know from the Gottesman-Nil theorem that this evolution can be modeled efficiently with polynomial effort in the number of qubits using the stabilizer formalism, even though the system actually may exhibit a very large amount of entanglement, actually a large amount of entanglement exactly in the sense of the Josen and Linden result. Yeah, so all components, the entanglement will be all pervading amongst all components of the quantum computer. So therefore, it's clearly not sufficient. And so then it's not so clear whether entanglement is really the key resource or whether it just happens to be there and maybe some other quantity is the key resource of quantum information processing. And another argument in that direction is also, or another challenge here, is that this result from Joseph and Linden really refers to pure state quantum computation. And in fact, in their paper, they very specifically point out at the end that it is conceivable that we have a completely non-entangled quantum processor that operates on mixed states and therefore has very complicated correlations in them, and that these may still be hard to simulate. It's not clear, but so certainly in the mixed state case, the connection between entanglement and quantum computational advantage is much less clear. Okay, so what I would like to now show you is a result that we have obtained recently. It's not published yet, but it hopefully will be placed on the archive in the next few days. That we would like to draw a connection between coherence content of a system and the computational efficiency at the example of Shor's algorithm. So this will not be a completely general result for all quantum algorithms, but we analyze this particular question for Shor's algorithm in particular. And actually, more specifically, what we will be able to do is we will be able to bound, upper and lower bound, the success probability of Shor's algorithm in terms of coherence measures. And so that will then suggest that it's really a quantitative bound. And this suggests that coherence really plays an important role as a resource in quantum computation. Okay, so let's get going here. So let's briefly talk about coherence and the elements that I need for this here. So resource theory of coherence is a little bit for some people a little bit almost trivially sounding, because nowadays we have such easy access to coherence, but nevertheless, in the old days of quantum mechanics, this was not, or before quantum mechanics, this was not really the case. So nowadays we have lasers, and so we can take atoms and we can make a coherent single qubit rotation without any problem. I mean, this is really very, very standard. You can do this with extremely high fidelity. I mean, in some realizations of experiments, the gate fidelity for single qubit operations can reach like an error rate of 10 to the minus 6. So it's really extremely high fidelity. So we can do this. But, you know, in the past, before the advent of the laser, this was actually really not easy at all. It was not easy to prepare an atom, let's say in the ground state, and then transfer it in a controlled manner to a coherent superposition of ground and excited state, for example, because we only had incoherent light sources initially. And so therefore, it is perfectly reasonable to ask, what advantage do coherent light sources give us over incoherent light sources? And in a world where we have only incoherent sources, then the presence of coherent superpositions present us with a resource that allow us to do general coherent operations using only incoherent light and coherent states that we buy in a shop. Yeah? And so that's the motivation for formulating the resource theory of coherence. And so let's say some basic definitions. So, well, we have to fix a basis, as we always have to do. So we take an orthonormal basis and we define coherence relative to that basis. And often this basis will be just given to us naturally in an atom, for example. It will just be the energy eigenstates of the Hamiltonian of that system. Okay. And then we have a constraint, namely that we cannot easily prepare a coherent superposition of basis states. Okay. And that means that the free states are simply the statistical mixtures of the basis states, and all other states are resourceful because they really require some extra effort to prepare them. Okay. And here I would like to now briefly make a remark that is maybe clear to many people, but I sometimes do get this comment, an objection to this theory that it is very, very different from entanglement theory, namely that coherence theory, the theory of coherence is a basis-dependent concept. And so it's meaningless, as we can change the value of coherence by changing the basis. And that's an objection that I frequently receive. And so I would like to briefly comment on that. So it is true that if I take basis states in the incoherent basis, and I make a basis rotation, that means a coherent operation that moves this basis to, let's say, the basis that I'm writing here, which is a coherent superposition of spin up and spin down state in this case, then of course, in these new basis states are resourceful. That's fair enough. That's absolutely correctly true. But exactly the same statement, or the analogous statement, holds true in entanglement theory. Because in entanglement theory, I have the basis states, in this case, local states. And if I apply an entangling operation, so that means a unitary that maps product states to entangled states, I can also go to a new basis, and this new basis will actually be composed of entangled states, and these are resourceful states. And so entanglement theory, therefore, is basis dependent in just the same way as coherence theory is basis dependent. Namely, if I make a basis change that requires me to use resourceful operations to implement it, then of course the new basis will have will contain resourceful states. So really, I am in every resource theory, I'm restricted to basis changes that can be implemented free of any use of resource. So that is true in resource theory of coherence, and it is equally true in the resource theory of entanglement. So both are basis dependent in the sense, but for as long as the basis change does not require resources, then the resource character of states is not changed. So this is a brief remark that I wanted to make because I get this frequently as a question or comment. So, okay, so now I want to talk about quantum computation. And therefore, I mean, this is clearly a dynamical process. And so therefore, I would like to go away from this concept of just the resource theory of quantum states. And I would like to formulate resource theories also for quantum operations. Yeah. And I could do this in a straightforward way by just saying, okay, I take resource free, I take quantum states, I take operations, and I just check how much resource they can add to my quantum state. That is a perfectly acceptable way, but I think it is not the most fruitful way for what we are going to do here in the following. So I would really like to formulate the theory of let's say, resourcefulness of operations and particular coherence of operations from the bottom up. And so therefore, I'd like to briefly remind you how we are doing this resource theory for states. So we define the free operations, and that gives us the lower level, at the lower level, the free states and the resource states. Free operations generate free states, the resourceful operations generate resourceful states. And in that way, we have built up the resource theory of states. Yeah, so at this level. So now I can say, okay, if I want to have a resource theory of operations, I could actually do this in a very similar manner, but now defining basically operations as the bottom layer and establish a structure above that, namely super operations. That means super operations would map one quantum operation to another. And then I can, again, establish the concept of free super operators and non-free super operators. And that can be used to define free operations and resourceful operations. So, and that's exactly what we are going to do. So, I mean, that we had already. So now we have the lower level is the quantum operations, and the higher level is now super operations. And so what are actually now free super operations? Well, these will be the parallel and sequential concatenations of operations with free operations. So we can allow ourselves to do the following. So we have, let's say, an operation theta, And now I define a super operator on this by basically concatenating the operation theta with another operation phi. So I just execute them sequentially. And clearly, if phi is free, then I would call this a free super operation. And also, I should be able to execute operations in parallel. So if I give an operation theta, I can introduce another wire on which I execute an operation phi. And if this operation phi is free, then this super operation would also be denoted as free. And of course, equally, I can also then start to make concatenations of this. And I can also, in some resource theories, I can freely interchange wires and I can build up networks. And then certainly in the resource theory of coherence, the interchange of two wires, that means the interchange of two states is an incoherent operation. It will also be an incoherent super operation and therefore would also fall into this class. So therefore we can define the class of free super operators. We can imply the class of free non-free super operators and build up now in that manner, again, a completely analogous framework of quantum, the resourcefulness or resource theory of quantum operations. And so that's what we have executed in this work here. Mainly Dario Icqif and Thomas Theurer did the hard work on this and really set up this framework correctly and carefully, and also identified and defined proper measures of resourcefulness that do not simply take recourse on the lower level of a resource theory of states. And that will become useful for us. And so concepts that are useful in this also are, well, again, fixed bases in which we define everything in terms of coherence. And then an important concept that was introduced by Siveng Wei and Seth Lloyd is the concept of resource destroying map. And in the case of coherence, that is the completely dephasing operation. So that means basically you take measurements in the computational basis, or you project into the computational basis, and you mix the outcomes. And that certainly takes any resourceful state and destroys all the resource in it and turns it into a resource-free state. And that is a useful concept. And then using this concept, we can actually now study particular operations, and namely there will be operations that cannot measure coherence. And by that, I mean they cannot really make use of coherence. So whether in the input coherence is present or not makes no difference to the subsequent output of this operation. And that can be encapsulated mathematically by this equation. So it doesn't make any difference whether we first apply a dephasing operation or not. Yeah. And so that is an operation. These would be operations that we call measurement incoherent that cannot make use of coherences. And also, there are also operations that might not be able to create coherences. They might be able to make use of them, but they may not be able to create them from nothing. And that is expressed in terms of this set of equations. So it's basically on the left-hand side, it depends whether the resource destroying map is on the left-hand side or the right-hand side. Yeah. So these are two concepts, and I mean, they have also operational meaning, because one of these measures how well we can possibly use coherence that is provided, and the other one is how well it can test for the presence of coherence. Okay, and of course an operation is completely oblivious to any kind of coherence if it neither can create it nor can measure it. Okay, so now this can all be placed into a framework, and we can define measures of coherence of operations, and we will require the usual thing if a measure of coherence of operations is zero. It should be zero exactly if the operation is incoherent. Of course, free superoperations should not increase the information, the coherence content of operations, and often for convenience, we require that the measures are convex. And so indeed, so now one can question which measures would satisfy these sort of things. And for our purposes now, it will be useful that these measures, there will be two types of measures that we will use. So we can always, on the level of states, we can define the robustness of coherence. That means how much, so given a state rho, how much of a different quantum state do we need to mix in to make sure that the resulting state is incoherent? And we want to find the minimal amount of quantum state that we have to mix in to make the state incoherent. And if for this measure, so this is also an analog of this exists in entanglement theory and also in other resource theories, of course. So then we can define the coherence creation capacity of a quantum operation or a channel. So in this case, meaning take a state tau that is incoherent, apply the quantum operation to it, and measure the coherence content of the resulting state. And now maximize this over all incoherent states. And so for this measure, we can show that this is actually a suitable measure for the coherence content of a quantum operation. So we prove monotonicity and all the properties that that we need out there. So this is also proven actually in the work down here. And the second quantity is the capacity of a channel to detect coherence. So that means we compare this. We take a channel lambda, and we compare it to detection incoherent channels phi. Yeah. We let both of them act on the input state sigma, and then we apply the resource destroying map, and then we take the trace norm difference between the two quantities. And so this quantifies the extent to which our operation is actually different from a detection incoherent map. Okay, and so this is highly non-trivial to show that this is actually a suitable measure of coherence of operations. But in fact, this was possible. I mean, we have actually been able to prove this. Okay, so these are the two quantities that I will now need to formulate the actual result regarding Shor's algorithm. And so in Shor's algorithm, you know that the primary function of that is to factorize numbers. And that is actually done by reducing the problem of Shor's algorithm to solving the discrete logarithm problem. And that was developed by Peter Shor. Original formulation of this algorithm, and it was a parallel algorithm in the sense that we had a lot of inputs and we placed them in a superposition using a Hadamard gate, and then we applied a complicated controlled unitary operation on ancillary qubits. Then we did a Fourier transform, and then we took a discrete Fourier transform, and then we took measurements on the output, and then we take this output to insert it into a classical algorithm that runs in polynomial time, and that would then deliver us the factors. So I cannot go into really that terribly much detail here because that's really beyond the point, but that's the basic makeup of this algorithm. And so in that form, it's not quite useful. It's not quite the simplest form in which we can use it. And so what we did, actually, we used an old result from 20 years ago or so that we had, that of course, it is possible to take this parallel version and turn it into a sequential version. That means we take the first qubit here, we execute, we place it in the coherent superposition, we execute a controlled operation on the ancillary qubits. We pass these ancillary qubits on, but we measure the control qubit. Then we replace it by a new qubit in the standard state, place it in superposition, execute another unitary, controlled unitary, make measurements again. And we do this several times, basically. And it can be proven that this is completely equivalent. These two formulations of the algorithm are the same. Okay. But here it becomes a little bit nicer to actually speak about the resource that we put in every step. We put in a coherent state with certain amount of coherence. We execute a more simple operation, then we take measurements in the uncoherent basis. And so this will allow us now to formulate the theorem better. And also what we are now going to do is, so maybe I go back. So here we basically put in a quantum state, a coherence state with a certain amount of coherence. So we formulate this a little bit more generally. So we put in here a state. So we will have an operation that creates the input state of the control qubit. And so this might require some coherent operation. Yeah, so coherent preparation of a state. And we allow ourselves also to surround this by free super operations, so that manipulate this operation further, because it is important to realize that the input of the Shor's algorithm, even if it has coherence, if it's the wrong type of coherence, it may not actually be helpful in the execution of the particular form of the Shor's algorithm. And so therefore, we should allow ourselves a free operation that takes a coherence that is prepared here and puts it into the right form for the specific formulation of the algorithm. And so therefore, we do this here. So we have an input state, control qubit that creates a certain amount of coherence and some free post-processing. And equally, we do in the end a detection step. So we detect the coherence in the output of the control qubit. And again, this is of course a detection operation. So this is a quantum operation, and we allow ourselves to do free super operations surrounding that. So those are our operations. So here we create coherence, here we detect coherence. And now we would like to see, can we formulate a quantitative bound on the efficiency of Shor's algorithm in terms of our ability to create and detect coherence. And indeed, that's exactly what we can formulate as a theorem. So the proof is really lengthy. So, I mean, this is, I will not really show you how this can be done. But the interesting thing here is, in particular, this part. So there will be one part here. So that depends on number theoretic properties of the specific problem, namely the input size, and also the order of the function that is being determined here, which is directly related to the factors that we want to determine. And that's purely number theoretical quantities. And then here there's a factor which scales exponentially in the problem size. And it depends here at the input on the ability of the channel, the input channel, to create coherence, and on our ability to detect coherence. So in terms of these coherence generation and detection measures that I had formulated before, and which we have shown that they're really proper measures of coherence of operations. And we can equally form a lower bound on the success probability of the algorithm. That means that the probability that with which it yields the correct factors, which is again a function which is depends on the problem formulation and again our ability to detect and destroy, create and detect coherence. And so this is a nice result in the sense that we can really relate coherence measures of operations with the performance of Shor's algorithm. And I would like to spend a small word about these prefactors, because you might be dissatisfied with the presence of these factors here. Those are actually also factors that appear in the purely classical regime. That means if I would execute a classical version of Shor's algorithm, only classical operations, incoherent operations, so that means classical computation, I can also up and lower bound the efficiency of the algorithm And exactly these prefactors actually appear in those bounds. So what is added by resource theory is an additional factor that tells us how much we are deviating from basically the classical performance by placing these extra factors here. And you can see that if these quantities, if C and M are equal to 1, then this bracket here is equal to 1, and we have the maximum possible performance. And in particular, it's not exponentially decreasing in the problem size. So therefore, we actually have a polynomial algorithm. But as soon as we lose this perfect ability to create coherence, then we start to actually lose efficiency, and the algorithm becomes inefficient, and we can make this quantitative. And that's kind of one result that we have here. And so we formulate this in coherence creation and the detection capacity. Okay. So of course, one has to say here, this is not for general algorithms. We only managed this so far to formulate something like this for the specific algorithm of Shor's algorithm. And we did it for the sequential version, but it actually can be generalized to the parallel version as well. So that's fine in that sense. For Shor's algorithms, it's fairly general, but of course it does not apply necessarily to other algorithms. We would like to generalize this actually to more wider classes of algorithms, but that's work for the future. One can also say, well, where's the entanglement gone here? Well, the entanglement actually is hidden to some extent because it is actually hidden in the execution of this operation here. So this is an incoherent operation actually. But of course, if I want to implement it in as a bunch, as basically a sequence of quantum gates, then we will start to see that if they're really generated by a Hamiltonian, then coherence will actually emerge, and also entanglement will emerge. And so the entanglement content has to some extent been hidden in here. There's some entanglement that will be generated between the control qubit and these external qubits here. That, of course, is in our analysis, and it's very well known that if we have coherence and incoherent operations, we can actually generate entanglement from that. Okay, and so what is maybe also a little bit different to perhaps to the result from Linden and Josa here is that we go beyond the statement, oh, we need somehow some amount, a certain amount of entanglement, but to enable, let's say, quantum computation, but we do not, they did not really quantify it particularly. Yeah, so it was more a general, rather non-quantitative, qualitative statement. So here we actually really took these questions and we turned them into a quantitative statement regarding the coherence content versus success probability of the algorithm. Okay, so that's the first part, and the last few minutes I want to briefly mention also results that we have obtained in terms of the resource theory of thermodynamics. And we studied here, motivated by really nice work by Nicole Younger-Halpern and David Limmer, the performance of photoswitches. So these are molecules that when a photon is absorbed, they actually change their configuration. So they go from this form here, which is called the transform, to the cis form. So they really bend along a particular bond. And that actually underlies our sense of vision. So it's an important ingredient in vision. And obviously it's a photon mediated process. And it is actually not so well understood how efficient such a process can be. Of course, we can always try and make measurements, but this is a very complex system in the end, because the system actually is a molecule which is in interaction with an environment which is composed of all the vibrational modes of the molecule, and maybe also protein environments surrounding it. And it's very difficult to simulate accurately such large environments. And in fact, we don't even know the environments to very high precision because they are very difficult to characterize experimentally. And so therefore, it is a valid question to ask, what are fundamental bounds on our on the efficiency with which an incident photon can actually generate this trans to cis transformation. Yeah. And I do not want to study this on the basis of, let's say, using master equations or a very specific model of a particular environment, because then I will always be reduced to the question of, okay, do I make approximations that are not, that are maybe oversimplifying, or do I actually do, or I need to actually run an optimization over all possible environments that there might be. And so this is an interesting question that Nicole and David started a few years ago. And we were interested in a particular question, namely, whether it makes a difference whether the environment is Markovian or non-Markovian. And to that effect, of course, we have to simplify the situation a little bit. We have to simplify the internal level structure of our system. We will actually really only talk about the initial states, which might be the state 0, the photoexcited states, or the final product state. We do not care what happens in between. The Hamiltonian in between can be as complicated as you like. The environment can interact in any way, complicated way you like, for as long as we satisfy one constraint, namely that initially, before photoexcitation, the switch and the environment are in a product state. And that is actually very well satisfied in these experiments. And the second constraint is that the unitary, the joint unitary operation between the switch and the entire rest of the world is such that it commutes with the total Hamiltonian of system and environment. And that's a fundamental ingredient in the resource theory of thermodynamics. And so that is an assumption that we are putting in. And it is not entirely clear how well this is really satisfied in this particular setting here, because we, of course, also have an interaction Hamiltonian and we have a sudden excitation here. And so this is a point we have to think about. But at least we have very well defined now conditions. These are the only constraints that we are taking on the accessible operations. And now we want to formulate the difference between Markovian operations and non-Markovian operations. And so this is, we do this simply by the global operation that is implemented by going from the initial state to the final state. This happens in a fixed amount of time. And we call our operations so embeddable, so time-independent Markovian. If there is a fixed generator for a dynamics that is of Lindblad form and generates this transformation from initial to final state, and it's such that it is a thermal operation at the end of the time interval. So that's the simpler form. And then the time dependent, let's say, Markovian operations would be such that I can actually split my total evolution into small pieces, and each small piece individually is Markovian in the above sense. But in each step, we can actually change the generator and make it time dependent. Okay, so these would be our operations. These would be our two definitions. The upper one is more restrictive than the lower one. And we want to study how this affects the efficiency. And indeed, we can now solve this analytically. I mean, this is mainly thanks to great work by Giovanni Spaventa, who's PhD here in the group. And he really managed to make analytical solutions or mathematical solutions of these questions. And we can actually here now see on the basis completely generally, irrespective of the detailed structure of this environment, we can actually show that the yield or the, let's say, the efficiency of the switch, if I may place no bounds, no Markovianity constraint on our operation, on our environment, then we get this as the upper bound on the efficiency. If I say I want to have time-dependent Markovian operations, then I actually see that I see a real gap in the performance of the switch. And the performance becomes even worse if I demand that the operations are embeddable time thermal operations. That means they are generated by a time-independent generator. And if I would just look at the thermal equilibrium value, I would be down here. And so this is attractive for us because in this field of quantum effects in biological systems, I mean, there's often the idea that the environment can assist processes, and in particular that non-Markovian environments can be helpful in enhancing the efficiency of processes. And these statements are typically by, here we have some Markovian operation, here we have non-Markovian operations with the non-Markovian environments, and we see one performs better than the other. Therefore, we see that, okay, non-Markovianity seems to help. But has never really been any proof that the optimal Markovian operation and the optimal non-Markovian operations really are different in efficiency. And this is the first example, and that was made possible basically by studying the resource theory of thermal operations in this particular setting. Okay, and with that, time is out. Actually, I overran a little bit, as you can see now. So with that, I would like to close and thank the team. This is a slightly older photo. The team is a little bit closer. And in fact, we are looking for people to join the group. And here's the funders that support all the work. Thank you.
Well, thank you very much for the excellent presentation. And this is now open for questions.
Sir, can I ask?
Yeah, okay, Nirman, please go ahead. Yeah, we'll come to the chat box. There is a long question, but first Nirman wants to ask. Okay, please go ahead.
Professor Plenio, thank you for this very interesting talk. So I have a couple of questions. When you told about that hierarchy of those operations, these high-level operations and the low-level operations. So in the low-level operations, we have the quantum operation itself. And in the high level, we have a serial or a parallel concatenation of these operations. So why are we making this hierarchy? Is it because that the higher level operations are creating more resource? Is there some kind of a quantification of that kind?
I think it's mainly so. You see, there are specific ways in which I could. Okay, let me go back. So if I want to, let's say, if I formulate, let's say here, so normally, if I formulate the resource theory of quantum states, then I make such a structure here. And now there are two ways in which I can go and define a resource theory of operations. So I can either say, take recourse to states and look at how operations act on states and then define the resource content of operations by simply seeing how much resource they can generate, or how much resource I need to implement the operations. But these are very specific schemes. Yeah? And what we want to do here by taking both of these parts to the next higher level, namely taking the states, taking the operations as the lower level and then the super operators as the higher level, we wanted to formulate general statements about what are good quantifiers of resourcefulness of operations. How can we set up a clear, consistent framework that is not merely restricted to specific constructions, but makes general statements about this. So that was really the point behind that. Yeah. Yeah.
Okay. And this, I have this.
Yeah. So now Apurva would like to ask something. Apurva, can you unmute yourself and go ahead?
Yes. You pointed out that superposition and entanglement, coherence in general, is a basis-dependent quantity. So you have to define what are the freely available bases. Now, in general, this choice of freely available basis, or what is also known as
preferred basis that depends on the environment of the system. If you take a thermal environment, then they are defined as eigenstates of energy, for example. So in that sense, this resource theory of what is the environment available to the system also. Is that correct?
Well, I mean, indeed, we would have to, so in all these cases, we will have to fix a basis, and this often will be done in the coherence theory case. It will often be done by saying, okay, here is a natural Hamiltonian of the system, and we take the eigenstates of that Hamiltonian. Yeah. But of course, we don't strictly need to. We need to use it. We don't necessarily need to use a specific Hamiltonian. It will also be possible that we say, okay, here is our set of basis states. Any Hamiltonian that is diagonal in that basis is a free. Is free because it generates a free dynamics. Yeah. And then it is a little bit more general than referring to a specific environment. Okay, and this is a little bit like an entanglement theory as well. I mean, there I could also say I take a Hamiltonian that happens to have an eigenbasis that is made up of product states, and that defines the basis that we want to use. Or I can say, well, okay, I mean, any basis, I fix a basis of product states, and then any Hamiltonian or any, let's say, operation that is diagonal in that basis is local. Yeah. But does that answer your question?
Well, you said that the Hamiltonian plays a role. It is correct if you are assuming a thermal environment where you can describe things by the Boltzmann factor. But you can imagine that the environment is not thermal. And then the function may not be Hamiltonian. It may be something else which dictates the efficiency of the dynamics.
Well, but I mean, now you are talking about, I mean, I would say you're talking more about now questions of thermodynamics, of system and interacting with an environment here. But here, I mean, certainly in the resource theory of operations, in the resource theory of coherence, I would just talk about a physical system. Yeah. And in that physical system, I choose a basis. Now you can argue, okay, the environment might actually naturally drive already this basis into some coherent superposition or something like that, and even in thermal equilibrium. Well, that just means that the operations that you are applying from the outside, so the environment, is already resourceful in the sense of coherence. That's perfectly fine. Yeah, but we can now, therefore, we can then quantify what is the resource content in terms of coherence of this environment, and that's per se a useful thing.
So we move on to the next questioner, that is Stanislav Filatov. Could you please unmute yourself and state it?
Thank you for the talk. I just wanted to ask about this fixing of initial state. Would it be possible to scan through all of the possible states and using your like theory, and then finding...
Sorry. Can you repeat this? There was something with my headphone. Sorry.
Yes, I just wanted to ask, is it possible, you said of fixing initial state, I'm wondering about, is it possible to scan through multiple possible fixtures of the states in order to find the most resourceful computation basis for a given circuit or computation?
Indeed, I mean, absolutely. I mean, we can also here find out what is the most resourceful state for Shor's algorithm. I mean, and that is, I mean, that's basically what he originally had in there. So you take the qubit in the ground state, you apply a Hadamard transformation, and you map it to the state 0+1. And that in this formulation is the most resourceful state. And in fact, it happens to be also the most coherent qubit state that there is. Because from that state, if I give you this state, you can produce all other qubit states by incoherent operations.
Thank you.
Okay, so now we come to the question by Ranjit. Long question on the chat box. Ranjit, could you please unmute yourself and read out your question? Might be easier.
Hello.
Mm-hmm.
So my question is like there was a long-standing debate if optical coherence is a physical fact or a convenient mathematical fiction, and there were many papers and a couple of papers by Speckens et al. And I think Paul Bush were received well, and their resolution was like, they basically highlight the fact that state assignment and what we call as observables, what we call as states, is kind of relative. So I wonder how much of that debate could reflect here for resource theory of coherence, the kind of systems we talk about here.
So okay, I have to say that I'm now not super familiar with the contents of this paper. I mean, I know that they exist and so on. What I would say is that this refers to, again, to some extent, I think, to this question of which basis to choose. So of course, it is true that coherence in one basis, or a state that looks coherent with respect to one basis, might look incoherent with respect to a different basis. So certainly in a quantum optical experiment, I will always be able to choose a basis in which a coherent state will look incoherent to me. So it will be simply a member of an incoherent basis. What I would say, however, is that this will be much harder to maintain if we think about operations and let's say coherent operations, because if I change bases in the process, then it becomes really rather artificial that that in each step I take a different basis sets that are connected by with respect to each other by a coherent operation. So I think in that respect, it's also maybe useful to think about resource theory or coherence of operations rather than merely states, because indeed for quantum states you could always decide, okay, for some reason this is my preferred basis, and in that basis this particular state is not coherent. But if I have a dynamically changing basis, this would be different.
Okay, so if there are no more questions, then let me ask a rather pedestrian question. So this refers to one of your comments just before your last section on biomolecular switches. So when you were talking about the operational research theory of coherence of operations, you made a comment saying that entanglement is, after all, it's kind of hidden here, and or any entanglement can be seen as a operational creation of coherence. So if I carry the same logic forward, then all resource theories of entanglement, for example, all tasks which use entanglement, for example, dense coding, can be recast into some kind of task involving coherence. I mean, could we set then limits for those tasks also as well?
Yes.
Using your formalism?
In principle, yes, yeah, indeed. I mean, so so you could always say, there is someone that provides me a maximally entangled state. That's and I count everything in terms of those resources. Or I can say I'm limited to incoherent operations, and I'm provided with coherence, which allows me to generate this maximally entangled state for me. So indeed, so if we say we are restricted to incoherent operations, then I can count all the protocols where I count the efficiency in terms of the number of maximally entangled states. I can equally count the efficiency in, or the resource requirements in terms of the provision, in that case, of maximally coherent states. Absolutely. And then the question is, to some extent, well, what is the practically more relevant question? So maybe indeed your experiment is restricted to incoherent operations, then really you should
you should talk about coherence that is provided to you. But maybe you can have at your disposal certain types of incoherent operations and an entanglement, but it's hard for you to generate entanglement. And then it's maybe a good idea to count this in terms of the number of maximally entangled states that you need to provide. So it's a little bit the question of what is really the costly part in the practical setting, the part that then you want to quantify. But basically, you're completely right. I can quantify it either in terms of entanglement or in terms of coherence. And coherence is kind of a little bit more fundamental in a sense.
Well, thanks a lot. And let us again formally thank Professor Martin Plinio for his wonderful lecture. And thank you very much for sparing your time and giving the last keynote lecture of the conference. So thanks.
Thank you.
Again.
Thank you.
So good afternoon and good evening to all. So this concludes the academic part of the conference. And before I hand it over to the conveners for their last vote of thanks, I would like to invite the audience and throw it open if any one of you has any comments to make or any suggestions to provide. Could you please either unmute yourself or if you want to make a comment. So it is open to the audience now.
Thank you very much. It was a great conference. I had a very great time. Thank you very much. Really very, very nice. Only good words I can say about this conference. I hope the videos will be available still after some time. My only suggestion would be to add maybe description under the video who is talking at which time. Yeah, that's it. For future, perhaps forum where after the discussion we could discuss something more would be also nice. But it was a very, very amazing conference. Thank you very much.
Yeah, thanks a lot. We've noted your suggestion, and that is what the others have also commented. So some classifications of the videos on YouTube is what is required. Yeah, thank you.
Archunda, Professor Warner.
Yeah. So now Shopon wants to take over. So maybe Reinhard can make his comment and then Shopon can take over. Yes. So I think it was great. Thanks to the organizers. This was really a fantastic event. We haven't had many big conferences in the recent times. So this was really very well. I mean, there were many excellent people there and excellent talks. I had a bit of a problem to listen to the contributed talks in the early morning because for me it's really early morning, so I didn't hear too many of those. But still, it was a fantastic event and some really inspiring talks. So great thanks from me. I greatly enjoyed this one, and I hope there will be more events like that. Thank you so much. And now, thanks a lot. Thank you so much again for participating in this conference throughout. And now I hand it over to Dr. Shopon Rana, one of the three conveners, to take this session further forward. Yeah.
Hello, everyone. I'm Shopon Rana, one of the conveners. Welcome, everyone, to the valedictory session. What an amazing 10 days it has been with so many excellent talks from many corners of the world. Well, we will all agree that quantum information has been so much diversified into several topics that it is impossible to cover all aspects of it, or more importantly, to include all the leading experts into a single conference. So, ladies and gentlemen, I take great pride in sharing with you that within our limited scope, we have been able to cover most of the interesting topics and had such an impressive list of speakers. We had with us some of the legendary figures of quantum information,
as well as the pioneering experts from topics like quantum entanglement theory, quantum foundations and non-locality, quantum thermodynamics, quantum communications, or rather nowadays it's called quantum Shannon theory, quantum cryptography, quantum metrology and sensing, etc., etc. So we also had very insightful talks about near-term quantum technologies and various experimental implementations. Thank you all, the speakers, the session chairs, and the participants to make this conference such a successful event. Now, organizing this conference, and I believe any such event, took lots of efforts. It is now time for us, the conveners, to thank all who have provided us help and support. I would like to start with our director, Madam Professor Sanghamitra Bandyopadhyay, for hosting this event. She is the chairperson of the organizing committee, and I'm sure you could remember she had kindly delivered the inaugural address of the conference. Next, I would like to thank our organizing professors for sharing with us their experience and guiding us throughout the whole event. Thank you, Professor Archanes Mojumdar, Professor Priti Parasar, Professor Guru Prasad Gaur, Professor Devashish Sarkar, and Professor Somsubra Bandyopadhyay. Ladies and gentlemen, may we have a round of applause for the professors? We also gratefully acknowledge financial support from the head of our unit, Professor Supratik Pal, and the professor in charge of our division, Professor Priti Parasar. Being an organizer herself and also the professor in charge, I would like to request Professor Parasar to say a few words. Madam.
Thank you. Hello, everyone. Hope you had an enjoyable conference. It's been an exhilarating experience for me to be exposed to new ideas by such renowned experts in the field. The deliberations have been very exciting and intellectually stimulating, and surely they're going to bolster our academic pursuits further. I would like to accord my deep appreciation to all the speakers for making valuable presentations on their research work. I earnestly hope that the COVID situation improves and we are able to organize such events in the physical mode. I must say that the conveners of the conference, Indrani, Ramiz, and Chopin, they have done a fantastic job taking care of every minute detail. A big hand to the three musketeers. Finally, on behalf of the ISI administration and the organizers, I would like to thank everyone for making this conference a grand success. Thank you.
Oh, thank you, madam, for your kind words. Now, I would like to invite my colleague and fellow convener, Dr. Ramiz Rahman, to share his thoughts. He has looked after all the logistics single-handedly. So, Ramizda. Thank you, Shapun. So, again, on behalf of all the organizers, I would like to greet a warm and graceful big thank you to all the eminent speakers and participants around the globe who have taken out of their valued time for their active and generous participation and therefore making the conference immensely a successful academic event. We tried out our best to make the event successful, but if you face any inconvenience or interruption, please excuse us. We already got some suggestion, but we welcome more constructive suggestion and comments from all of you. It will help us to hosting such program in future. Every academic event, as Shapun mentioned, that there are some people behind the scene. Always there are some important supports. So
without support of our young researcher and various technical team of ISI Kolkata, it would not be possible to conduct this event smoothly. My heartfelt thank goes to all of them, and let me allow to mention at least few names here. In this regard, first I convey my thanks to the research scholars of the Department of Applied Mathematics, University of Kolkata, Mr. Amit Kundu, Mr. Atanu Bhunia, Mr. Indranil Bishwas, Mr. Priyobroto Chor, Mr. Stephen James, and Mr. Shubhobroto Bera, and the research scholars of Physics and Applied Mathematics Unit, ISI Kolkata, Ms. Sutapa Shah, Mr. Shubhendu Ghosh, Mr. Anando Das Maiti, Mr. Tathagato Gupta, and Mr. Saurabh Das for their continuous support and dutiful presence which ensure the smooth running of the conference through Zoom and uninterrupted live telecast of the conference. I would also like to express my sincere gratitude to the Office of the Physics and Applied Mathematics Unit, ISI Kolkata, Mr. Jayanto Das, Mr. Badal Maiti, and Mr. Sanjay Mollik, and the technical team of the Computer and Statistical Service Center, Audiovisual Unit, Electrical Maintenance Unit, Guest House and Canteen of ISI Kolkata for their kind help and support. Finally, before I conclude, I again thank you all for being an integral part of this eventful conference, ICQIF 2022. Thank you all. Thank you, Rameshja. Now I invite my fellow convener, Dr. Indrani Chattopadhyay from Calcutta University, to share her thoughts. She has helped us in articulating the schedule and in many other tasks. Indrani.
So, being an outsider, I would like to express my gratitude to particularly this host institute, which take all these responsibilities, the administrative, academic, and technical staff of this institute, all my fellow organizers, my fellow conveners, particularly my fellow conveners who take all the workload so that we can just stay and enjoy the whole program. Actually, I may say a wonderful journey which started from the from making friendship with qubits and lead us from atomic to biomolecular modes and all the different interesting topics. And I particularly thank the learned speakers who for their acceptance, for their presence in the whole program. We are overwhelmed by your acceptance and your response, and I also thankful to the great number of participants who unfortunately got vanished in most of the talks in Zoom platform at least, but well, this happens sometimes. This is all in all a wonderful experience, and I look forward for a actual offline interaction which will lead us to some real life correlations and all. Thank you all.
Thank you, Indrani, for your nice words. And now, some of the participants have drawn our attention by attending the conference very regularly and asking relevant questions or providing feedback to our speakers. We would like to hear directly from you about your thoughts. And as we have already heard, it was an honor to hear something from Professor Reinhard Werner about our conference, and he was our very regular participant and speaker, we all know. Next, I would like to say
few words from Professor Ajit Iqbal Singh. She is here, and also she has written a nice poem like things for us, and we will be sharing it with you. Also, she had sent me our voice message. I think we can read it from here. Let's see. Okay, Adam.
So will you please share the PPT? I'm going to speak.
Preeti, Sangmitra and Indrani Didi, Archan, Devashish, Gurprasad, Som Shubro, Supratik, Ramesh and Swapan Dadaji. How could all the wise men here online go, zooming from the super galaxy to make friends in a columnar row?
You have to also move the slides. No, hello, Oit ma'am, are you there?
Yes, I'm there. Shall I speak?
Oh, so could you please read it then? It would be better. Okay,
fine,
thank you very
fine,
much.
I'll speak. Okay. How could all the wise men here online go, zooming from the super galaxy to make friends in column or row and faster than anything that I can see? But not busy, not just in surface level talk, in deep information with foundation, provoking reflections and new musings walk, surprising connections and wild experimentation, perplexing Euler and many for hundreds of years gone. 36 officers have also played a motivating role in different reincarnations and Latin rectangles planned with vacant positions for quantum entanglement goal. We all learned how to factor a polynomial when we were at school, identifying 1 and xj with spin up and spin down at jth level can make it for entanglement a quick good tool. The moment that I heard is gravity quantum, and then the reality check. My old poem on sunset, fast and masked. To put all things quantum in your basket, a wave went down and soared high again. Newton, your law of gravitation is a lost game. The sun watched his daughter's defeat and spread all its grandeur in red. Beauty is the cause of many a pause. This weakness of the wave landed it in us enclave. And we have to make good of this sunset of the conference because all quantum bits are in our lap to be looked after, to be thought after, to be worked on. And we have set up good context to establish that well. Thank you very much for this wonderful conference. Long-lasting, long conference with long-lasting impact.
Thank you, Ajit Madam, for your nice words and the poem. Okay, now I would like to invite Professor Shivashish Ghosh, who has not only just regularly participated, but also has saved us in many occasions by chairing. Is he available here now? Don't see. Is he? Okay, sorry, he is not available. So, do you have Manik Bonik? He is there, right? So now,
Shapanda, it's a great event, Shapanda. So thanks to all the organizer and the convener to take this responsibility for a long 10 days long journey and organizing so nice, great talk. Actually, I think it will motivate most of the Indian students to do good research in comparison to world level. That will in comparison to the world level, and that could be this conference will be one of the starting building
block at this point. So all credit goes to you, all this organizer and the convener. Thank you. Big hand to you.
Thank you, Manik, very much for your inspiring words, and definitely it will motivate us to manage future events like this. And now, to all the participants, please give us your feedback so that we could improve ourselves in the future events. Please write it in the chat box, or we'll give 2-3 minutes if you would like to unmute yourself and you can say it directly to the audience. So we'll wait 2-3 minutes. Before concluding, let me announce to all our speakers, especially the younger ones, that if you would like to have certificates for your talk, please email us with your name, your institute's name, and the title of your talk. We'll give you a certificate. So we wait 1 or 2 minutes if anybody would like to give any feedback. And is there anything in the chat or maybe? Yeah, maybe can I add something? Yeah.
Yes, please go ahead. Yes. Prashant, go ahead.
You know, I must say the way you people have conducted it with, younger people getting exposure plus very experienced people talking more details about, the intricate structure of quantum information is wonderfully done. Very right mixture of old and young and experienced and knowledgeable. Very beautifully done. Truly enjoyed it. All moments of it. Thank you.
Thank you, Prashant. Thank you.
Thank you, Prashant sir. This point also has been mentioned during the inaugural session by Professor Orchonis Majumdar that it is really mixed events from many perspectives, different age groups, from many nationalities, and I mean, also, invited speakers, contributory speakers, and young students, everyone. Also many topics. I mean, as I said, quantum information now has so many branches, but we have tried our best, and hopefully we have been able to cover most interesting branches. Okay, so we now conclude this session as well as the conference. Thank you all once again for your kind cooperation and participation. Hope to see you in the near future, most likely in physical mode. And goodbye.